Hello, good morning, everyone. Let's start. My name is Marcello Romano. I'm a professor at the Technical University of Munich, and I will be chairing this first session. The first presenter is Mr. Scott Ziegler with Space Kinetic, and the title of his presentation is From Defense to Dual Use, Applying the Needs Criteria to Commercial Space for Effectiveness, Survivability, and Cost Effectiveness. Please.
Thank you. So just a little bit about me at the outset. I'm one of the co-founders of Space Kinetic. Is this working? No. You know what? I'll do the hand setup. Better now? Ooh. So as I was saying, I'm one of the co-founders of Space Kinetic. I'm the CTO. So my background's more technical. I got my master's at UC Berkeley in mechanical engineering. So for what you're about to see, this starts on my side and goes from there. But essentially what Space Kinetic's building is a system that mounts onto a satellite. And in simple terms, think of it like a trebuchet strapped to a satellite, where we will physically spin up a rotary launch arm and launch another satellite. So assume that we're doing space-to-space operations, where the release velocity at the tip of that arm is the delta V that we impart on a payload to put it into an entirely new orbit. Now, there's a lot of cool things that you need to figure out to actually be able to do this successfully. I know it seems simple, but you need to actually launch it in the right direction every single time, right? You need to make sure that you don't spin your spacecraft like crazy. You need to make sure that you can actually launch enough things to make this interesting, right? If we only launched one satellite off one satellite, there's no real utility. But if we're able to put a magazine with 100, 200 different effectors on board, now we can do something fun. I'll get into applications in a bit. But this is the core premise of this technology, which is changing how we actually move in space and trying to pull in something like drone economics, where you're stripping away the entire satellite to do a mission, and you're only moving the individual payload. Of course, you still need a little compute, you need a little battery life, a little power gen, but you move away from the multi-million-dollar satellite to do the one thing into something entirely new. And the way that we're going to frame this for this talk is around the NITS criteria. Now, I don't know if any of you are history buffs around the old Ronald Reagan Star Wars program, but the NITS criteria came out of that, where we're looking at 3 criterion. They're simple, but they're hard to follow. One is it has to work, so it's effective. It has to be resilient and be able to survive. And it has to be cost effective at the margin. Cost effectiveness kills a lot of things. We all can make a really beautiful multi-million, multi-billion dollar system. But can we get it so that we can compete effectively and someone can't just try and outspend us with a dollar-to-dollar ratio that's more favorable in their direction? And this isn't just for threats and defense operations. This ties to commercial activities. For us to successfully succeed doing interesting applications like debris mitigation, we need to figure out how to make the solution as cheap as fixing the problem is, or we won't get the funding to be successful. Now, I will hit a little bit on dual use, because from my personal perspective, if we want to have a really cool space economy, we have to figure out how to protect and defend it. And that means we're using technologies in such a way that we can do both commercial applications as well as defense. And that allows us to better understand the threat landscape that we're currently in. Because these days, we have to consider cyber attacks. We have to consider jamming, all occurring in the space domain. And we have to figure out how we can operate commercially with these effects potentially occurring. So to get a little bit more into our system, if we actually think about a specific payload that's sitting on board, it might sit for a couple of years. It might just be waiting there until we have a mission, because obviously the payload doesn't have to be this super robust system now. But when we're ready to actually launch, we're going to give it some information, preload it, we're going to spin up, and we're going to toss it out the door. And we get our resiliency because we're actually scaling. We're very quickly manufacturing and making as many of these as possible to then deploy on demand. And then we're driving costs down because we're working at scale, not bespoke, custom-created individual payloads that cost millions of dollars to build one, but we can drop costs significantly into the tens of thousands if we build hundreds. Now, applications are quite varied. We can even push this further than what you see here. But we can do stuff like space situational awareness. What do we want to do if we have a satellite that's having a problem and we want to inspect it? We can launch one or many payloads. If we can get our effector costs down to $30,000 per, this becomes very cheap to actually analyze what went wrong with our bespoke satellite. We can create constellations that are set up to remove debris that give us global coverage to be able to look for hotspots and can adjust to the top priority list. We even do stuff like orbital logistics, where we actually move payloads around in space, be able to move fuel, move between LEO and GEO and beyond, and then connect into ISRU, as well as in-space manufacturing type activities. In case you want to see something move. So we built hardware in our facility in Albuquerque, New Mexico. Dr. Mortari has visited us several times now as we've been building this out, and it's been very exciting to see something he came up with several years back around debris remediation, be able to see the actual hardware get constructed and built and tested. Now, as we continue to talk about resiliency, we have to talk about how do we actually expand at scale. And this is where Space Kinetics pushing for our most recent acquisition, which was a facility in California where we're building out our own R&D space with 24,000 square feet. And then when we look to the future, where we're building out effector manufacturing and additional space vehicles being built across the country. So I already talked about myself. I have a co-founder that's here in spirit, who's actually out in Orlando today. Very excited to have different folks on the team. Dr. Mortari has been with us for the past couple of years as an advisor, helping us with his very varied skill set. Some of the constellation work that you won't see here that we presented, we've been very excited to have his help with in building. And of course, he's also been helpful as we've designed and developed the most optimum system we can. So that's it for me. Hopefully it was interesting.
Thank you for the presentation. Any questions?
Hey, great presentation. So what kind of masses are we talking about with regard to the kinetic energy you are going to be imparting onto the satellite that's going to send it to these kinds of orbits?
Sure. So we're looking at between 2 to 6U satellites that we're essentially launching. 2U is sitting around 2 kilograms. Now, we did make the satellites chunky, so we were looking at about 2,800 kilograms for the satellite, plus our whirlwind system that's physically doing the spin-up, plus the bus. Plus the other payloads that are on board. So if we're hanging out in, let's say, GEO, and we spin up and launch at 350 meters per second, the actual kickback on the bus itself is about 0.9 meters per second. So that means you have to have propulsion on board if you want to continue doing station keeping, or just hope that your next mission is the exact opposite direction, the exact same place. Very probable, I'm sure. But it all becomes proportional to mass, to your point.
And that was kind of my question, is how do you handle the momentum exchange? Mm-hmm. What's your technique?
Sure. For the actual angular momentum when we spin up, even our little system that's in Albuquerque right now is 600 nms. So it's a lot of momentum. Can't find a reaction wheel that'll actually work effectively. So we actually built our own fat and sloppy reaction wheels that'll soak up all of that momentum, and then we let the bus handle the unique pointing. And then, of course, for linear, we just use the propulsion system itself. If we want to get cute with the angular momentum, we can spin up, launch clockwise. Then we spin down. And our next launch will be counterclockwise. And that way, every other time we alternate. We'll build up error eventually because it's not perfect, but that helps minimize how many desaturation maneuvers we have to do. Sure.
Just a quick question. And because you have a sort of store of satellites, do you think that we need to change the requirements of these for the launch of the satellite, I mean, with respect to the standards?
On the payload that we physically launch off our satellite?
Because yes. Actually you are there, you stole the satellite for, I don't know, 1 year, 2 years.
Yep.
So you need to add additional requirements?
We have to add some and we have to strip others, because the goal is to make our vehicles as cheap as possible. However, this is a centrifugal acceleration entertainment system, shall we say, because we can go all the way up to 10,000 Gs when we spin up. So we have additional structural requirements and component level requirements to handle that G loading. Conversely, we don't necessarily need to have a really robust power generation system, because the interface on the bus to the actual payload itself can provide heat, power, communications, etc. We don't have to communicate to the ground, because we can use our mothership as our relay back and forth.
Okay.
So it's the navigation of a new flight vehicle design, just frankly, if you think about it.
Okay, thank you.
Yes?
I also have a question. How do you solve the problem of mass variation of the bus when you launch and you in the transversal angular momentum?
So basically what you're saying is if the payload itself is not the same each time, you'll have a different amount of momentum at the tip of your arm that you have to counteract in real time. There's a couple different ways to solve it. A, if you're right at the margins, you can already sense the imbalance as the system starts to try and rotate and then calculate off of that, which would really suck. You can over-engineer the design such that any vibration that occurs from the imbalance in the rotary arm isn't affected in the shaft. And then you make your actual mechanical inputs between the bus and the actual whirlwind system such that they have vibration tolerant systems to a specific specification. Then you let go of it. From a purely physics standpoint, since we're spinning up, we might see a little bit longer ramp-up rate because there's additional torque needing to be used. But when we actually let go of it, once we're at our effective RPM, it'll always release the exact same velocity.
But the question is also, in the picture that you showed, the plane of the rotor seems to be offset with respect to the center of mass. And in any way, the center of mass is changing as you launch. So
I understand.
How do you...
Yes. I was talking about a different problem. So in this case, the center of gravity is going to be closer to the center of the bus. And what will happen is we'll actually have some rotation motion. So instead of having the momentum storage wheels equidistant between each other, we actually offset one of them a little bit further away from each other. And that way we can vary both the RPM on one wheel to the other wheel, to the rotary arm, and then the distance also helps us offset that momentum. So it's a very valid question.
So do you have requirements about the direction of the velocity? Because the detachment mechanism should be pretty precise. And also, how do you guarantee that the payload does not have a rotation after detachment?
So for this system right here, can you guys see my cursor? Oh, awesome. All right, so you see these two structures standing straight up. These are non-rotary, so they're not going to rotate in real time. And what will happen is we'll actually spin up. We send an activation command 1 revolution before we actually want to actuate. Our release mechanism is in 2 parts. One is physically holding the payload inside the rotary arm. The other half is on the stationary piece. Once we give the activation command, essentially we'll turn on an electromagnet. And as we pass by, it pulls back like an action on a rifle on the release mechanism that causes it to let go. And that way we're always releasing at a fixed location at a certain point in time. And then we don't have to have a control system that's going to have to be accurate to 0.0001 degree at 3,000 RPM, which is unreasonable. Can you repeat your second question, or your second part? Got it. Perfect. So you're absolutely right. We would have it start spinning as soon as it escapes the arm. If we weren't to do anything. We have a mechanism right at the tip that allows us to actually push up and then push down on the either end of the actual vehicle we're launching, so it counters that rotation as it escapes. Our assumption and requirements we flow down as we've been making these is to say that we'll have 0 to 3 RPM, plus or minus, induced, because that's a very fast action in a very short period of time. But we have gone ahead and simulated it using Siemens tools, so at high fidelity to confirm that it'll work.
I just want to add a little bit, if I skip that maybe you already say, that this system can be used for as a gas station to refuel also geosatellite. and sending a capsule of and this is one thing. The second thing is that I don't know if you are enlightened enough the fact that it doesn't require fuel, basically, for functioning, basically.
Yep. Well, if you look at in-space logistics, to your point, and we assume that we have a really cool economy where we're moving stuff from LEO to GEO, then we get into your point of actually launching at exactly the right spot and the right time in different directions. And that's where we can get to pretty close to a thrusterless constellation where we're exchanging goods back and forth. And that's kind of what you're actually seeing in this constellation, where we start out polar and then we adjust once we get into GEO our inclination until we're equatorial, and we can adjust between each of these individual nodes in handoff payloads as we go. Thank you for tracking that out for me.
Thank you again.
Thank you, everyone.
So I will present the second paper, again, in Marcello Romano, Technical University of Munich. Before that, from 2001 to 2024, I was a tenure track professor at the Naval Postgraduate School in Monterey, California. And my topics are astrodynamics, orbital robotics, and space systems engineering. Today, I will present on Lyapunov-based low-thrust control and stabilization of a tether satellite system in arbitrary attitude configurations. I would like to acknowledge my co-author, and actually the main author of the research, Stefano Aliberti, who's a PhD candidate. So the rationale for this research is as follows. Typically, tether satellite systems are flying, when they're flying vertically, stabilized by the gravity gradient. The idea is to stabilize the tether in a different configuration, and in particular, even in the cross-track configuration. So that, why doing so? So to provide a large aperture laterally, cross-track, like in this figure, the second figure here, in order to carry out missions such radar sounding for measuring the thickness of ice at the poles and investigating the subsoil. Why doing it with tether and not by formation fly? Well, because formation fly, for instance, if you fly two satellites into different plane with different inclination, you get to this configuration, but only twice per orbit. By doing with a tether, if we can stabilize it in cross-track, we have that capability of doing measuring all over the orbit. So this is the rationale. Initially, I thought to stabilize by using differential lift in LEO. And that's possible according to simulations. However, the induced increased drag basically shorten the mission to just a few months. So the second idea was to use instead electric propulsion. So we are basically currently studying this second solution. So electric propulsion on the two extreme satellites that are providing basically a drag-free flight, plus they are providing the component of lateral force that is needed in order to keep the tether in tension, which otherwise will be, of course, compressed by the relative mechanics of the proximity flight. So the goal, again, is to stabilizing, to find a control to stabilizing a tether satellite systems in this way at an arbitrary configuration. So not only cross-track, but also possibly other configuration. So first of all, we start with a dynamic model, and for the control design, we use a Dumpel model, so a classical model of considering the system made of two satellites and basically a rigid connection instead of the tether. And typically, if you consider the typical expression for the state variable in alpha beta with the angle of the theta measured on the vertical plane, you get a singularity or at the cross-track. So we just had to change the variables with respect to the usus and consider the horizontal plane for the definition of the angle gamma and delta. After that, we can write the equation of motions for the damper, for instance, using the Lagrange approach, and the equations of motions are reported here on the left-hand side. So gamma double prime, delta double prime, and epsilon double prime are on the left-hand side. Gamma and delta determine the configuration of the system. Epsilon is the strain of the tether, and prime because we are deriving with respect to the true anomaly, considering that the orbit, the nominal orbit, is circular and Keplerian of the center of mass, of course. In order to, we use this model to design the controller, but in order to provide a preliminary, at least, validation by simulation, we use a higher fidelity model for the system, and we use a lumped mass approach. So we divide the tether basically in intervals, and we consider the mass of concentrated at a few points along the systems, and we consider a damper and a spring in parallel for each subpart of the tether. By doing so, then we write the equation of motions for this system with much more states than the Dampel approach, by using as vector states the relative position, so rho, of each of the lumped masses with respect to the overall center of mass of the system, and second state, vector state, the vi, which are the time derivative in the inertial frame of this relative position. And then we take the time derivative, but in this time with respect to the hill, to the local vertical, local horizontal reference system. By doing this, that is not the usual way of expanding the velocity and acceleration, we avoid the dependency of the derivative of the states on the time derivative of the angular velocity. We, of course, then project the equation into the Hill Cartesian coordinate system to obtain the scalar version of the equation. And for each of the lumped mass, we consider the gravitational force, the drag, and the tether effect in terms of forces on each of the lumped masses. Now I'll cover quickly the design of the controller. We based on the Lyapunov indirect method, and we use, as I said, the Dampel model. So we linearize the system, and before doing that, we basically redefine the state variable gamma, delta, and epsilon in order to then have the origin at of the state space at the configuration that is our desired configuration to reach. Then we assume that at the two extrema, at the two satellites, we have forces equal and opposite, produced, as I mentioned, by electric propulsion, for instance, and we give an assumed expression, analytical expressions of these force components as polynomial dependent on the state variables. From that, we can, of course, compute the generalized forces. So we have basically 7 times 3, 21 design parameters that we need to determine. By imposing that the desired configuration be an equilibrium point, equilibrium state, we obtain 3 of these 21 parameters, these constant feed-forward parameters f naught, x, y, and z. In order to obtain the other 18 parameters, we do the linearization around the equilibrium point, we obtain the Jacobian matrix, and then we basically impose that the system behaves like 3 damped harmonic oscillator having natural frequency A, B, and C, and damping coefficient D, E, and F. And so we can basically, by equating element by element the A matrix from the dynamic model to this desired A matrix, we obtain the values of the control coefficients AX, AY, and Z, BX, BY, and Z, and so on and so forth. So we obtain the other 18 values. We have an analytical expressions of those 18 gains for the control. Numerical validation, at least preliminary. We consider the control design by using the dampened model, but we do the simulations by using the higher fidelity model, using the lumped masses. In particular, we divide, in this case of this simulation, we have 5 lumped masses in addition to the masses of the extreme satellites. And we consider, for instance, a length of the tether of 200 meters, a linear density that corresponds to a tether made of Kevlar with a diameter of 1.7 millimeters, the Young modulus corresponding to the Kevlar, and an orbit that is a nominal orbit that is of 450 kilometers of altitude. A masses at extrema of 50 kilograms of the satellites and surface of a quarter of a meter square. One of the simulations, starting from an initial configuration of gamma, delta, and epsilon having these values, and wanting to reach another quite far equilibrium configuration. By running the simulation, we see that the system is basically asymptotically stable to the equilibrium. And I think there is a video, let's see if it's playing, of these simulations. Doesn't play, sorry. In the video you will see that the modes of vibration are excited for the tether itself. Anyway, this is the evolution of the attitude, the evolution of the control forces. So we need control forces for the maximum channel control. We need about 0.05 or 6 Newton, of course. Second set of simulation, we vary the masses at extrema, the length of the tether, the altitude, and we scale the surface accordingly, and we run 1,000 simulation for this. This is the distributions of the various parameters, and we obtain basically, again, with different transient, we obtain, again, a stable system. And finally, we want to do some preliminary Monte Carlo analysis of varying the parameters in a certain way. That is, we have the control that is tuned to nominal values, these 3 ones, and then we change these nominal values with a standard deviation of 10% of these values. And we obtain basically a dispersion, and we have, at the end, in this case, we have a bias for each of the cases, but still there is this stable behavior for large, basically slewing maneuver type of motion. So in conclusion, we design a stabilizing control for a tetrasatellite systems that enable the system to fly in an arbitrary attitude configuration, And we think this is the first time something like this is achieved, and even to enable a tethered satellite system to fly in cross-track. We use a Lyapunov indirect method, the Lyapunov indirect method, to find the control, and we did some higher fidelity initial preliminary validation by simulation of this control logic. And that's it. I thank you for your attention. And I will be happy to entertain questions if there are.
So very interesting, and having worked on TSS-1 and TSS-1R, which both failed, I find this application really interesting. A tether system is intrinsically complex, so this is a drawback. What are, in your opinion, the advantages of a tethered system which requires control and a control of two satellites in free-flying information?
Yeah, good question. Of course, we ask ourselves this question, and the main advantage is that we connect the two satellites. So we basically, in a sense, we fix 1 degree of freedom, in a sense, of course. And we have the possibility of communicating between the two satellites, because we can embed, say, fiber optics on the cable. But possibly more importantly, we can distribute over the aperture sub-satellites, for instance, for synthetic aperture radar. And so we have a more a constraint with respect, physical constraint on the distributed systems with respect to free-flying satellites information flight. The final answer is not yet. We don't have the final answer, which is a trade-off analysis that we need to complete, basically. Yeah.
Thank you, Marcello, for your very interesting work. Just a question. In this simulation, okay, in these results, you consider the eccentricity equal to 0. But if not, maybe the system is perturbed, and I don't know if you consider that. Even because, actually, as far as I understood, you consider the tether like a flexible system. So this could have some perturbation for the dynamics. Okay, thank you.
Yeah, thank you for your question. Actually, we consider the nominal Keplerian circular orbit for the design of the controller, but then when we do the high fidelity simulations, we consider J2 effect and drag at each of the lambda masses. So the center of mass is decaying slowly, but is decaying, and so the theta dot is changing with time. So we consider that effect. We consider the effect of the perturbation, at least up to J2, and the drag. So it's included in the higher fidelity simulation. Is that answering? Yeah. Any other questions? Okay. So, thank you. Our next speaker, I invite you to the podium. And actually, if you can please introduce yourself, because I don't have your bio, but yeah. Oh, great. So I introduce yourself. So, Dr. Trent White is an aerospace research engineer for the Army Research Laboratory, and is stationed at Texas A&M as a visiting scholar. He is a DoD SMART scholar, currently serving out phase 2 of his SMART requirement, and graduated from Texas A&M University in 2023 with a PhD in aerospace engineering, focusing on data-driven, reduced-order modeling of nonlinear static aeroelasticity. Dr. White has experience in wind tunnel experimentation, design and control of adaptive structures, smart materials, and a variety of numerical and optimization methods, including the theory of functional connections.
Alrighty, thank you for the introduction. So today I'll be taking us back to that differential equations class we might have taken in undergrad or graduate school. So we're talking about solving discontinuous differential equations using the theory of functional connections. And so as you might have noticed from the bio, I'm no mathematician, and this is really not related to my primary work. This is kind of a side project of mine that began about a year ago. I thought I might use TFC to solve some trajectory optimization problems, and as I was refamiliarizing myself with TFC, I came across this paper where finite element method is being compared against TFC for solving Timoshenko beams. And the results showed that for every continuous loading case, TFC outperformed finite element method, but for the single case where there was a discontinuity in loading, FEM outperformed TFC. And I thought this was really interesting, and the reason for this is rather straightforward. If you assume your field is globally smooth, but it's not actually smooth, then obviously you're going to generate some error. And so I talked to Dr. Mortari about this, and he kind of confirmed that the fundamental assumption for a lot of the developmental work for TFC is that the field is globally smooth. And so this kind of became a side project of mine, working with Dr. Mortari, of kind of extending the theory of functional connections to discontinuous systems. And we came out with a paper earlier this year, and so I'll be talking about kind of the overview of that today. So the scope of this effort is really straightforward. We're just talking about 1D inhomogeneous differential equations, where, and linear and nonlinear doesn't matter. And so the discontinuity lies on the forcing function, right? And this is very convenient because if we have an nth order system, then we know that the derivative of the field lies in the nth derivative. And so it's very convenient. If we also then know the location of, say, that discontinuity, then in addition to these boundary constraints, we can also define these continuity constraints. So the nth derivative, so any derivatives lower than the nth derivative, right, we know are continuous. So that's what we're working with here, very straightforward. And now I understand that, right, we're here celebrating Dr. Mortari, but not everyone is maybe familiar with theory of functional connections. So TFC basically extends classical interpolation to functional interpolation, where you have n-linear constraints that are satisfied by the entire family of interpolating functions. And really the simple way of thinking about TFC is that it's really a systematic approach of converting constrained problems into unconstrained problems. So for 1D cases, we have two formulations. We have the eta formulation and the switching projection formulation. So I'll just talk to the eta formulation for now. So we have a constrained functional, which is comprised of a free function g and a set of weighted support functions, where the weights on those support functions are termed coefficient functionals. And so the crux of TFC really is identifying or computing those coefficient functionals such that all of your n-linear constraints are satisfied. And so we can go through a quick example here. So say we have a two-point boundary problem, and let's assume we have support functions, two support functions, 1 and x. And so we can write the constrained functional as just our free function plus eta 1 plus eta 2 times x, right? And so now we have two unknowns, eta 1, eta 2. We have two constraints, so two equations. We can solve for the coefficient functionals in terms of our free functional. We can plug that back into our constrained functional, and you can see on this right side that if you evaluate at the bounds, then you obtain those constraint values independent of that free function, right? So we can choose g to be anything we want. So now how might we go about extending this to discontinuous systems? The simplest way, kind of most straightforward in terms of stepping from that simple continuous case to a discontinuous case, is just make our constrained functional piecewise, right? So we'll chop up the domain according to the discontinuities, and then each domain will be assigned its own coefficient functional with its own local free function, weighted support functionals, support functions, and then we'll just go through the same exact process. The only difference now is that we also have these continuity constraints that we have to impose. But we build those into our support matrix just like we do with boundary constraints. And so there's nothing too different here. So I thought it might be helpful to maybe compare this against how we might have solved kind of classical discontinuous problems, say in a structural mechanics class, right? So we have a bending beam constrained between two walls. We have some jump in the loading. So how we would solve this, right, is split the domain, integrate both sides independent of each other. So we have this fourth order polynomial, and so the unknowns are going to be the 4 coefficients. So we have a total of 8 coefficients unknown, but we have 4 boundary conditions, 4 continuity constraints, right? We can solve that. So the thing to point out here, right, is because the problem is so simple, right, in integrating, right, we kind of have that fourth order polynomial form. So all that we really have to do is solve for those coefficients. We're kind of simultaneously resolving the form of the field as well as the constraints. But in the event, say, we have some spatially varying elastic modulus or cross-sectional geometry, we can no longer take that approach, right? We can use brute force numerical integration if we want, or we could maybe start stair-stepping the geometry and assume kind of constant cross-sections over each element. And right, we can do that. But with TFC here, we can easily resolve those types of situations because we have decoupled the constraints from the form of the displacement field. So that's kind of the power, right, in employing this type of approach. And we can visualize this. So let's just say we have 3 discontinuities, C2 discontinuities, right? So discontinuities in the second derivative. Right, we can go through, define our boundary conditions, continuity constraints, build out our support matrix, solve for those coefficient functionals, plug back in, and I can just randomly seed, say, a bunch of quadratic local free functions, and you can see, you know, we get those nice stair steps, those discontinuities, but then once we get to the first derivative and the constrained expression, we're seeing, right, it's all continuous, okay? And so really the idea here is we're just basically enforcing continuity through a set of weighted support functions, just like we do with continuous systems for TFC, right? Nothing too different there. You can take an alternative approach where, so again, working with just the eta formulation, we can, again, maybe just look at a simple 2-point boundary value problem, C2 discontinuity. We can impose just our boundary constraints using the weighted support functions, right? And you can see, right, that those terms are globally continuous. So what that means is that the free function has to encode that discontinuity, right? And we can do this in a rather straightforward way. So the second derivative of the free function can just be defined, again, as a piecewise function. We can stitch local free functions together using the Heaviside function. If you integrate the Heaviside function, you can see that's the ramp function, right? It's continuous. And so just by simply integrating, we can kind of enforce, right, continuity. And really what's happening here is as you kind of integrate across the domain, you're basically applying a sequence of transformations to the local free function, translations and shears and whatnot. And so basically continuity is enforced through these transformations to these local free functions. Now, these terms might be look messy, right, and difficult to work with. But if you actually start grouping the local free functions together for each domain, you actually get this nice structure that forms. And you can group all these local free functions into what we're calling P functionals, right? And so there's a generalized form for these P functionals in the paper. I don't have it here. But basically, right, anytime you have now some linear differential operator acting on, or a differential operator acting on your free function, you can just express that as a summation of your P functionals. And so the nice kind of philosophical, I guess, advantage of this approach over maybe the S-embedded approach, the previous approach, is that the application of TSC to continuous systems and discontinuous systems is identical, right? There's no change. Similar to how with TFC, there's really no change in how you resolve boundary value problems or initial value problems. And so we'll look at some examples, just some details there. The local free functions are all just assumed to be weighted Legendre polynomials, so the coefficients on those polynomials are unknowns. And then because we're splitting the domains, we're going to use CGL, Chebyshev-Gauss-Lopata points, to discretize the domain so that we can distribute more points to the ends of each local domain, just to avoid, approximation error due to like Lagrange's phenomena. And we're going to remove those points of discontinuity from the system of equations whenever we're actually solving for those weights. So So the first example, just a simple second-order boundary value problem. There's nothing really too, kind of complex going on here. Right? We know the analytical solution, and then basically the idea, whether you're using that G-embedded approach or S-embedded approach, as you increase the number of basis functions, you get this nice spectral convergence going to machine precision, machine error, and then you get a really nice kind of condition number, right? Remains small and grows very slowly. And we can compare this against, say, a central difference scheme, and basically after 2 basis functions, we're outperforming central difference. And now we just have a third-order boundary value problem, right? Nothing really different here all that much. In terms of implementation, it's rather straightforward to make that switch. Again, same kind of behavior in terms of error and the condition number, right? So still seeing, right, some robustness to the method. But I wanted to point out is that the coefficients for the differential equation, the Laplace transform is not known, right? So we can't use traditional techniques that we might use for discontinuous systems. And so that's kind of an advantage here. And then finally, I wanted to make the problems a little bit more complex, so I just added in a radiation term to the typical heat transfer equation. And so we have 5 distributed loads across this rod with some variable geometry. And so in terms of going from some type of linear discontinuous differential equation to this nonlinear problem, the only thing that changes with the formulation is we just have a nonlinear least squares, right? And that's nothing new to TFC. We've been doing that for a long time now. And we get kind of similar behavior in terms of, residuals dropping, condition numbers staying small and growing slowly. And then, right, how we might use this in practice is, right, maybe we want to optimize, right, those heaters, right? We want to minimize power consumption, and we want the minimum temperature of over that rod to be above some, minimum temperature, right? And so I just threw this into MATLAB real quick just to kind of illustrate, how we might use this for a practical engineering problem. And you can see, right, we get those nice discontinuities in the second derivative of the temperature, but first derivative and the actual temperature field are all continuous. And so that's really all I have. And so I'm looking for some interesting problems to solve with this. If you have any ideas, that would be great. But really, we're just extending TFC to these types of discontinuous systems. I'd like to go to 2D at some point. We'll see when I get there. And yeah, I'd be happy to answer any questions.
Are there questions?
Very, very interesting. Have you compared it to, I guess, co-location or other schemes where you're sort of approximating the or enforcing the structure via basis functions that are not the TFC? Like, how does it compare? And
So I personally haven't done that, but I know there probably has been work in the past where TFC has been compared against. I don't know the answer to that unless.
Many different TFC has been compared with different for different I don't know, there is nothing special here. Collocation method, like the spectral method, basically you have the problem that in order to embed the constraints, they had the constraints as a data during the discretization. This means that they will not respect, and you get the error like this, while here is analytically embedded, the constraints. So you completely forget the constraints.
And in that case, that was led by one of Daniela's students, right? We knew, for example, in that case there were 2 discontinuities, but we didn't know. It's usually a max, min, max for a landing, And there were a couple of, the only thing that we didn't know were the discontinuous were. In this specific case, however, we applied the first methods. We didn't know about the G methods at the time, just 5 years ago. And in that case, we put another loop, okay? So everything went smooth because it's basically, we used Chebyshev spectral convergence on the point where you didn't have discontinuity. But in the discontinuity, you enforce the constraints that way. It worked very nicely with the only difference that we had to put another loop to find the switching times, right? Be interesting to see what we can do with these things, just reapply to that problem. That's what I was thinking.
Yeah.
Any other questions? I have a question. So you're assuming that the position of the discontinuity is known.
Yes. Yep.
Do you have any idea of how to extend where that is not?
Haven't thought a whole lot about that. Right. I mean, so you could add an outer loop, right, and just solve for it. Would it be possible to somehow incorporate those locations as an unknown and simultaneously solve for them? Yeah. I don't know what type of an algorithm, right, we would use for that, or what that would look like. It's kind of a final system of equations, but I feel like it should be doable. Yeah.
Okay. Very interesting. Yeah.
Usually, discontinuous differential equations are solved using Laplace transform, things like this, where also there is where the discontinuity happens. If you think about, for instance, discontinuity like turn on or turn off some like a bang bang or things like this, this can be solved, for instance, with an external optimizer. I don't know. The first thing that comes to my mind is a genetic algorithm, for instance. But also, in the I don't know if it can be applied, for instance, when we solve the optimal control problem for energy and time energy. Also here is you need to find some quantity that are not specified at the beginning. Okay.
So if you just solve the TFC with the smoothing, parameters for bang problems, it works very nicely. It's just time consuming because you have to do the iteration, the usual continuation problems. But I think it would be more exciting to see how we can extend this to using actually the G embedding. I would be interested to look at it to see in case of unknown, how do you do that directly?
Okay, thanks again. Our next speaker is Alan Aguilar. He's a graduate student assistant in the Systems Engineering Autonomy and Knowledge Lab here at Texas A&M. He's a PhD candidate and is working in the Systems Engineering Architecture and Knowledge Lab, I mentioned that, under Dr. Daniel Selva. His research focuses on autonomous Earth observation missions with an emphasis on developing decentralized satellite constellations capable of rapidly detecting and monitoring short-lived environmental events and their impacts on communities and Earth systems. The title of his presentation is...
it's kind of a mouthful.
Decentralized autonomous operation methods for agile Earth observing satellite constellations under dynamic event monitoring missions. Please.
Thanks so much for the introduction. Hello, everyone. My name is Alan Aguilar, and as mentioned, I'll be going over my work on decentralized systems, particularly for Earth observation. Now, obviously, satellites have become a massive part of Earth observation systems monitoring. Not only do they offer global coverage and temporal frequency, I guess a fixed temporal frequency of their measurements, for different events detections and all that. But however, if we just base our estimations on single satellite missions, which are the current state of the art, we notice that there's like very long periods of long gaps in between measurements of particular positions. And when you have events that last very little time, this can be problematic to constantly monitor these events. Now, as we increase the number of satellites, it obviously goes down as a problem. The current tendency seems to be going from single satellite missions to constellations, and eventually hopefully scale up to a system where we not only consider many satellites in their measurements, but also ground stations and possibly aerial measurements. This is all enabled by the fact that we have easier access to space and easier ways of making satellites in a sustainable manner for larger constellations. Now, when it pertains to actual Earth scientists, a lot of the things that they are demanding from us on the system side of things, not only just being able to observe these events, but closely monitor. A lot of the requirements are kind of focused more on like noticing the change and how things evolve in different events in Earth systems, and primarily the large gap in these observations come with very short time scale events. So I'll be using events a lot in this presentation, but by that I mean situations such as floods or algal blooms that have I guess time of development around the hour to minutes time scales. And because, satellites, if you have a single satellite, it takes about an hour or more to, in the best case scenario, to reobserve a point. These types of events are very challenging for scientists to actually keep track of and to actually know what's happening beyond just noticing that they're happening, but also, all the changes that we mentioned are interesting to them. Now, the current operations, not only do they have single satellites, but they also have this limitation of how the tasks are actually scheduled. You have a ground station making up the plan that gets uploaded to the satellite. Satellite performs these instructions and then downloads the information that is then processed on the ground and then used to come up with new sets of operations. Now, with the limited time in between in between communications with the ground, you might have events that are missing, were not being monitored, or that occurred and were actually measured by the satellite, but because it was unable to actually process the data on board, it was unable to react. And you may have situations where the plan that is actually uploaded might be outdated by the actual plan that you're performing. In this little diagram right here, you may imagine that the blue dots are a river, and as you're measuring different points on a river, you notice that there's a flood, and the red dots are communities that live nearby, and therefore it will be more interesting to see if there's damage on those communities rather than just seeing downstream and how much more water there is down the river. Because of this, the current system of operations of having it all be downlinked to the ground and then uploaded to the satellites seems to be like a very massive bottleneck in these operations for larger scalable constellations for Earth observation. So how can we improve this? How can we make this a lot better? We propose the use of autonomy, and the higher capabilities that we have on board allow us to actually consider this. However, there are two big parts that need to be considered whenever we implement autonomy into satellites. One of them is having a way to consider the science objectives of our mission while also taking into account the different coordination, the operation constraints of our constellation. But if we were able to come up with a formulation for this and different implementations, we might be able to actually increase the responsiveness of our constellations to these events. We first tried to, like I said, in our work, we proposed using a formulation of missions more on the side of executable requirements that satellites can actually take as a form of evaluating performance. And you encode a mission as a set of objectives, which themselves consist of a series of requirements that possess a function that you can model different requirement satisfaction. For example, you might have an interest in seeing the number of increasing the number of observations of a particular point, but then don't really require much measurements after. So you might model this satisfaction function as a sigmoid, but you can encode all kinds of different requirements this way, and therefore you can evaluate the performance of a measurement based on the requirements of a mission. And because of this formulation being solely depending on the particular satellite, you might also use different types of requirements and objectives for different satellites that might belong to different missions, and also allow for coordination even though their priorities might not be the same. So now that we've established how we can make these decisions, how do we coordinate satellites? How do we actually give them this autonomy? By having satellites decide what to do, it kind of becomes a task assignment problem. You have a set of tasks that you want to do. By tasks, we mean observations of ground points, and then you have a set of agents, in this case the satellites, that can perform these tasks. And so the question is, how do you come up with the best assortment of who gets to do what and when? And as you can tell, there's a lot of, I guess, there are not that many explicitly written here, but the maneuverability constraint here expands to all of the observations that are performed. And so as you increase the number of satellites, the number of constraints also grows. So this makes it a very, very hard problem to solve individually. Additionally, we have two different types of tasks that we're trying to solve. So we have tasks that try to monitor the Earth and see if there are events even present. And then there's other types of tasks that try to look at events that we already know occur, and therefore we need to pay close attention to them. And it's a kind of a balancing act as to which ones we get to perform. But if we can encode this priority within the mission requirements, then this operation will be taken into account in our task assignment formulation. Now, to do this all centrally and to consider all the satellites and all their constraints is a massive challenge. Even in current operations, they tend to stay away from using exact methods due to their large runtime, and they tend to just go for approximate methods. However, if we do this on board, we have even more limited computing power. So we propose using a kind of like a two-step process to come up with these plans. The first one will be to use a periodic planning approach, where we have a new plan being developed at a fixed period that will be repaired by a much simpler planner that takes into account new information that's coming in and tries to coordinate with other satellites. In the first one, with the periodic plan, we propose using a dynamic programming planner, so they'll give us an optimal solution for the particular observation plan for a particular satellite. So this reduces the problem to just one satellite, not the entire constellation. And then as the information is coming in, we would just try to insert these new tasks that might be requested into our existing plan that was made by the dynamic programmer. So it will be suboptimal, but it will allow us to insert these tasks as they're coming in. And then we would use a consensus-based algorithm to come up with a coordinated assignment of tasks with the other agents. So now that we have our own way, I guess the satellite has its own way of making up its own operations and own plan based on its priorities and based on its capabilities of what it can do in its assignments, it can then talk to others and see if they can come up with a good solution with their information. And this is a market-based approach where satellites will propose bids based on the utility they expect to get from a particular measurement, and they start negotiating. Whoever gets the highest bid gets to do it. And if you get outbid, you may consider performing other tasks. And the idea of testing this is to see how well we can improve our reactiveness to the new events that might be coming in, the new requests that are detected from other satellites. And we first started comparing here in the top plot. You will see the probability distribution of observing events based on them being observable, so that there's enough coverage for satellites to observe them. And having a high quality plan such as the dynamic programmer increases the probability of events being discovered, versus in the lower plot you have a more rule-based heuristic that just assigns tasks as they're coming in. So having a dynamic programmer that looks for the optimal plan just for that one satellite and then coordinates has a higher chance of actually discovering new events. But if you start to look at now the possibility of events being co-observed, that is, you have more than one satellite, more than one instrument actually looking at that task or that event, by having the CBBA, the market-based approach to coordination, you see that this probability also increases regardless of what your base plan is, either the dynamic programmer or the heuristic rule-based planner. And likewise, the probability of these events being fully observed, given that they're co-observable and detected, also increases. In general, you see that there's a higher performance and higher coordination level by just allowing satellites to be able to even take their limited information to just share in bids, and that allows them to actually modify their plans accordingly. However, this current implementation was tested on a series of kind of randomized plans, so randomized events. They were not based on any historical data, so any relation between events was not considered here. But currently, that's in the works. And we are very interested in seeing how the different mission requirements and different mission objectives might impact this performance as well. Currently, in the results that you just saw, that they all consider the same priorities, but maybe having a set of satellites within the constellation prioritize monitoring, whereas the other half might consider event detection, might see different results in terms of the coordination. But that's all I have for you guys. Thanks so much. And I'll take any questions.
Questions? If not, I have a question. Could your approach accommodate for satellite-to-satellite communications?
Yes. So one of the main limitations of the consensus approach is that you obviously have very limited communication windows with other satellites. So actually, it doesn't aim to find the global optimal. It's incapable of. I guess in a way, if you had perfect communications with everybody, you could. But we just assume that two satellites need to agree on their particular plans, and they within the schedule they are able to propagate when they're able to talk to others and say, okay, if in 10 seconds I will talk to the other agents, I will schedule a message saying like, hey, this is what I'm planning on doing. What do you think? So it is considered, and then but the actual plan that comes out of that, it might not be the optimal just because they're unable to talk to everybody at once.
Okay. Thank you again.
Thank you.
Our next speaker is Mr. Jack Joshi. Jack started his PhD at the University of Texas at Austin in the fall of 2024, and is co-advised by Dr. Ryan Russell and Dr. Renato Zanetti. Prior to UT, he received his bachelor's degree in aerospace engineering from the University of Illinois in Urbana-Champaign. He's currently an NST GRO fellow and is focusing on state representations for measurement fusion and uncertainty propagation in the cislunar regime. His presentation is titled Angle-Based Star Occultation Measurements for Spacecraft Navigation. Recognition for this set, or try to transfer the presentation to a different computer.
Okay. All right. Sorry about that. Yeah, thank you for the introduction. My name is Jack Joshi, and I'll be talking about star occultation measurements, and specifically our angle-based representation for spacecraft and navigation. I'd also like to acknowledge my co-authors, Dr. Renata Zanetti and Dr. Ryan Russell. So to give a kind of quick roadmap of what we'll talk about, I'll quickly introduce and motivate the problem, and then I'll touch on our 3 different measurement models that we're exploring, and then I'll sort of set up a circular restricted 3-body problem scenario before diving into the filter performance, and then finishing with some concluding remarks. So for a little introduction, I guess fundamentally, a star occultation measurement is a measurement of a star being occulted by the moon or a body of interest. And this can refer to either the star disappearing or reappearing from behind the moon. This is particularly advantageous when the moon is poorly lit. This is in contrast to other traditional optical navigation methods, such as crater navigation, which require the moon to be well lit. And it can be it can provide position information essentially for free. So you can use a modified star tracker, so you can get attitude information, but you can also get some position information from the occultations using that same star tracker. This was originally tested during Gemini 7 and 10, and the results were inconclusive, but it's since been explored a little bit in literature, and I'll touch on that a little bit more in a second. So we, in this work, we explore 3 different measurement models. So those are the models 1, 2, and 3 that you see there on the left-hand side. And inherently, a star occultation measurement is a time-based measurement. So ideally, we'd like to represent it as a time-based measurement, but this can be difficult because our filter uses time as the independent variable. So in order to do so, we have to make an approximation, and because of this, Psyche in 2007 explored using minimum altitude as a way to map the occultation measurement from a time measurement into a distance-based measurement. And then we proposed a new model, Model 3, which is an elevation angle-based approach, as a way to allow our measurement function to still remain exact, but our measurement noise to be closer to the hardware itself. So we can see an illustration of the 3 different models on the right. The predicted measurements are shown in blue, and the true measurements are shown in green. Of course, we have our true occultation time as our true measurement for Model 1, and then for the other 2 models, the true measurement is 0. And we'll use that specifically for developing our implementation for Model 1. So as I mentioned, we need some sort of approximation for the time-based measurement, and we'll use a first-order Taylor series. So we'll truncate all higher-order terms, and we're left with the result you see on the far right-hand side of equation 1 for the predicted occultation measurement time. While this is a linearization, the resulting predicted measurement is still highly nonlinear, as it is a function of both the predicted elevation angle and its time derivative. And then we can see the measurement function shown in equation 2 there, where the main source of measurement error in this case is state dependent there on the right. So in order to represent the measurement function exactly, Psyche, as I kind of mentioned before, in 2007 proposed this minimum altitude approach, where essentially it's represented by the h-bar term up there, which is maybe an oversimplified visual of what is actually happening, but it's a function of both the spacecraft's position relative to the moon, as well as its position relative to the star. and it allows the measurement function to be exact. In this case, though, the main source of measurement error, which I'll touch on in a second, is also state dependent. And then lastly, we have our proposed model, which is our elevation angle approach. And this stems from elevation angles themselves being used as a possible measurement source for Orion in the case of loss of signal. And we have the measurement function that you can see in equations 4. This is essentially the elevation angle between the two vectors that you can see at the top of the screen. And I will note that it is defined as a linear combination of two separate angles, and this allows the elevation angle to remain continuously differentiable around a point of where the elevation angle is 0. And that's specifically important to us because at time of occultation, the true elevation angle is 0. Yeah, and I guess the other thing is that in this case, the main source of measurement noise remains additive here. So as I kind of alluded to, we have a couple different error sources. I mentioned the camera detection error, which is our main source of measurement error, but we also have time tag uncertainty, and we have some uncertainty in the lunar terrain that affects when we receive these occultations. So for time tag uncertainty, this includes both a jitter and a quantization error term, and those are both encompassed in the delta T term you see there in equation 6. And this comes into play because we process the measurements at the measurement time. So at a given filter time, we backpropagate to the time of the measurement. We process that measurement and map it back to the current filter time step. And I can touch on that a little bit more if I have time at the end. And then we have the detection error of the camera, which is fundamentally a pixel-based error, but we map it into an angle-based error using camera parameters. But this is entirely independent of the state in the case of Model 3. And then lastly, we have a terrain morphology error, which gives us some uncertainty in the lunar terrain. This is currently represented as a time-correlated Gauss-Markov process that you can see in equation 9 there. And the process noise is defined such that the steady state covariance of the bias is equal to the initial state or initial covariance of the bias. So essentially we have constant uncertainty excluding any possible cross correlations, and we add this bias term that's perturbed by the random walk to the average lunar radius to get some variation in the terrain. So these errors are summarized a little bit more in a high-level sense here in this table, along with the measurement function. So we have models 1, 2, and 3 in the different rows, and we can see for the measurement function, both the altitude and angle-based approaches provide an exact measurement function, and then each of the different error sources correspond to a model in which they are particularly I guess most advantageous. So for Model 3, the angle-based approach, that detection error remains additive, and then the other two models have error sources that are particularly advantageous for those cases. So to see what this looks like if we implement it, we'll consider an Earth-Moon 9-2 NRHO scenario. This is chosen for a couple different reasons. The first is it's expected to be used for NASA's Gateway program, and so it's of high interest right now for vehicles like Orion and Gateway and potentially other vehicles as well. And it also naturally provides a wide range of measurement frequencies. So star occultation measurements themselves are highly dependent on the dynamics, and with an NRHO like this, we have a wide range of measurement frequencies. So at Apolloon, we have very infrequent measurements, whereas at Paraloon, we have much more frequent measurements, and so we can see how our filter performs in those different situations. A little bit more about the scenario. We implement an EKF, and we have a star catalog that's based on the Hipparcos star catalog. Specifically, we include stars up to magnitude 6, and this is based on characteristics of the Jenna Optronics star tracker, which is used on board Orion. And this leaves us with roughly 5,000 stars to have potential occultations. We also have a 20-degree circular field of view, which is visualized there on the right. And one thing that's important to note is that we can see that we have two occultations occurring. So we have the green and the orange stars both being occulted by the moon at the same time in this figure. But we're only able to detect the green star being occulted because it's along the dark limb. And so that's reflected in the filter as well. So if we move into the filter performance, for the results I'll show, we'll consider the portion of the trajectory near Paralune, as it's a little bit more interesting. You can see in the bottom right, we have a range of measurement frequencies, where as we get closer to Paralune, which is right around the 4-hour mark, we have much more frequent measurements. And there's also a period of time in there, right around 4 hours, where we get no measurements. And that's because the moon completely obstructs our field of view. And then we have the relevant error sources there defined on the left. So if we take a look at the position errors for each of the different models, so we have models 1, 2, and 3 from left to right, we can see that as we get measurements, our errors snap down. And across the board, they look consistent both in filter performance as well as across the 3 different methods. And then if we take a closer look at Paralune, which is maybe a little bit more interesting, where we have the red dashed line represents our filter covariance, the blue line corresponds to the true covariance. We can see similar behavior across all 3, and we can see that the time-based approach is maybe slightly more conservative. We can also see that this corresponds to a time where there's a period where we're not getting any measurements. And then we see that once we get measurements, just on the other side of 4 hours, we see our covariance snap down as we'd expect. And we can see the consistency of the filter a little bit more if we look at the scale normalized estimation error squared, or the SNEES, which is shown on the right. And for our filter to be consistent, we want our SNEES to be around a value of 1. And we see that for all 3 cases, this is the case. Specifically, if we take a closer look, we see that the time-based approach is maybe slightly more conservative, and this may be due to the linearization of the measurement function or the nonlinearity of the measurement function. But overall, all 3 methods are consistent. We can also see that there's a period of time where the SNEES flatlines, and that corresponds to when we are not receiving any measurements near Paralune. And then if we take a look at the RMSE, and specifically the time average quantities in both position and velocity shown on the right, we can see that for all 3 cases, we have pretty similar performance. And so this sort of indicates the performance that we expected to see, especially with the altitude and angle-based approaches being geometrically equivalent. And so we wanted to sort of see how they would perform in an actual filter implementation. So in this work, we kind of considered a standard case. Future work and ongoing work looks at exploring measures of nonlinearity to sort of distinguish between the 3 different models that we have, as well as measures of non-Gaussianity to distinguish how the measurement error the distribution of the measurement error may change across the 3 different models as it becomes state dependent for models 1 and 2. And then we'll also look at different orbits, including the DRO, 2-body, and some other orbits. For the DRO, for example, we have relatively infrequent measurements. And so, again, these star occultation measurements are pretty dependent on the dynamics themselves. So, yeah, and I guess another key takeaway is that we see for both the distance and angle-based approaches, we have an exact measurement function, and our filter performance is consistent. And so that's what we expected to see. And our angle model, sort of as we sort of sought out, allows the measurement noise to remain closer to the hardware. So, yeah, with that being said, I just want to take a quick moment to thank the NSTGRO Fellowship for funding this work in part, and I'd be happy to take any questions.
last presentation here. I didn't see here a couple of error source like the stellar aberration, because basically you move at 30 kilometers per second, and so this will create something like an error 20 arc second.
Definitely. Yeah.
Second, this is strongly relying into the precision of your moon orbits also,
Yeah.
which is a little bit tricky because it's strongly perturbed. And if you have time, also I would like to see that this can be applied also not only when a star disappears, but also when it appears.
Yes, yeah. And so that's included in the results in here. So it includes both when a star disappears and reappears, but only along the dark limb, depending on the sun's location at the current time. Oh, and then, yeah, sorry. And then for the first point, that's an error source that we've not included in this work, but definitely something that can be included in future work. And then what was could you remind me of the second point?
Propagation accuracy.
Yes, yeah. And so that's another thing that was just an assumption that we made to sort of simplify things, is that we assume perfect, I guess, propagation to the moon and no perturbations from there. So, yeah, just.
Any other questions?
So, Daniele, I think that the aberration is a deterministic effect that can be taken into account, isn't it? So it can be, I mean, it's one of the things that needs to, I would like to understand whether you need to load on board the digital elevation model of the moon, because the shape of the moon is highly irregular. And the offset between the center of figure and the center of mass, which is the origin of the reference frame, which is used for position, is about 2 kilometers. Mm-hmm. So do you need to upload on board for autonomous navigation a digital elevation model of the moon?
So I guess I don't have an exact answer for that. I think our approach was to model the error in that using the Gauss-Markov process. And to sort of allow for some uncertainty in the lunar terrain. I guess we could take a closer look at what the sensitivity of that is to the lunar terrain, and if it would be sort of necessary to upload that on board. Yeah.
Probably it's not complicated, but it would lower the error sources.
Yeah, definitely.
So this was my point.
Yeah.
Any other questions? If not, we thank again the speaker. And this concludes the first session of today, and we'll have now a coffee break until 10:30.
Okay, time to start. All right, our next speaker is Sang-Moon Choi. He's a PhD candidate in aerospace engineering at Iowa State University, working under the supervision of Dr. Osama Abdelkhalak. He is a recipient of the Korean Government Scholarship for study overseas and earns a master's degree in astronomy from Yonsei University and a bachelor degree in mechanical engineering from Busan National University. And his research focuses on space mission design and navigation, as well as the application of machine learning to it.
Thank you very much. Hello everyone. Today I'm going to talk about like another presentation, learning-based prediction of like deep space maneuver position and for rendezvous missions. Yeah, like in the preliminary mission for the interplanetary mission, like we generally use the patch-conic approximation. So like the easiest model is like direct transfer, so like Earth to the target body or like target body to the Earth. And then like we can solve the Lambert's problem, which is 2 impulse, and then may not require like optimal control. It might not be optimal solution, but it is the simplest, and then like maybe smallest time of flight. However, like we can consider maneuver in the ballistic transfer. So in this case, like we need to determine the position and timing for the deep space maneuver. But this can reduce the cost, but generally like it increases the difficulties of problem. And then like we have 3 impulse, so like we may have like more design variables. It has larger design space, but like a moderate time of flight. The other one is like a flyby, so we need to choose the flyby bodies, and then like we also need to model the flyby model, such as the non-power flyby or power flyby. It can be fuel friendly, but like due to the choosing of flyby sequences, it has the largest design space, and also like generally longest time of flight. In this study, like we'd like to focus on deep space maneuver, and then like we using the neural network, we'd like to predict the deep space maneuver position and timing. So to design the deep space maneuver, generally like we can consider like 3 different types. The first one is primary vector theory. We can consider the necessary condition of the optimality. And then like we can reduce the optimal control problem to the optimization problem. And generally like it is the local optimal solution. The next one is like an efficient maneuver placement. It is like based on the primary vector theory, but like instead of like solving it itself, but like we can solve the 2 sequential route finding problem, one for like initial guess and then the other for the actual solution. It can be applied to V infinity leveraging or flybys, and the design variable is like delta V DSM magnitude. The last idea is like a global optimization. So we can add 4 design variables. 3 are associated with the positions, and the other is the timing. And in this case, like since we use the global optimizer, then like we don't need to have the initial guess, and then like possibly it can be a global solution. So in this study, we'd like to use the global optimization, and then given the initial and final states with the time of flight, then we'd like to predict the optimal DSM, position, and timing without solving the optimization problem. Here is the problem formulation. The first one, like this is the easiest one, as I mentioned earlier, the ballistic trajectory. So like if we know the initial position and final position, and then like we can solve the Lambert's problem, then simply we can subtract the planet velocity with the velocity from the Lambert's problem, then like we can easily compute the required delta V. And this is like generally 2-dimensional problem. So like if we know the arrival planet and then the departure and arrival planet's epoch, then like we can get the like stage from the ephemeris. And in the case like mission cost is like the total delta V, which is the delta V ballistic is equal to delta V departure plus delta V arrival. And this is the DSM trajectory problem formulation for the one DSM trajectory. So like for fixed initial and final orbits, that means like a position and velocity with a given time of flight, then we'd like to determine the intermediate DSM position and the timing. So it is like 4D problem, and then like we'd like to vary the delta V vector with the time of flight ratio. This is like epsilon over here related to the time of flight. So as you can see in the first leg, initially we have the velocity as a VPD, which is the same as the planet's velocities. But like once we add the impulse by the delta VD, and then like spacecraft velocity changes, then we also need to determine the time of flight. But here, like epsilon is between 0 to 1, so it's fraction of the entire time of flight. And then once we propagate to the DSM location, then we can solve the Lambert's problem, the remaining arc. So the discrepancy of the velocity at the DSM location is going to be the delta V for the DSM. And then the total mission cost is the delta V, which is the delta V departure plus delta V arrival plus delta V DSM, which is delta VM over here. So for training, like we'd like to generate the initial and final conditions and the transfer between two Keplerian orbits. Here is the range for the initial and final orbits, like a lower and upper bound. Semi-major axis is between 1 to 3, and then eccentricity is between 0 to 0.2. Inclination is also like between 0.0 to like 15 degree, and others are like all possible, any possible range between like 0 to 1 revolution. The time of flight, the minimum time of flight is like selected as the minimum period of either the departure or arrival period, and then like not just like a period itself, but like a quarter of it. And then the maximum time of flight is the half of the larger period. And also like we'd like to use the filter to get the like more valuable results. So delta V, departure or arrival, must be smaller than 10 kilometers per second at each case. This is like a dimensionality reduction, and then like I've explained last time, so I will really briefly explain this. So instead of like having 13 dimension, because like it's rendezvous problem, we need to know the 6 state at initial and then the other 6 at final with the time of flight. So we can normalize the initial distance, and also we can rotate the initial position. Then the new rotated and then normalized initial position is going to be always 1, 0, 0, and then like initial velocity of the like z component of the initial velocity is going to be always 0. So like the total input dimension is going to be 9 dimension instead of like a 13. And this is the training data generation. So we use the particle zone optimization to solve the optimal global optimization problem, and then design variables are like delta VD, which is the velocity magnitude, and BL, those are like all angles associated with the departure velocity vector, and then like epsilon is the time of flight fraction. So the lower bound and the upper bound is given over here, and also we used another data filter. Then like the delta V total must be smaller than the ballistic delta V plus 1. That means like it should be -1. So DSM has to be more efficient than just ballistic trajectory. Otherwise, like this is like not really useful for our mission design consideration. For this reason, like this is the our filter, and the last 4 setups are related to the particle sum optimization. This is the training data generation. So like as I said, like we use the 9 data for 9 dimension for the inputs, and then from the first like initial velocity x, y with the time of flight, and the second row is the final position, and then the last row is the final velocity. Like they do not have like anything like a weird shape, and the right 4 figures are related to the our outputs. So velocity x, y, z components, and then like epsilon, which is the time of fraction. instead of like using the delta V magnitude with the two angles, like we choose the Cartesian coordinate over here. Also, like the just weird thing we can notice is like epsilon can be biased like at the lower bound. I think this is like more like just waiting instead of the departing right away, but still we can reduce the delta V more than 1 kilometer per second here. And this is the neural network setup. We used about like 200,000 data, and then for the test, like we used about like 8,500. And 9 inputs, 4 outputs with the 5 layers with 64 nodes. The total time of training time is like about like 3 hours. This is the training and test result. As you can see, like from the left, this is epsilon v x, vy, vz prediction errors, and then the right one is the test errors. Mostly they are like very similar, and as you can see, the mean error is like about like 1e minus 2 for epsilon, and then 1e minus 3 for the velocities. Even for the test, like they are still like a same order of magnitude, although test has like a slightly higher mean error. And this is like another training and test result. So x-axis is the direct delta V, which is the ballistic delta V, and then y-axis is the predicted deep space maneuver delta V. And you can see the dotted line, dotted red line over here, which is y is equal to x. That means the ballistic and then deep space maneuver prediction is the same cost. And then if the if the points are like under that line, that means like deep space maneuver is like a more efficient than ballistics. So using the neural network, like it is not perfect, but like we can see like a lot of improvement without solving the optimization problem. On the left, this is training. The right side, like using the about like 8,500, we can see that like most of them are like improved, but like some of them has like still greater delta V instead of like improvement. Here is like some example trajectories. First one, this is the solution from the training results. And initial inclination is 0, and then like final orbit inclination is about 20 degrees. Those are like capillary and orbital elements from like semi-major axis, eccentricity, inclination, run, AOP, and true anomaly. So starting from the red circle over there, and then like we like to get to the blue circle at the end. Then the red curve means the ballistic trajectories, and it's hard to figure out. But like one is like the green dot over there is the true deep space maneuver position, and actually the yellow like under the green is the predicted deep space maneuver position. So basically, like once we use the neural network, like we were able to predict the deep space maneuver location and timing fairly accurately in this case. And also the ballistic delta V is about like 13 kilometer per second, as you can see in the title. And true DSM is 9.8, and prediction is like 9.9. So those are like well aligned to each other. And this is like a view from y-axis. Now we can see the yellow circle over here. And we're departing from the blue dot over there and to the red dot. And for the deep space maneuver case, I mean like for the like a big inclination change case, we can see that like after the deep space maneuver, those orbits has changed inclination a lot. So for this reason, we can save the delta V a lot. And this is like another example from the training case. So initial orbit, Kepler and elements is given, and then like final orbits, Kepler and elements are given. And yeah, for the ballistic transfer, it is like delta V is about 16, and then deep space maneuver, the optimal solution is like about 10. But unfortunately, prediction is about 40. But as you can see, like the green one and yellow ones are almost like overlap to each other. But like later, it turns out that they are actually like a 180-degree transfer. So you can see that those points are like literally opposite side of the green dot. That means like when we solve the Lambert's problem for the last leg, and then Lambert's arc was not able to determine the inclination of the transfer plane. So this is the a view from the y-axis. As you can see that the blue dotted line, this is the prediction from the neural network. So solving the Lambert's arc transfer plane is undetermined. For that reason, this high delta V was caused. But this is this can be solved later with the post process. And this one is another test result. So delta V is for the ballistic is about 8.24, and then delta V true is 4.67, and prediction is 4.72. So basically the same. And then in this case, we don't have big inclination change because departure is 0, and then arrival is 5.5 degree. But still, we can see the big improvements. That means although whether we have a big inclination change or not, still DSM can reduce the mission cost a lot. And this is a portrait plot application, Earth to Mars, which is fairly easy. And right-hand side, this is the ballistic, so just two impulses are considered. And in this case, the optimal delta V is 6.04 kilometer per second. This is the deep space maneuver portrait plot. So we can reduce the mission cost from 6.6 to about 5.78, but it took about 4.6 hours to compute the entire stuff, because we need to solve the optimization problem at each solution, each problem. Unfortunately, neural network prediction is pretty bad, but our optimal solution is 5.92, which improved the actually delta V. But we can get this in a few seconds, and I will tell you the reason why we cannot reproduce the DSM portrait plot. So this is one of the example for the optimal solution for the ballistic transfer trajectory. So you can see that delta V ballistic is 6.04, and delta V true DSM is 6.04 as well. And this space maneuver is applied right almost after the departure. That means DSM, the true DSM knows that we need to use the DSM as soon as we can, which means almost identical to the ballistic. But in this case, delta V and delta V true DSM is the same. That means those data might be filtered out based on our consideration. We'd like to predict only for some good solutions whose delta V true is smaller than delta V B plus 1. And this is another optimal solution. So delta V ballistic is 41, and then delta V true is 5.78 kilometer per second, but prediction is a 31.53. As you can see, the Lambert's arc is really bizarre in this case, but if we consider one revolution, it's going to be much better due to the longer time of flight. And you can see that a green dot over there for the optimal DSM, and then it has a one full revolution and getting to the Mars. However, in my assumption, in my training data, we considered that only the maximum time of flight is half of the larger period of the orbit. For this reason, this kind of the data is excluded. So it is more related to our future work. Once we train our model with the smaller time of flight boundary, but later we'd like to add a longer time of flight as well to make those kind of transfer better. And lastly, this one is the optimal solution for the DSM model, DSM prediction. So from the red to the blue, as you can see, the yellow and then green dots, they are almost overlap to each other. that means like they're pretty similar. Although like we were not able to find the optimum, but like we at least were able to find the solution whose delta V is smaller than the ballistic. And this is the like how the prediction goes. So this is from the true DSM optimal solution. We have like very discrepancy between the yellow and green, but I tried to decrease the number of, I decreased the time of flight, and then it will goes there, and then the yellow dot will move to the green dot, and once this is the less than 1 revolution, and keep decrease the time of flight, then we can see that they're getting closer and closer, so the neural network prediction is like getting better and better. For this reason, like we perfectly noticed that our training data was like almost like tightened too much in terms of the time of flight. So we will focus on the like a longer time of flight later. Yeah, in conclusion, the neural network model can accurately predict the deep space maneuver position and timing. With this model, like we can avoid the computationally expensive optimization problem, but due to the limited time of flight for the current model, it was not fully able to duplicate the DSM pork plot. And DSM prediction position is close to the true sometimes, but due to the like close to the transfer angle with the 180 degrees, and then Lambert's problem cannot determine the transfer angle. In this case, like we need to develop like another post process. And future works, we'd like to retrain the model with the larger range, especially the time of flight. And we'd like to apply the proposed method into the actual mission scenarios, such as like multiple rendezvous scenarios or like a multiple asteroid exploration. Lastly, we'd like to extend the work to the intercept cases as well as rendezvous. So we want to use this model for the flyby missions, not just for the rendezvous missions. Yep. Thank you very much for the attention, and I'm happy to take any questions.
We actually have no time for questions, so thank you again. So our next speaker can please come up. Our next presenting is Alejandro Carrasco. He's a first-year master candidate at the Massachusetts Institute of Technology, working with Richard Linares. He did his undergraduate degree in software engineering at Polytechnic University of Madrid, and he is now working on autonomous space robotics and artificial intelligence with a focus on large model-based agents for guidance, navigation, and control.
Good morning, everyone. I'm Alejandro Carrasco from MIT Arastro, Massachusetts Institute of Technology, and I will be presenting my, I think, work of 2.5 years about language models in guidance, navigation, and control, specifically autonomous control of a spacecraft. As you can see in the title, Mayday, Mayday, GPT, you're in control now. So I want to present you how this research come together and some kind of the motivation I had. So at MIT, I was at UPN doing my bachelor's thesis, and we found MIT challenge called KSPDG about autonomous spacecraft operations. And basically, we wanted to find a solution, an AI-based solution, because I'm a software engineer, so I'm not that much related to space. I'm becoming more and more, that could operate well in a scenario that was that didn't have good simulation environments, so we couldn't rely on RL, and we decided language models. And as you can see, we won, not one, we got second twice in this competition in the podium, so it was a decent approach. And basically, these are the problems that we found and that we wanted to solve. So first of all, it was based on Kerbal Space Program. I don't know if you know the game, but it is not an RL scenario, an agent scenario. You don't have good training data at all. You cannot parallelize, so you cannot have like fast simulations. You cannot replay. So basically, RL was completely discarded for this problem, which was validated because other RL approaches that were in the challenge were not successful and quite far from us. And we decided LLMs because they have this tacit intrinsic knowledge that we wanted to explore. And basically, we were working a little bit around with it. And we found out that it knew more than, about space than we thought of. And we could leverage these zero-shot and few-shot models to be able to, with an agentic loop, to operate in these spacecraft operations. So the most important questions, what are the spacecraft operations that an LLM could achieve, or at least that we proved that it could achieve? So the first of all is just a rendezvous scenario. Simple orbit, quasi-circular or circular orbit. We want to, let me introduce you to this terminology. So we are the bandit and the target is the lady. The bandit needs to approach, do a rendezvous to the lady and get as close as it could. And you can see this in here. So basically this is the environment, the scenario that we were working in. And you can see that we are 1.4 kilometers away from the lady. And the second scenario that we worked on and the one we were evaluated on the challenge was the guard evasion or lady bandit guard problem. So we just add another spacecraft, and that's the guard that you can see in there. It's like 600 meters. I cannot read it very well, but basically the guard is actively approaching us. So what does this mean in this problem? That this problem is dynamic and unpredictable, and depending on how the guard behaves, and this is a continuous environment, so we cannot just categorize all the different states that we can encounter with the guard, so we know what it will do. We need to react, some kind of adversarial game, and it's non-cooperative, so it's highly unconstrained and dynamical environment that was pretty useful for us to use LLMs with. And this is the a diagram of how we implemented this. So basically, if you don't know, LLMs, they have system prompt, user prompt, then the response. We can call that all of that context. You can use more things in the context, but I will just use those. And basically, we develop a system prompt defining the problem. Everything that I told you, we tell the LLM. We also tell some things, some recommendations, just because the LLM doesn't have the exploration capacity to be able to solve the problem out of the box. We need to guide it with the system prompt and user prompt. And then we decided, because of latency issues, LLMs are slow, but you can work with them and you can try to structurize to make it faster. So we just used the state observations in the user prompt. And as you can see, instead of just letting ChatGPT say what will happen, everything about its approach, we wanted to make it a little bit like a Markovian action structure, where we want to define in a function calling, just let the agent for every state give an action and just that, and we used it this JSON structure. This was not the only architecture we used. As you know, language models can also be vision language models, and we put it some glasses, and we also gave it screenshots of the video game, of the environment, with similar results. It has some limitations, but I won't deepen in it anymore. But we also try to use reasoning models. These models were out 1.5 years ago, something like that. And we wanted to see if the models with reasoning would improve, and effectively it did. So I will show you the results. I will just show you some trajectories. We can see that we fine-tune and we use a few short trajectories. And as you can see in the fine-tune model, there is a huge deviation between Llama and ChatGPT, which we used. And it was basically prompting. I don't know how familiar you are with fine-tuning, but in these kind of models, maybe you lose flexibility, maybe you lose the adaptability of the LLM. But we could see that that deviation was actually an error we had in the prompt. And it means that the prompting, the context, still influences the actions of the model, even after fine-tuning. And we could get as close as 70 meters in this approach. These are old results. We're working on a new paper, but we don't have the results yet, or at least not for presentation. And I think for a problem like this, you can just like watch a video and the results, like it will speak for itself. So we can see that we start at 2.7 kilometer. Right now we are evading. I don't know if you can see the guard around there, but basically we want to like approach the lady laterally to avoid the guard, and then the LLM just will do the latest proximity operations. And given the recent advancements, in contrast with previous years, we were able to capture the lady and just get the maximum score, which is actually just like a collision with the lady. So we could see that it was quite precise, and only with textual hints and recommendations, the model was able to design a solution that could avoid the guard while impacting the lady, literally. And I was talking about the results. We are doing some new research that is in progress, and we want to right now leverage. I was mentioning that LLMs were not able to explore. RL does, but quite lately LLMs are also trained with RL, and we don't want to fine-tune it or do that kind of exploration, but we want the model to explore it and to be able to develop a solution by itself. So that's where evolutionary algorithms come in place. And as you can see, there are two different approaches that we are trying to solve. Both of them try to work with the context, and both of them are what literature says as in-context learning. And basically, in the first part, we have a playbook, and the model will just reflect on previous missions, see how well it went, all the results that you saw and more that I couldn't present here are presented to the model, and then it's able to create and give itself some insights to be able to improve itself. And then the second one is a Monte Carlo tree search based framework that the LLM will be able to, using different self-prompting, will be able to get a good solution, and just this exploration versus exploitation thing that we can see in these kind of models. We try to make all our code and all our experiment data public. So Right now, there is this GitHub repo. This is for the last participation. Soon enough, there will be the next one because there is a participation in progress. And also the data is everything in there just for it to be public and used. And we have published some papers with the vision language models, the large language models, and like our first preprint called Language Models Are Specs of Operators. And finally, I want to talk about StarCloud, a company that has deployed its the first graphics card in space. And actually, last week, or maybe 2 days ago, an LLM was trained in space. So I don't know if you know NanoGPT, but a language models made by the community was trained using an NVIDIA H100, which is a GPU that is currently used in space. And that's all for me. We also published a journal paper. All the different papers that you saw are inside the journal. And thank you for listening to me, and I'm open to any question.
Any question? Did you try also having the guard be taking actions from a different LLM? Because it looked from that video that the guard was either deterministic or pre-planned actions, even though you might not know it. And so, or was the guard playing any game theory? Because it's a lot easier to evade somebody that is not reacting to you than it is to evade somebody that is reacting to your evasion.
Yeah, that's a good question. Actually, I think for research, if we want to improve the LLM, it will be interesting to have the guard as an LLM because it will make it like an adversary condition. It is currently adversary. We just don't develop the guard behavior. It is done by the challenge, but the guard is not deterministic. I don't actually know what it uses. I know it used MPC, maybe some kind of RL, but we don't really know because it is obfuscated because of the challenge. But the guard is actually intelligent, and there is, depending on the scenario, there is one scenario that it orbits around the lady and just approaches you when you're close to the lady. And if you are far, it will go back to the lady. So that's quite an intelligent guard and difficult to bait and work against.
Very interesting. Any other question?
No, just a quick question, because I didn't see in your model, did you model the real trajectory? I mean, the environmental dynamics and so on. This is the question. Did you?
So the main question?
The trajectory dynamics, attitude dynamics, did you model in your system? I mean, is modeled?
Well, the thing about that, if I get your question right now, the orbital dynamics are closed source and constrained with the environment, the scenario. That is a problem because we wanted to predict the next states and just for us to know where the guard will be, but it is not similar to the Earth. So we don't implement them. They are quite good orbital mechanics. This whole game was collaboratively developed with NASA, but we don't have them. The LLM is more kind of a pilot than a trajectory designer because it decides the action for every state. So there is not a whole memory from start to finish with trajectory.
Okay, thank you.
Let's thank our speaker one more time. Our next presenter, please. Okay, as he sets up, I'm going to introduce him. Ashan Paranjape is a PhD candidate in aerospace engineering here at Texas A&M University. His research broadly involves state estimation and space situational awareness. He is also performing research in sensor fusion, sensor technology, and signal processing. Asian earned his undergrad degree in aerospace engineering from the Better University of Texas at Austin, and he's currently working with Suman Chakravarti.
Howdy, everyone. Thank you. First of all, I want thanks everyone for being here, and special congratulations to Professor Mortari on a successful long career within this department. I wish you many, many great years ahead for you. Okay, so today my talk will be about probabilistic methods for initial orbit determination and target tracking or orbit determination, particularly in cislunar space. So, brief outline. First, we're going to talk about this. Oh, sorry. Can you hear me? Okay, perfect. So first, we're going to talk about our initial orbit determination and orbit determination framework, which we call the kinematic fitting particle Gaussian mixture, or KFPGM framework. Then we're going to show how this framework works on a bit of a chaotic trajectory within this within a nonlinear dynamics model, and then we're going to talk a little bit about variations of this target tracking framework and some comparisons between different filters that you see throughout the literature. All right, so let's go ahead and talk about our filtering framework. So dynamics in cislunar space, well, I'm going to skip most of this. We're using the CR3BP model, which most of you, I'm assuming, are familiar with. But for the measurement model, we're going to be using azimuth and elevation, so angles-only measurements. However, to get an idea of position and velocity, you would need to know a little bit of range information, which is pretty hard to get in cislunar space. But we try to do one of two things. One is we do assume we can get a range measurement, but we compensate for the unreliability by inducing a pretty high measurement noise, something to the effect of 5 to 10% of the true range. The other thing we can do is what I call the minimal range assumption, is to just assume that the target is somewhere, anywhere in cislunar space. And we model that with a very large uniform PDF that spans roughly from 2 times the GEO distance to about 550,000 kilometers, which is what the Aerospace corporations define as the upper limit of cislunar space. And very quickly, I should note that what we define as a pass refers to a single streak of these measurements right here, a single streak of continuous measurements, and that's just another way of saying how long the target is within our sensor field of view, and this varies between 10 to 20 hours depending on the trajectory. All right, so let's talk about our kinematic fitting IOD framework. So our framework is rooted in the fact that you cannot use a minimal assumption method such as Gauss's method because the dynamics in CR3BP are just not conducive to similar assumptions. However, we can leverage the fact that our target will be in our field of view for a long enough time that we can make several measurements. The idea is that if we're able to fuse some range information along with some azimuth and elevation angle measurements that we already have, we can kinematically fit polynomials for the 3 position coordinates x, y, z in the coordinate reference frame of the observer. Now, if we take now that we have x, y, and z, if we take a simple time derivative of these, since we've already fitted it with respect to time, then we have vx, vy, vz. So that together makes up the 6 coordinates that make up a full state estimate. So here's a little. So this is just a brief illustration of how our framework works. Again, we're fitting these red, green, and cyan polynomials through the blue circles. And then we're taking the time derivative of each of these to get velocity estimates. Now you'll notice that that these star points represent a single state estimate, which is not supposed to be accurate. However, when you repeat this for multiple different measurement sets and different ways of getting range information, then you'll obtain a particle cloud, which you can abstract into a PDF, in which you can estimate the state of your target. And so I mentioned a couple slides ago that there's two different ways of doing this. One is by assuming you can take the range measurements for the IOD, and that's what yields the particle cloud on the left. And the second is when you use the minimal range assumption, and that leads a much larger particle cloud, the one you see on the right. So this is your initial state estimate. From here, it's very large, but if you have a good filtering framework or OD framework, then you can bring down the size of this particle cloud over time. So the way that we use or do orbit determination is we use what's called the particle Gaussian mixture filter. And we combine this with the kinematic framework that yielded our initial state estimate. So PGM, for short, consists of 4 key steps. First, we propagate the ensemble that we saw on the previous slides. Then then when we have an observation, we cluster this into different. We cluster this such that we get an a priori estimate that's a GMM, a Gaussian mixture model, and then we use an ensemble update on each of those clusters to get your posterior PDF. And I'll show you. And I'll show you in the next few slides an example of how it works. So I want to talk a little bit about chaotic trajectory. So the trajectory I choose here is one that passes by the L2 Lagrange point at a very small velocity. And the reason I choose this is because if you do a little simulation where you take a bunch of particles that are scattered with very low standard deviation near the L2 Lagrange point, and you pass them through it, you're going to see a very warped particle-based PDF after a while. So what we do here is for at least the first 2 passes, for the first roughly 36 to 48 hours, we're taking measurements every 40 minutes. For the first 36 hours, and then we induce something like a 10-day sensor shutoff to give enough time for our state estimate to warp into a position where you can no longer really estimate it as a Gaussian. And then after that, we try to take measurements roughly every 8 hours, since that's you most likely will have that type of sensor scheduling scenario in real life. So this is what our initial state estimate starts off as. We're using the minimal range assumption just to generalize it the most. Now, when we propagate so next we propagate these particles, but do note the little hole you see in these plots right here. We're filtering out any particles that are below or above our defined cislunar space bounds. Because we're assuming the target will remain in cislunar space at all times. And then we use the Kalman update on each of these clusters. And many will die out, a couple will remain. But we still need to keep iterating with the PGM filter to bring down the size of our estimate. So at the end of that first pass, after we've had maybe 6, 7 measurements more, we're able to really reduce the size of our estimate down. And we do the same thing for a little bit longer, just to get it down a little bit more. And then after this point, Now we're going to induce that long sensor shutoff for about 10 days. And what tends to happen is you see a lot of warping. So something that looked nice and straight like a pencil now kind of looks like a seahorse or a whale, or however you like to view it. And this cannot be modeled with Gaussians. It has to be modeled with the GMM. However, when you use the PGM update step here, what you'll see is that most of these clusters do indeed disappear away, and the clusters that we want to keep, which is the blue and the cyan ones, retain. And from here, we can keep using PGM to bring down the size of that state estimate. So next, I want to talk a little bit about the variations of this framework. So I mentioned that there's two ways you can get range information, and that will give you an initial state estimate. So the first two, to recall, the first two were one, you can assume you can get range measurements, but you compensate for it by inducing high measurement noise. The second one is just that big uniform PDF, the minimal range assumption. The third thing we do is we take the minimal range assumption, but we also add a velocity constraint of 42 kilometers per second. And the reason we can justify it is because we can reasonably assume our target is not actively trying to escape the solar system while in cislunar space. So we have a little velocity bound there, and we can filter out a bunch of particles in our initial state estimate and get a slightly smaller PDF to begin with. So just to recall, this is what the initial state estimate looked like when we just did what I call range bounding, but it's just the minimal range assumption. Now, when we filter out a bunch of these particles by velocity, we actually lose something like 85% of them. So that's why you saw a very dense, very big particle cloud with a lot of particles then, because 85% of them are going to go away at this step. However, there are smarter ways to get down to this region to filter out particles by velocity when you have more information that we are looking into. But for now, we're going to assume that we can use this PDF and use our PGM filter on it. So for this case, we decided to look at the popular 9-2 resonant near rectilinear halo orbit, which many of you will know is a big orbit of interest for NASA's Gateway and Artemis missions. Stable orbit with a period of about 6.25 days. And we're going to try tracking with our PGM as well as other filters over that orbit. So we use a metric. So we use the entropy metric here, which you can define as the negative expectation of the log of P of x, which is the PDF representing the particle cloud at each step, which is a GMM. And because there's no closed form solution to H for GMM, we use a Monte Carlo approximation for this, using a large number of particles. In between passes, we have to approximate P of x with some clusterings or GMMs just to get a better estimate for P of x, since you can't exactly estimate P of x precisely with a bunch of particles. Well, you'll get more precise, but you won't always get to the right answer. So what tends to happen is so we have the range. So we have the three assumptions, one plot each for each of the assumption sets, and within it we compare the UKF, the ENKF, and the PGM. What we see is that for the range measurements, when we start off with the range measurements IOD estimate, we're able to all three filters do work. However, even though PGM works PGM is able to bring the entropy down slightly more than the other two. It's kind of a wash. It kind of ends up being a wash. So the choice of filter is really up to what you prioritize, the amount of time you want to run the filter, or the exact precision that you want. However, when you start off with the different assumption sets, so minimal range assumption, which is the plot in the middle, you'll notice that only the PGM is consistent the whole time. What actually happens is the UKF breaks down within the first pass itself, just because you have a very large PDF, and the 13-odd sigma points that you have in a UKF do not are not representative of such a large PDF. With an ENKF, it can only bring an estimate down so much. So when the starting estimate is so large. So as a result, what tends to happen is it becomes very big and unwieldy in the state and measurement space that it'll eventually slowly become inconsistent. And for the last one with the range and velocity bounding, even though the ENKF does become a little bit, will give you a consistent estimate, you're not exactly going to gain much information from getting more observations. Only the PGM will really help you out. So you'll have to be a little bit careful here what filter you want to use when given your initial information. So. All right, and with that, some future work. So we're kind of doing one of 2/3 things. So one is the development of information techniques to reduce the size of the IOD estimates. Like I mentioned, you lose something like 85% of the particles when you filter by the velocity. We don't want to lose that much, so we can use a technique such as subset simulation, or we can fuse other information about our CR3BP orbit, such as energy level, or just an idea of where in the sky we might be, or what type of orbit we might be to hone in on the ranges. The other is we want to use some multi-sensor fusion techniques, and the deal with that is if you have two estimates which have a nice small overlap between them, two estimates with a nice small overlap between them, you can basically get the intersection of them, which is going to be a lot smaller than either of those two estimates, and then that gives you a much better state estimate moving forward. And finally, the other thing we also want to explore is more refined dynamics models, such as the elliptic restricted 3-body, the generalized R3BP, as well as the BCR4BP, especially when effects of the sun are important. And with that, we would like to thank the U.S. Space Force Chief Technology and Innovation Office for funding this research, and specifically to Dr. Jill Brewer and to Dr. Islam Hussein of Trusted Space for their collaborative efforts. And with that, thank you so much for coming. I open the floor to questions.
Any question?
Hi. Can you speak about the clustering algorithm that you're using and how sensitive the PGM in this scenario is? And have you considered comparing with the ENGMF?
That is actually a very good question. Thank you for asking that. So for the clustering step, generally we've used the k-means algorithm to get clusters, especially the a priori estimate. And to answer your second part, yes, I have looked at the ENGMF. I've been thinking, it's been on my mind to try to compare this filter with, I think, your filter. We just haven't gotten to it yet. Okay.
You can have better clustering algorithms. You can have fancier things. So what I'm saying was the PGM was the first one, and then Renato and your group that picked up on it. So they're really the same filter, right? And you possibly have other, variations on it, which I know you guys have done. But there'll be very similar performance. right? The key point here is that what it allows you to do is it shrinks your uncertainty down because you've got these clusters, right? And you don't have the particle depletion problem because you're doing the the ensemble update with the Kalman filter.
Resampling.
So yeah, I mean that's basically what I just wanted to clarify that. Okay.
There's one over there.
When we think about the performance of the orbit determination, what are the state error and the 1 sigma uncertainty about your result?
Oh, actually, that's a good that's actually a pretty good question. So with the so do you want it for the PGM only, just to follow up? Yeah. So actually, I do have a little extra slide about it. Just wait a second. So which one? Okay, so this is for the leftmost plot that you saw on the slide where I was comparing filter entropies and the PGM specifically. So this is what so at the end of each pass, this is what the state estimation errors, just the 1 sigmas look like. So they start off pretty high with something like 50 to 60,000 in the position space, and in the velocity space, something to the order of like 17 to 20 kilometers per second. But you can see at the end of it, we're able to bring it down quite a bit. So in the velocity space, we're even in the meters per second, but in the position space, we've boxed it into a couple of kilometers, maybe even the size, maybe even a fraction of the size of the Bryan College Station area, to give you perspective. Does that answer your question? The state error, we haven't done that. We don't have it. But oh, thank you. All right. Any other questions? Okay.
So you said you have range measurements, right?
Mm-hmm.
Is there a scenario in which this might be a decent assumption? Or do you see how you could use your second assumption that you know some a priori bounds on your range? Can you somehow make those bounds more informative rather than just being somewhere in that cislunar space?
Yeah, we could. For example, I did mention in my example we're working with the 9.2 NRHO orbit. So what you could do there is just propagate something in the 9.2 NRHO and just see what those ranges are from your observer, and then just create a uniform PDF with those ranges. And what you'll get is a much, much smaller particle cloud than with either of those 3 assumptions we discussed. Those assumptions are meant to be very general. The idea is you possibly know a lot more about your orbit than what we think you know. And so you're always welcome to peruse it. It's just it also makes the state estimation process a lot easier as well.
Thank you. We are going to thank our speaker one more time. Okay, while we set up, I'm going to introduce our next speaker, Dr. Lorenzo Federici is a postdoctoral research associate at the Department of Aerospace, of System and Industrial Engineering at the University of Arizona. He received his bachelor's, master's, and PhD degree in aerospace engineering from La Sapienza University in Rome, and from fall 2022 to fall 2025, he was a postdoctoral scholar at the Space Systems Engineering Laboratory at the University of Arizona. So his talk is called a Pulse Width Modulation Thruster Control for Autonomous Docking via Reinforcement Learning.
Thank you for the introduction. Hello, everyone. So, yeah, today I'm presenting research work that I did at the University of Arizona together with Professor Curti about the use of reinforcement learning for the autonomous guidance and control of a spacecraft during the rendezvous and docking with another spacecraft using pulse width modulator thruster control logic that I'm going to explain right now. So, autonomous orbital rendezvous and docking is critical technology for making possible a wide range of future space missions, for example, active debris removal or on-orbit servicing, in-orbit assembly, and so on. And typically during these missions, and especially during the terminal approach and docking phase, the Chaser spacecraft relies on a multiple thruster reaction control system as the only actuation system on board. And this kind of control systems are made up of different thrusters, typically 12 through 16 thrusters, that are organized in 3 to 4 thruster clusters, strategically placed around the spacecraft body, and that control both the translational motion and the attitudinal motion of the spacecraft. The problem with this system is that the thrusters are typically on-off thrusters, so they can either fire at their maximum thrust or they're completely off, and that they naturally couple the translational and attitude dynamics of the system, because in order to thrust in a specific direction, you need first to change the spacecraft attitude in order to move the different thrusters in the right way. And generally, traditional guidance and control strategies that are used during these mission phases neglect at first glance this kind of problematic, and instead they determine continuous control laws for the thrusters that either command directly the net thrust and torque that is generated by the entire reaction control system, and then that typically are supposed independent. That is, of course, a simplifying hypothesis. Or they command the thrust level of the individual thrusters that are, though, considered throttable, so that they can produce any thrust between 0 and their maximum value. And modern data-driven guidance and control approaches in the literature follow pretty much the same control logic, mainly in this case because they want to avoid the use of discrete action spaces. And this is mostly related to the fact that traditional neural network training pipeline typically work far better with continuous output instead of discrete outputs. The problem with these formulations is that they must rely on an additional control logic to be implemented on board in order to translate the continuous commands into actually executable on-off thruster commands. And this is typically realized with a combination of thruster allocation algorithms and pulse width modulation algorithms that, I mean, for sure lead to an increased onboard computational burden because you need to solve on board an additional optimization problem in order to allocate the cumulative thrust and torque into the single thrust generated by the different thrusters. And also they lead typically to approximation errors or generally suboptimal performance. And the goal of this study was to investigate a reinforcement learning driven guidance and control approach to directly command pulse width modulated thruster firing schedules for the different thrusters. That means that at each control step, we want to directly command the initial firing time and the pulse width for the different pulses realized by the thrusters. So we're considering the thrusters as separate and as on-off kind of thrusters. And we compare this strategy with more traditional strategies used in the literature, specifically directly commanding the net thrust and torque generated by the entire reaction control system considered independent, or commanding the individual thrust level of the different thrusters considered throttable. These two control logic that we implemented are kind of ideal control logic, because then we didn't implement the second control logic, that is translating these continuous thrust commands into on-off commands for the single thrusters. And so we use them as a baseline to understand if our methods could reach the same performance as these strategies. And then we consider a third strategy where the continuous thrust commands for the different thrusters were actually converted into realizable on-off commands using a classic pulse width modulation logic. So the case study that we considered was the terminal approach of the Crew Dragon to the ISS right before the final docking. And we chose this problem because it's a very well-known trajectory, so we know what performance to expect for the system in terms of accuracy and propellant consumption. And the Crew Dragon uses actually a reaction control system with 16 on-off thrusters, able to generate 400 newtons of thrust each. And they're organizing 4x4 clusters around the spacecraft body. As nominal initial state, we consider the actual, the second and last waypoint that is realized during the actual approach mission of the Crew Dragon to the ISS. That is a waypoint that is located 25 meters away from the final docking position. And we also consider the Crew Dragon as 0 relative velocity, the correct docking attitude, and 0 angular relative velocity in the nominal state. But then we added some uncertainties on this nominal initial state in order to consider more, a more realistic scenario where we can have deviations from the nominal trajectory. So we added Gaussian errors on the initial chaser state in the order of with standard deviations in the order of 1 meter for position and 10 centimeters per second on velocity, 1 degree on attitude, and 1.0 degrees per second on the angular velocity. We also added some Gaussian noise to the state estimate provided by the navigation system that we suppose is running on board, and that is used as the input to our guidance and control policy. And then we consider different orbital altitudes for the ISS within the range the ISS actually flies at. The goal is to find the fuel optimal state feedback control law that brings the chaser as close as possible to the docking position and with the right attitude with 0 relative velocity, both linear velocity and angular velocity, and that keeps the chaser within a conical visibility zone centered in the ISS. It is the one depicted in this picture. So we're sure that the chaser spacecraft is always visible from the ISS during the maneuver. As for the dynamic model, we describe the model within a radial transverse normal resonance frame centered in the target spacecraft, so in the ISS. And the chaser translational state is described by the relative position, velocity, and its mass, and the dynamics is governed by the Hill-Closky-Wisher equations for relative motion. In this case, the control for the translational motion is the total thrust generated by the RC system and the total magnitude of the thrust generated by the different thrusters. And also we implemented the conical constraint and as a linear constraint on the translational state of the spacecraft. It is this kind of constraint that you can see here. As for the attitude motion, we described it in the body fixed reference frame. And we, for simplicity, we suppose the spacecraft to be a homogeneous cube with a side equal to L and with a symmetric inertia tensor. The rotational state is described either by the quaternions and angular velocity or the Euler angles and angular velocity. And the dynamics is described simply by the Euler attitude equations. And here the control instead is the total torque generated in the body reference frame. The translational and attitude equation of motion can be combined into a single equation, and the control law that we try to find with our reinforcement learning based method is the torque, torque and thrust norm in the body frame. So in order to tackle this guidance and control problem with reinforcement learning, we had to first model it as a Markov decision process. So the total simulation time that was 100 seconds was discretized into a number of time steps or control steps, 100 actually. So each control step for us was exactly 1 second. And at each control step, the sensors plus navigation system on board is supposed to provide an observation to the guidance and control system based on the current chaser state. And this observation is made up of, as I said, is basically the current spacecraft state, the real spacecraft state, plus a Gaussian noise and the current time. This observation is used as an input from the guidance and control system that we call agent in reinforcement learning terminology. This is a deep neural network that takes this observation as input and returns as output an action. This action is translated into the actual control that I mentioned before, so the thrust, torque, and thrust norm, based on the control logic that we are using. And I'm going to describe the different control logics in a bit. And this control goes into the dynamics of the system in order to generate a new spacecraft state and generate a reward signal that is what guides the optimization process in this case, and is what contains both the objective function and constraints of the problem. So in our case, the reward contains a frequent terms, that is basically the propellant mass consumption plus the violation of the conical visibility constraint, and a terminal constraint that is given to the agent just at the end of each simulation that instead contains the final error at the docking position. So the position error, velocity error, and attitude and angular velocity errors. Those are the different control logics that we compared. So the first one is when we directly command the net thrust and torque generated by the control system. And in this case, the action returned by the neural network is an action with 6 components. And the first 3 components are used to define the thrust. The last 3 components are used to define the torque. And the thrust norm is simply the norm of the thrust generated. The second approach is considering separate thrusters but throttleable. So the action return is actually a 16-component action where each of these actions define the thrust level generated by each of the 16 thrusters, as you see. That can be continuous between 0 and the maximum value, and it is supposed to be constant during the 1-second control step. This logic is then converted into an on-off logic that is actually realizable on board using a classic pulse width modulation strategy that is the so-called equal area strategy. So basically, if the deep neural network determines that this is the optimal thrust level for these thrusters, then this is converted into an actual pulse with maximum thrust by keeping the area the same. And so we can determine what is the actual final time of firing for this thruster. And this thrust is supposed to be placed at the beginning of the guidance step. This is a convention that we used. And this is the final control logic that we actually implemented, where the action space contains 32 actions, because each pair of actions determine the initial firing time and the total duration of firing for each of the 16 thrusters. We train this neural network with reinforcement learning, so the goal is to try to find the network parameters that maximize the cumulative reward obtained during the simulations that we did. We use proximal policy optimization as the training strategy. So what we do is you alternate between policy rollout and policy update. During policy rollout, you basically deploy your most up-to-date control strategy in the simulation environment to collect as much data as possible. These data are then used to update the network parameters in order to maximize the reward using stochastic gradient ascent on the parameters. Those are the results obtained during the network training. And these plots show some metrics, how they vary during the network training for the different policies that we're comparing. Here we have the final distance from the docking position, the final velocity, propellant mass, attitude error, and angular velocity error. We can see that the green policy, that is the baseline one, when we determine the actual cumulative thrust and torque, is of course, is the most accurate one because it's an ideal scenario. And this is what we want to try to aim for. But our policy, that is the red one, actually shows better performance than the other policy that we use to compare our methodology with. That is the blue one, and it's the one where we actually control the different thrust level for the thruster. So we're actually able to obtain better docking accuracy at the end in almost all metrics, and actually a better mass than both of the other policies. And we can see it better in the next slide. Those are the trajectories obtained. So to understand the deployment performance, we realized a Monte Carlo simulation with 1,000 trajectories. And here you can see the nominal trajectory in black that is pretty much similar between the different policies, but you can see that the dispersion of the Monte Carlo trajectory is a bit different, and specifically our policy is more similar to the baseline policy because, the dispersion is bigger in the central part of the trajectory and tend to shrink, of course, when getting to the final docking position because of the constraints that we enforced. And this larger dispersion is actually a symptom of more adaptability because the policy is able to differentiate better the control between the different trajectories given the actual uncertainty realization that we have in the different scenarios. And those are the performance in terms of distribution between the Monte Carlo trajectories of the different constraint violation and the propellant mass. Same as before, here you can see the error on the final docking position, on the final velocity, the propellant consumption, the attitude error, and the angular velocity error. And you can see that, of course, the baseline policy is the best one in all metrics, but our policy, that is the red one, it's actually as similar performance as the other ideal policy we compare it to, where we suppose that the different thrusters are actually throttleable. And it has always better performance than the other actually realizable policy where we use the equal area pulse width modulation strategy, that is the black one, and especially has way better performance in terms of terminal velocity, where we reach accuracy in the order of a few centimeters per second in velocity, a few centimeters in position, and less than 1 degree in the final altitude. Also, the propellant mass is actually the lowest because of the on-off strategy that we actually use. So we're able to consume a lower propellant consumption, and here, this is just to give you an idea of the different thrust lows for the 16 thrusters, where this is our policy, and this is the classic pulse width modulation policy we compare it with. And you can see that in our case, we have a much coarse control because this is optimized to control the spacecraft just when it is needed in order to reach the desired accuracy and consume as less propellant as possible. And this is the actual trajectory that we obtained using our control strategy in order to approach the ISS. This was sped up by 10 times, I think, in order to, for illustration purposes. So by concluding, we presented our reinforcement learning-driven guidance and control approach in order to control a reaction control system with on-off thrusters. And we compared it with traditional strategies, and the results show that we obtain a similar accuracy to the ideal approach where we consider the different thrusters as throttleable instead of on-off thrusters, but we also are able to obtain a lower propellant consumption and better docking accuracy in terms of velocity. And we always obtain better accuracy in propellant consumption compared to the other classical pulse width modulation strategy. Future work, we want to consider a more realistic model of the spacecraft with also variation, for example, in the center of mass and inertia. And we want to try also to learn just the actual thruster allocation and pulse width modulation logic, starting from control law obtained with a more traditional strategy. Thank you.
Unfortunately, we do not have time for questions. Thank you again. Okay, our next speaker is gonna take us to the end of the session. Dr. Lorenzo no, wrong person. Here we are. Alberto Zamorano is a PhD candidate in aerospace engineering at Texas A&M University. He's currently working under Dr. Carl DeMars in the Prometheus lab. His work consists on the design and simulation of algorithms for autonomous threat detection and classification and active sensing for navigation and control in the cislunar regime. He received his Master of Engineering from Texas A&M and his Bachelor of Science in Mechanical Engineering from the Costa Rica Institute of Technology.
Thank you for the introduction. Well, hello everyone. I hope we can make it on time for lunch, but we're going to talk about error bounds guarantees for the reproducing kernel Hilbert space EKF, or the REKF, what we reduced the name to. First, we're going to talk about why we chose the REKF. So I'm trying to convince you here first. So most of the traditional filters rely on known system models and observations. Some of these are not excluded, but are not limited. So the extended Kalman filter, Kalman filters, and their variations, and the particle filters, for example. We also have made some study on adaptive EKFs that are showing improved robustness to modeling errors, but are sensitive to innovation outliers. With this comes the question, what happens if models are incomplete or measurements are degraded or spoofed? One example of this is in lunar space operations, where we have limited or inexistent GNSS coverage. Why does it matter? Well, it's mission critical risk that leads to navigation or tracking failure, and also loss of spacecraft or costly maneuvers, or even worse if the human being is involved in the equation. Some other associated risks are not limited to jamming, spoofing, degraded sensing, or limited infrastructure and high uncertainty. So this makes the REKF a very good option because it works on certain knowledge of systems and observation models, although we know about, or we have some interest in the state dimensions, for example, that we assume some topologies on the other filters parameters. So why do we want to do or perform analysis of the error bounds for the REKF? Well, first of all, no prior work has been done in stochastic stability of the REKF. Also, it provides with some conservative bounds or guarantees of the estimation error, and a relationship between these error stability and the filter's initial conditions and the nonlinearities of the dynamics of our observations. How did we do this? Well, we use stochastic boundedness of the error, which involves, but it's not limited to, concepts such as exponential boundedness and probability 1 boundedness of the error. And we also use Lyapunov techniques in stability of the error dynamics. So just to get started with the REKF preliminaries, we have its formulation where we have a system model, very similar to what we all see of the EKF, with a general additive noise on the system and the observations and some nonlinear functions. It consists of a prediction and an update steps, and where the parameters we are actually interested in consist of A and B, which are the system matrices and the observation matrices, and PW, W, and PVV, which are our noise covariance matrices for each of these as well. And state and observations functions are shown here, and they consist of functions that have to be rebuilt using kernel function approximation and an expectation maximization algorithm in real time. We also take some general assumptions here before we start our analysis. First is we assume our state and observation functions are continuously differentiable, which means that we can find their Jacobians at every time step in our flight or simulations. There also exist some raw values that are positive and also real, such that the following bounds on the Jacobians and the covariance, noise covariance matrices are true for every time step as well. We also assume there's some also positive real constants such that when we take the Taylor series expansions of the dynamics or the system model of the REKF, its phi function or nonlinear terms are bounded via the following inequality on these constants. And similarly for the observation function using the Taylor series expansions. To start with the error study, we use the error dynamics of the REKF formulation, where we have that E plus and E minus are the a posteriori and a priori error of the filter, and it's compounded by the difference between the true trajectory and the state estimate. When we substitute the a priori and the posteriori estimates in these errors, and we combine them using the Taylor series expansions of F and H, we obtain this expression of the error in terms of noise, nonlinear terms, and also its previous value. So we also need to talk about two very important definitions here. The first one is exponentially boundedness of the error, where we assume it is a stochastic process, and in the mean square sense, it is exponentially bounded if there exists constants ρ1, ρ2, and ρ3, such that we can meet with this inequality of the expectation of the squared error. The second definition is that our error will be bounded with probability 1 if its supremum is less than infinity. So we use these two definitions to build a result or a proposition that says we assume now that we have a Lyapunov function that is also a stochastic process V is a function of the error and the covariance of the matrix of the state. And we assume that there are some constants as well that are positive and given like the bounds here, such that we can meet with these two groups of inequalities. So then we can conclude that only if the third inequality here that is very similar to the one presented before, then we can conclude that this error is not only exponentially bounded, but also with probability 1. And this is a very good result that we're going to use later. So now we can go into the introduction of the boundedness over estimation error. And here we take a couple more assumptions. The first one is on the system Jacobian, that we say that is non-singular at every time step. And the second one is that there exist some bounds that are real and positive on the state covariance matrix, such that we can bound it from the left and the right-hand side. And so if for some constants, epsilon and delta, where we can say the initial error is bounded by delta, then we can also say or assume that there's a squared bound on epsilon for the noise covariance matrices. Then the result, after all, a lot of work in math carpentry, is that we can conclude that for this filter, the error is exponentially bounded and also with probability 1, which is good and gives us a guarantee, as we're going to show later in this presentation, that the error keeps its stability as well as it keeps bounded and the covariance matrix is stable. So for simulation error, we have a setup consisting of two filters that are cascaded. The first filter, what we call the alpha filter, is just an EKF in this case. The second one is the REKF, what we call the omega filter. So the alpha filter uses the nonlinear observations or nonlinear range observations of the Cloesi-Wiltshire equations, which are linear, and generates a state estimate mx that is here. While the omega filter uses this state estimate from the alpha filter to learn the alpha filter's parameters that he doesn't know about via an online algorithm and the kernel function approximation by rebuilding these functions. It also produces a state estimate ms that is an estimate of the alpha filter. And we'll show that, for example, this estimate is actually more precise. So in our simulation, we also use Monte Carlo analysis to characterize the filters' performance with ensemble average error and standard deviations that are compared against the Monte Carlo intervals, as well as the time average mean squared error that is used to assess the estimation accuracy. So in our simulation, again, we use the Cloesi-Wiltshire equations in the xy plane, which simulates the motion of a chaser in close proximity of a target that is in a circular orbit around Earth. And these dynamics are used to generate only the alpha filter's noisy observations that will be used to produce mx, or a solution of the chaser. So the initial conditions that we use for the alpha filter consist of initial mean and a covariance, and then we have a constant noise covariances for the process noise and the measurements, where again we have a scalar because we're using nonlinear range measurements for the measurement covariance. So now what's interesting here, for the omega filter, we use very similar initial mean and covariance, but now we have scaled values of the alpha filter's process noise and measurement covariances, but this reflects the need of the filter to initially explore a wider range of dynamic behaviors in the sense of the process noise or the dynamics, while for the measurements, it shows a greater confidence in the early observations. And these two help also to accelerate the learning of unknown parameters. So other parameters of our simulation are shown here, but the most important ones are we had a simulation of over 1,000 Monte Carlo trials with over 50 time steps. So for the alpha filter, as expected, we have the EKF. Well, let's explain first what the lines are. We're showing in red the estimation error, while in black we have the filters, standard deviation, and in blue the Monte Carlo intervals. If the Monte Carlo intervals and the standard deviation of the filter agree, this means that the filter is consistent, and the error, we can see that it's stable as expected for the EKF, but we see that for the covariance, the standard deviation, the alpha filter shows some difficulties while processing nonlinear measurements, especially between steps 25 to around 40, where the intervals don't agree as well as we wish. But for the omega filter, we provide and show that the standard deviation shows some stability after its transient phase. And this is very good for statistics because then it means, or it could mean, that our filter knows what it's processing. We also have an interesting result here that is not bad, but we usually want the error to be as low as possible. But this result here in the omega filter is expected because we're assuming that an alpha filter is not being as precise as we want. So our dynamics in the omega filter are based on the alpha filter's estimate. And that's the reason why we use the time average mean square error to show that the omega filter really outperforms the alpha filter. So it's more accurate in this scenario. Some concluding remarks are, well, for our study, the estimation error remains bounded in the mean square sense and probability 1 if the following conditions are met. The first one is that the initial estimation error and noise terms are have to be small enough. The second one is that the nonlinearities are discontinuous. And this is met because we're using a kernel function approximation, which is, in our case, an exponential function. And if the error covariance remains positive, definite, and bounded. We also have some bonus result here that I would say. We have posted a paper before on the square root extension of the REKF. So these results are also applicable to that method. So they not only work for the REKF, but also its square root extension. And finally, we want to conclude with these two filters enable for adaptive and stable estimation to incomplete or uncertain systems and observations. And now I would be more than happy to take any of your questions.
Any question? No? Okay. Well, this is the end of the session, and we're going to have lunch next. Let's thank our speaker one more time. Thank you.
Usually bounded. It just means that here it's still go. It's going, it could go to infinity. Is the special purpose slower than?
Yes.
So it could linearly go to infinity.
Yeah.
Yeah, it's just in a case we're using a.
Hello, hello. Can I have attention, please? The lunch is served, so let's go to the other room and continue. Thank you. And you can leave your computers and bags in this room. Thank you.
Testing.
Just push that button down. There should be one more mic, yeah, for me. Good afternoon. I think we are ready to start the post-lunch session. Our next speaker is Dr. Bonnie J. Dunbar. She's a John and B. Slattery Chair Professor at Aerospace Engineering at Texas A&M. In addition to being an engineer, she's a retired NASA astronaut who flew on 5 space shuttle missions, including the first space shuttle flight which docked with the Russian space station Mir. She received her BS and MS in engineering from University of Washington, and her PhD was from University of Houston. Early in her career, she was an engineer for Rockwell International Building, the space shuttle, and responsible for development and manufacture of the thermal protection system. At TAMU, she directs the Aerospace Human Systems Laboratory and the Anthony Wood Artificial Gravity Lab Centrifuge at Texas A&M. Her areas of research interest are advanced spacesuit design and performance optimization using digital engineering and reduced gravity two-phase fluid physics. She was elected to the National Academy of Engineering. She's a fellow of the American Institute for Aeronautics and Astronautics, and also elected to the Royal Society of Edinburgh, and is an academician for the International Academy of Astronautics, AIAA. With that, please welcome Dr. Bonnie Dunbar.
Thank you very much. It's a real pleasure to be here, and I'm not going to talk about developing orbits, but I'm going to talk about how to use some orbits as we kind of delve into a little bit of a different topic. I'm going to have to... So there's another way to translate the title of my talk. It's how will our models for heat and mass transfer that we're so used to here in 1G really change when we go to a reduced gravity environment on the Moon and Mars. And this is based on my experience in a microgravity environment where we don't have a lot of the forces that we're so used to in fluid physics, especially liquids and gases. And I'm trying to get this to change here. Hold on. See, that'll go. Okay. I want to give credit to 3 of my students who really, our graduate students, performed the basis of our research. First placed poster for the International Space Station R&D Conference back in 2019 was my PhD student, Paul Burke, and an MS student of mine, Daniel Varnum Lowry. And it's based on the CFD work and some of the experimental work they did that I'm going to talk about today. Paul is now a professor at Johns Hopkins University, and Daniel went on to work for KBR. And in terms of follow-on instrumentation, one of my MS students, Jaden Carricher, is now a PhD student in mechanical engineering, and he won a poster for his work, third place poster at the International Conference on Environmental Systems. So this is the big picture. We're here on Earth. We're getting ready to go back to the Moon. Artemis 2 launches sometime between February and April of next year. That's a fly around, and then within a few years after that, we'll be back on the surface of the Moon. We have companies already developing infrastructure for the Moon that will take advantage of in situ resources. There will be chemical engineering on the Moon, and the question is, do a lot of those same equations apply? Because on the Moon you have 1/6 the gravitational level here, and then as we go to Mars you're at 3/8 the gravitational level. So most of the work that we've been doing in reduced gravity work has been in LEO, low Earth orbit, because we're in constant free fall. It's not really 0G. It says that we're all falling at the same rate. And there's actually some drag there. That's why we keep reboosting the space station. And we call it microgravity because that drag is actually 10 to the minus 6 G. But for all intents and purposes, when you're doing research on the station or the shuttle, we call it zero gravity. Everything's falling at the same rate. And so our normal perception of forces is not the same when it comes to fluids. So we had 135 flights on the space shuttle, many of them laboratory flights. Fluid physics was a big part of those, part of the flights I flew. This is just a few of those slides. This was from one of the inside the lab flight for STS-50, we called it, which was a U.S. microgravity lab flight. We had a number of fluid physics experiments from Case Western, from JPL. But this was not the beginning of fluid physics. We had to do fluid physics early on in the space program just to learn how to manage liquid systems in a microgravity environment. You fill a fuel tank with hypergolic fuels, and you launch to orbit. You're going to still use those fuels to come back. They're sitting there floating around in this tank. How do you get them to the ignition source? What kind of strategies do you have? So some of the very first experiments were done on Project Mercury, but they actually go back to a parabolic flight program at Wright-Patterson Air Force Base. Well, for the last 25 years, we've been operating continuously on the International Space Station. We have fluid physics experiments from all over the world as we continue to look at not just fundamental physics and fundamental processes, but in-flight fuel transfer, which is going to be critical for SpaceX, for example, to accomplish their mission in getting us onto the surface of the moon. So in microgravity, this is a typical slide that we use. We say there's no convection, there's no buoyancy, and there's no sedimentation. Those all can be problems when you're designing a system, but they can also be attributes when you're trying to do research. That's why we have some of the new crystallography work that's being done there, protein crystal growth, for example, new compositions in semiconductors. That photo on the left, which shows the candle burning, was actually performed on STS-50 in 1992, and it had to do with combustion. How does a flame, how does the fuels and the air and combustion all operate when you are in a non-buoyant environment? And it changed the way that we fight fires on spacecraft, as a matter of fact. So in a microgravity environment, without those forces, what dominates? Surface tension does. Liquids will wet what you don't want them to wet, and they'll beat off what you want them to coat. And then in many cases, you simply can't predict it based on the research you're doing on the ground. Pool boiling, which is a process that we use to control temperature in tanks, is problematic in a microgravity environment because the bubbles don't go up. You don't have normal buoyancy, and then the heating wires will dry out and burn up. All of these are important effects for cryogenic fuel management, ISRU, environmental control and life support systems, chemical bioreactors, and heat exchangers. And I think most of you have probably seen what astronauts do with liquids on orbit. See if we can get this to play. Put any liquid, water, Kool-Aid, coffee, anything out there, and surface tension will dominate into a spherical shape. Get it close to something with the right surface energy, and it'll completely coat it, depending on whether it's wetting or non-wetting. I don't know, that played for me, it didn't play for you apparently. So I'm just going to close it up here. It's actually quite a good video if you get to see it. And it looks like I'm going to have to start over. So in order to try to understand the effect of both gravity and surface tension materials in a variable gravitational environment, we decided to look at something we called a balance of forces, and where buoyancy was the only variable, and look at both wetting surfaces and non-wetting surfaces when we were using bubbles in a liquid. That's a little bit inverse to when you think of wetting and non-wetting. We normally put a liquid onto a substrate and the gas is on the outside. In this case, a model called the submerged orifice model, which is used in the chemical industry, was what we used, where we're actually growing a gas bubble on a solid surface in a liquid, in this case water and gas. So you can have a wetting liquid in this case, which is going to squeeze the bubble off, or a non-wetting liquid in which the bubble becomes entrapped. So what dominates when you're on the moon or Mars? Again, on Earth, buoyancy dominates. In microgravity, the solid surface tension dominates. Moon and Mars are in between Earth and microgravity. We had no specific experiments when we went on the surface of the moon, so we have nothing at 1.6 G. And most of what we've done, except for small centrifuge tests in LEO, has all been in microgravity. So to design this experiment, we had to look at all the potential forces which would oppose the growth of a bubble from a submerged orifice. We wanted to reduce ourselves to the buoyant force, so we had to grow a bubble very, very slowly. We had to reduce the drag. The only force that we wanted to consider was the buoyancy force being opposed by the surface tension force on the bubble. We looked at different materials that we could use to characterize this a variable G environment in different surface tensions. So you look at the far end of the scale. You look at what is not wettable. Wax on your car, plastics. Many of the systems in flight use polycarbonates. It's non-wetting. The glass on some of our experimental systems are quartz, high surface energy wetting. So we picked those two materials first to put into our experimental system and into our CFD model. And we actually measured our own surface energies using a Cecil test. Basically, we're looking at air, water, and various materials, whether they're wetting or non-wetting. We started out doing a CFD model. This is what Paul did for 4 years. We used a supercomputer here at A&M. We used a open foam solver, a volume of fluid solver, and working very closely with a lot of our fluid physics people, because I'm mostly a materials person and not the fluid physicist. We refined the cells and the model down at the orifice. We looked at polycarbonate, quartz, and stainless steel, and then eventually went to aluminum as the plates. Now, this is the final product from between zero gravity and Earth gravity, the gravitational level on the bottom, and the bubble volume, predicted bubble volume at detachment in microliters. And you can see they're not the same. And in fact, the predicted volume of the bubble at lunar gravity on some of these materials is widely disparate depending on what you're using. So if you look at Earth, we don't see that much difference when we do the submerged orifice testing. We've got the data, shows, if you look at the standard deviations, they're all sort of grouped together. The prediction, though, at the moon is that if you look at quartz, it's not going to change that much even when you get to Mars. But when you get to the lunar levels and below, and they'll all go to the microgravity, it will not wet. Polycarbonate has one, and stainless steel had two of the largest diversions on that. And then we later on added the aluminum into it. And both of those metals were difficult to polish, had grain boundaries in them, but behaved more like the polycarbonate than the quartz. We created a set of parameters on that, the coefficients on a power law, and actually Paul and I just to some point in the future want to continue on this work to say, okay, if I know the surface energy of my material and I know the gravitational level and I know the fluids, can I stick them into my CFD and predict what my containment material ought to be if I want bubbles to detach from the interior? Because if the bubbles do not detach, then my heat and mass transfer models are not going to be what I expect, especially in cryogenic fuel management. If I've got a cryogenic fuel on the surface of the moon and I'm storing it there for as my propellant, can I predict what the thermal gradients are going to be? Next, we had to verify the 1G work, so we designed, this is what Daniel did, this is the desktop experiment with a single chamber, 2 cameras, using high-speed CMOS cameras. There's a lot of testing involved in that in terms of the flow rates. We're able to generate bubbles that match the CFD. But again, we're sitting here looking at Mars and Moon and say, well, how do we test at those levels? At first, at one point, we had an opportunity to get onto Eclipse mission, which lands on the Moon. That didn't pan out, but we worked with Collins for about a year, I think it was, to develop a set of experiments that took us to a preliminary design review. That didn't work because we couldn't cover the launch costs. And so we decided to team with Southwest Research Institute. I have a colleague over there who's interested in pool boiling, not single bubbles, and we purchased a microgravity zero-G flight. Sorry, there we go. We built a device to go onto the zero-G. It had 4 levels. Southwest used the bottom 2 levels. We used the top 2. We flew in April of 24. For those of you that are familiar with the zero-G, it flies a parabola, and you get about 20 minutes or 20 seconds at some G level that they fly a profile for. And so we picked Mars and Lunar. Get back here. And Jaden, his chamber configuration was a work of art. We developed 4 chambers, 2 with each material, polycarbonate and quartz. You can see here the top view. We had a microliter air pump in here, and then we predicted how many bubbles we might be able to get per parabola, because the key is we wanted at least 1 bubble per parabola on the polycarbonate, and fortunately we actually did get that. So here are the photos from the zero-G flight, the chambers installed inside the zero-G, and I'm operating it because we were canceled 3 times and all my students graduated, and so they left me to go fly the experiment. We are still working on the calculation of the volumes in concert with Southwest. We're developing, and actually they're leading it right now in an AI process to automatically calculate the bubble volumes. But I did want to show you, here's a bubble from a quartz plate, and here's the bubble from the polycarbonate. You could see that it just kept growing and growing past the orifice until it finally got large enough where buoyancy separated it from the substrate. I think we could be in a situation where we get to the moon where the gravitational level is so low, and depending on the material, that you may have bubbles that stay entrapped on a surface, which is going to be a problem. We see that in zero-G, and it's going to be that combination of gravitational level and surface energy. They'll determine whether or not our models, which we don't have validated right now, will be able to predict how that will work. So we're off to the moon, and we've got a CFD model we think is pretty good for 0 gravity and 1 gravity, because those are the 2 regimes that we operate in. The plan is to have satellites, or having stations on the moon. That's my own. And what we learned from the moon, we're going to extrapolate to Mars. This is a NASA slide. And partial gravity operations, partial gravity science is going to be a large part of what we're planning to do. Again, Artemis 2 is launching early next year. I can see, and this is a NASA slide for the late 2030s, that eventually we'll be hopefully on Mars, and then we'll need to really understand how our systems are going to operate, because it's not a 3.5-day return trip. Once you're on Mars, you're there for 2 to 3 years. Thank you.
Thanks. Any questions? We have time for a few questions.
You're all experts now, right?
Can you explain the difference between a wetting and non-wetting again?
Yeah. Okay, so the way I explain it to my students is that if you wax your car, you want the water to bead off. That's non-wetting. And you measure that by the contact angle. If you put paint on your wall, you don't want it to bead up. You want it to spread. And that's wetting. So it's all based on interfacial surface energies, and we typically measure contact angles to determine whether it goes from wetting to non-wetting, but then quite frankly end up with experimental work.
So if it forms like a sphere and more than a hemisphere is off, that's the wetting?
Well, then it's a little bit backwards when you're talking about bubbles. And bubbles get in microgravity. We have a problem in both research and in heat pipes when bubbles are not driven by buoyancy and they become entrapped in systems because of the interfacial surface energy. And so that's why the title of the talk that we gave for the ISS was about bubble entrapment, because that has stopped experiments. It stopped our first heat pipe experiment on the shuttle. And if we don't understand, especially in low gravity environments, how bubbles are going to depart or be entrapped, it'll affect our heat and mass transfer.
Can you just put little fans or something in the water to encourage it to?
Well, if you do talk about cryogenic fuel, probably not. But the way we manage fuel right now in the tanks on the shuttle is we take advantage of capillarity, where we have screens to help wick the material away. But if you're talking about a tank and you're assuming that you've got a heater on the bottom, for example, and now you're not isothermal, but you're looking at boil off and all of those things, you need to be able to predict it. And that's the bottom line. We want validated models. Okay, thank you. My colleague is next, and he's going to take us back to Leo.
So our next speaker is Professor John Connolly. He joined A&M faculty after a long career, 36 years at NASA. And that included positions as NASA HQ Exploration Chief Scientist, Altair Lunar Lander Project Manager, and positions in NASA's Astronautic Office and Artemis Human Lander Systems Program. At A&M, he teaches the capstone and space-related design courses. He serves as the faculty advisor to the university's AggiSat laboratory and manages the A&M TAMU Spirit Laboratory aboard the International Space Station. John's NASA and academic careers have been devoted to developing human exploration systems and educating the future leaders that will take human crews back to the moon and lead them to Mars. Please welcome Professor Connolly.
All right. Thank you. We're going to take you from Mars and the moon back into low Earth orbit for a little while, and we're going to talk about a new facility that you'll see connected to the International Space Station in the next year or so. So some of you may have already heard the term TAMU Spirit. It is the name we've given to an externally mounted experiment facility that we're attaching to the International Space Station in the spring of 2027. So I wanted to give you a briefing about it, and maybe more importantly, let you know about some opportunities for all of you to participate in this and actually get experiments that can be flown in space up on the International Space Station. So first of all, what is this facility, and why does Texas A&M have their own flight facility on the International Space Station? Well, we are Texas A&M, and we want to be first in space. And part of that is to have a permanent facility on the ISS that is A&M branded for the exclusive use of Texas A&M system researchers, faculty, and students. Now, the system is Texas-wide, so it's all of the associated universities with A&M. But to be part of this, you only need to have the principal investigator be part of that A&M system. So if there's people from other universities, and I know there's people here, people even from private companies, even universities around the world, you can partner with the principal investigator from Texas A&M and fly an experiment on TAMU Spirit. We're very fortunate to have this. It's an investment by the A&M Board of Regents, along with a few of our very nice benefactors, specifically Aegis Aerospace and their CEO, Stephanie Murphy, who's one of our fellow Aggies, and the Wood Next Foundation. So let's go into depth and talk about what TAMU Spirit is. So as I said, it's an externally mounted flight facility, an experiment rack, if you will, that will be on the port side of the International Space Station. So picture in the upper right is the space station as it's flying away from you. It's mounted on Express Logistics Carrier 3, and the picture on the bottom basically shows you the idea of having this rack of experiments. And it can hold up to 12 different experiments simultaneously. And the idea is to continuously fly different experiments and leave them on orbit for 6 months at a time, and then return them to the principal investigators. So it's one of the very nice things about having this is that your experiment not only goes up into space, but it comes down from space and you get it back. The experiments are mounted on one of two different types of carriers. One is called a pallet carrier. That's the one on the left. It can hold an experiment that's about 45 centimeters long, 20 centimeters wide, and maybe about 35 centimeters tall. The one shown on the right is the science carrier. It's sort of like a foldable shoebox, and it's ideal for things like exposing materials to space and for experiments that have more of a flat platform. So those are the two we have available to us. We made an announcement earlier this year for experiments to fly in the very first flight of TAMU Spirit. We're calling that TAMU Spirit 1. TAMU Spirit 1 will feature 3 of the pallet carriers shown there in the upper right, and the figure there on the bottom shows where they'll be configured on TAMU Spirit when they're launched in the trunk of a cargo mission. So we've had a competitive selection, and we've selected 8 different experiments to fly on these 3 pallet carriers on the first mission. So I want to introduce those to you right now. So in spring of 2027, as TAMU Spirit, the flight facility, is loaded into the cargo mission, it will be pre-integrated with these 3 pallet carriers. And you see the orientation Z is for zenith. That means it's facing up to space. Nadir is facing down towards the Earth. Wake is facing anti the direction of travel of the space station, and RAM is in the direction of the velocity vector. So you get a lot of atomic oxygen in that orientation. So on the zenith side, facing space, and I'm going to go through each of these. We have a quantum dot experiment. We have an experiment with shape memory alloys. We have another one with printed aerogels and magnetic responsive resins. And we have some horticulture experiments with seeds. On the wake side, we have a larger experiment looking at different components of a robotic system. And then on the RAM pallet carrier, we have some entomology experiments looking at materials that are based, from bugs, along with an experiment on cells to see how we can look at survivability of certain types of cells in orbit. And then Shield 2 is really about different shielding materials for space. So let me feature each of those for just a second. And along with the PIs. So we had our first competitive selection back in August. In September, we made the initial announcement of the PIs, and these were basically the ones that were chosen for this very first mission. So we have Dr. Sun from the Department of Chemistry here at A&M with the quantum dots. We had Dr. Hartle from our Aerospace Engineering Department with the shape memory alloy morphing radiator. Dr. Pencer from the Department of Chemistry, along with her co-Is, looking at printed aerogels and the printability of magnetic response resins. And from our Horticulture Sciences Department, Dr. Justin Shiner, looking at the viability of different seeds in space, and in this case, specifically grape seeds. On the wake side, we have PIs Justin Wilkerson and his partner Dr. Tom Berlin from the Department of Entomology with the chitozans in space, which is looking at the durability of insect-based resins. We have Dr. Jeffrey Chancellor, who is the head of the Aerospace Medicine Department, looking at the survivability of endothelial cells, and this is the first of a 3-part experiment. And then SHIELD 2 actually comes from a number of our PIs from both here at A&M, as well as some of our partners from Lamar University and Prairie View University, looking at a follow-up experiment that's, the first one is actually flying right now, looking at smart skin technologies for materials flying in space. And then finally, on the Nader pallet carrier, Dr. Rob Ambrose, who many of us know in the mechanical engineering department, is going to be testing robotics components and avionics in the space environment to see how we can get the longest survived robots in space. When you take all those together, we have a very nice combination of PIs and organizations involved in this very first flight. And so you can see all the departments within the university that are involved in this. You could see other universities who have partnered with us, NASA research centers, and others. And so we're very happy with this first selection that we've been able to get a group of PIs together, and they had a very short amount of time to put their proposals together, only 30 days. And we've had this good group of PIs come together, and we have this very nice array of experiments that's going up on the very first flight. So they'll be packaged in the trunk of a cargo mission, along with the flight facility itself, and the launch time right now is sometime in the spring of 2027. And the plan is that we're going to repeat this process every 6 months. So every 6 months there'll be a call for experiment proposals, and we hope to go through those very quickly and announce them so that you have something on the order of 18 months between being selected and your flight. And every 6 months we'll pick a new set of experiments to go up as the previous set of experiments comes down from space. We hope to have a pipeline of experiments from A&M researchers and our affiliates that keep heading up to space station and coming back down. So we are just getting started. These first 8 experiments I talked about are just the first round. This is what we're calling the TAMU Spirit 1 mission. The next time we'll announce will be in the spring of 2026, around April. And the experiments that are picked for that second mission, which will be TAMU Spirit 2, will fly approximately in the fall of 2027, so about every 6 months on center. And we're hoping to see more and more of the departments here within this university and within the system universities around A&M, along with our partners from other universities, other companies, and others throughout the world flying on this facility. It's a very unique opportunity we have, and we hope to see many of you in space as part of this. If you want to find out more, our website is aggiespacelab.tamu.edu, or you can write for information tamu-spirit@tamu.edu. That's our official email address. You could just check the website, and it will show when the next call for experiments is coming up, and it will give you all the information, all the links you need to submit your proposal as well. So it's a unique opportunity. I hope many of you take advantage of it, and I hope we'll see many of you in space in the near future. Thank you.
We have time for questions. I'm sure there'll be a lot.
Very interesting. Is there a sort of cost for integration? Who is doing testing, management integration, and do we suppose that I come with a proposal that is selected from my university? Do I have to pay something to contribute to the development of the lab?
Very good question. Thank you for being the straight man on that one. The investment by the Texas A&M system basically pays for the facility on the space station. It pays for the operation of your experiment once it's up there. It pays for the transportation to get it there and to bring it home. What it does not pay for is the development cost of the experiment itself. That you'll have to find your own funds for, and describing the development funding and what the source of that is an important part of your proposal. So basically, it's a free ride up. It's operations for 6 months on orbit, free ride down. You just have to figure out how to get the experiment built. Right?
But the cost of testing, vibration testing, this kind of thing is, because there will be several payloads, several experiments. So is it shared by the different experiments?
So we would encourage you, if you have the facilities available, to do some thermal vac testing and vibrational testing on your experiment. If you don't do that, you're running a little bit at risk, but before we send any experiments up, we will vibration and thermal test the entire rack of experiments as a unit. And so nothing will fly into space unless it's gone through all the testing. But it would behoove you to do a little bit upfront testing before you turn the experiment over. All right.
Just following that questions, but there is, as far as understood, our payload will be launched on the International Space Station, but we have some link. I mean, there is a communication with the ground station.
Another good question. So yes, you will have frequent communication with your experiment. The experiments need to be more or less standalone, so you can put them out into space, turn them on, and they do what they do. They have power available to them up to 60 watts. They have a communications link, and it's all given in the interface document we give you. And you can get real-time data down from your experiments, or you could get it dumped on a regular once a week or once a day, whatever you'd like it. So yes, there will be a portal given to each of the principal investigators that will link you directly to your experiment, so that you can see how it's operating, and you can download the data coming from it.
Can we send commands?
Yes, you can. So there are opportunities to send commands up to your experiment. There are small windows based on the communication windows that are available to the space station that are allotted to us, that we can command things on and off, or recycle your experiment, or whatever it is you want. So yes, there is both uplink and downlink, so we can send commands to the experiments.
Thanks.
All right.
Any other questions?
All right.
Thank you.
All right, we hope to see you in space.
Exciting. So, our next speaker is Professor Butcher from the Aerospace and Mechanical Engineering at the University of Arizona, where he directs the Autonomous Space Vehicles and Astrodynamics Lab, and has joint appointments with Electrical and Computer Engineering and the Applied Mathematics Graduate Interdisciplinary Program. He has received the BS in Engineering Physics from the University of Oklahoma, MS and PhD in Mechanical Engineering from Auburn, and an MS in Aerospace Engineering Sciences from the University of Colorado. After obtaining his PhD, he was a postdoctoral fellow at Sandia National Labs, assistant and associate professor at the University of Alaska Fairbanks, and the Dwight and Aubrey Chapman Associate Professor at New Mexico State University, prior to moving to the University of Arizona in 2014. His research interests include the stability and control of dynamic systems with time delay, fractional dynamics, parametric excitations, control and synchronization of chaotic systems, cooperative control of multi-agent systems, optimal orbital transfers, and control of spacecraft, relative motion, and attitude, with a focus on proximity operation and attitude pose synchronization. So with that, let's welcome Professor Butcher.
Yeah, thank you. When I was thinking about an appropriate topic to present at this symposium, I definitely recalled much of Daniele's earlier work on attitude estimation, which was a big inspiration for me to pursue problems in attitude control and estimation, although admittedly I've done much more control than estimation in that area. But that's why I chose this topic. And I worked with my postdoc, Mohammed Madani. He did most of the work on this, this topic. So here's some applications of finding the mean of rotations. The most important one for this group may be the first one on spacecraft attitude estimation for multiple star trackers, but here's a list of other applications. And I can say that there's a subgroup of literature on attitude control and estimation which addresses these problems directly on SO3, meaning that it works with the rotation matrix rather than the quaternion or some other attitude parameterization. The reason being that it avoids issues with singularities, non-uniqueness, and undesirable effects of discontinuous control. So I can say that this presentation is in the spirit of that philosophy. So we have proposed a new algorithm for computing the mean of multiple rotations based on geodesic interpolation. It improves the robustness and expands the region of attraction compared to the Karcher mean algorithm. This, you can see the references below. So the algorithm itself was actually proposed by Manton, but it's based on the mean that was proposed by Karcher. And it avoids the intermediate step of quaternion computation. And I referenced the paper by Markley. The title of that paper was actually called Averaging Quaternions, but it's actually also applicable for averaging rotation matrices, and I'll get more into that later. But that is based on chordal interpretation. So the proposed method iteratively updates the mean and consistently yields an identical result to the use of chordal interpretation, which you would get by the Markley method, as well as, and this is what motivated our work in the first place, to the containment problem on SO3 with n fixed leaders, a single follower, and globally continuous control. So the 3D special orthogonal group SO3 is the configuration space for rigid body attitude defined here. It's a Lie group, and we assume that a member of this group is a rotation from the body frame to the inertial frame, and therefore we use the left invariant kinematics shown here. Everybody's familiar with the cross matrix operator. We use the down caret to undo that operation and map from the Lie algebra, small SO3, back to R3. And of course the principal rotation angle and axis everybody's familiar with. Down here at the bottom, we use the y of r notation to define the skew symmetric component of the rotation matrix, which, using the definition of the principal axis, is equal to the sine of the principal angle times E hat cross. Now, we all know that we cannot simply add rotation matrices, and we can't take their arithmetic mean to get a mean of rotations. Because when we add rotations, we multiply the rotation matrices. Furthermore, we want to preserve the geometry of SO3 when we take the mean. So this might point to a couple of naive approximations, I call them. The first one is the geometric mean. It's basically analogous to taking the geometric mean of n scalars. You can see the analogous formula here in terms of rotation matrices. This is not a good approximation, though, since even though it preserves the structure of the geometry, it depends on the order of multiplication. A slightly better strategy would be to take the arithmetic mean of the matrix logarithms of the individual rotation matrices and then exponentiate the result. This also preserves the geometry, but it still is not good for many sets of rotations. And what some people have done is actually to take the arithmetic average of quaternions and to normalize that to get the unit norm, and then you can extract the corresponding rotation matrix. So I talked about chordal interpretation. In chordal interpretation, this arises from using a specific embedding of the manifold into a Euclidean space. Okay, such as the use of R2 when taking the chord between two locations on a circle here. So the chordal distance is defined here as the Euclidean distance, defined in terms of the Frobenius norm of the arithmetic difference of the rotations. And this is related to the sine of the half of the PRA associated with the relative attitude. So using this metric, we can actually get the weighted mean, called r hat court here, which should minimize the weighted sum of the squared Frobenius norms of the rotation differences with a projection back to the manifold. And essentially, this is the problem that's being solved in the paper by Markley et al. I reference here. But the machinery used to solve this is simply the machinery of the Davenport Q method by finding the quaternion, which is the eigenvector of the 4x4K matrix corresponding to the largest eigenvalue. But here the B matrix is actually defined as the weighted sum of the individual rotation matrices rather than in terms of unit directions as we usually have in attitude estimation. So in contrast to that, we use geodesic interpolation. Okay, geodesics, of course, represent shortest paths between two points on a compact manifold. And as we see in the picture, the geodesic arc between those 2 points is the curve on the surface of the circle. So unlike chordal interpretation in Euclidean space, geodesic interpolation respects the manifold's geometry. So for two rotations in SO3, the geodesic interpolation is defined here, where the lambda is an interpolation parameter between 0 and 1. Notice that r hat GO of 0 gives you R1 back, while if you use lambda equal to 1, you get R2 back. So intermediate values of lambda smoothly transition from R1 to R2 along the geodesic path. And if we want the unweighted geodesic mean, we simply use lambda equal to 1/2. The natural question arises how to extend this formula for more than 2 rotations, though. And there's no closed form formula, so that actually is why the Karcher algorithm was invented, to actually extend this approach to more than 2 rotations. So first of all, let's look at our proposed algorithm, and I'll show you the difference between ours and the Karcher algorithm. So ours is on the left, and so given n rotations, R1 through Rn in SO3, we initialize an initial guess, r hat m, which could be, but doesn't have to be, equal to one of the initial rotations. We choose a tolerance, compute the skew-symmetric matrix A. Again, remember Y extracts the skew-symmetric component of its argument. And then we update the guess using the multiplication by the matrix exponential of matrix A. Now, the difference between the Karcher algorithm is in the way A is computed. Step 2 in the Karcher-Manton method is actually using the logarithm of that relative attitude rather than extracting the skew-symmetric component. And this is a very subtle difference. As I showed earlier, the y of r is actually equal to sine of the principal angle times E hat cross, whereas log of r is equal to the angle itself times E hat cross. And this makes a big difference in terms of convergence characteristics of these algorithms. So first of all, you would expect that this algorithm does minimize a cost function. And it does. It minimizes this Morse-Bott function that's shown here, which has non-degenerate equilibria. It usually has a unique minimum, although there are exceptional circumstances where the minimum is not unique, and it has a continuous manifold of maxima. So our algorithm is actually a Riemannian gradient descent algorithm that minimizes this cost function. So the Euclidean gradient is shown here, and that can be used in turn in projecting the Euclidean gradient onto the tangent space, TSO3, to give the Riemannian gradient, which is defined in the bottom of this slide. And notice that the Riemannian gradient actually involves the extracting the skew-symmetric component. You see the y of the relative attitude between Ri transpose R there. So if we set that to 0 and solve for R, this actually gives us the Rm that our algorithm converges to. So let's look at an example of 2 rotations. So we have the 2 different rotations separated by a relative PRA of 140 degrees in this case. And you can see the errors plotted versus the interpolation parameter lambda compared to the exact result obtained from geodesic interpolation for the geometric mean, arithmetic mean, quaternion averaging, which I mentioned before, just arithmetic average of the quaternions and taking the unit norm, and then also the quartile mean, which again refers to the paper by Markley. Notice that the last two actually have 0 error for lambda equal to 1/2. And that's significant. I'll mention this later in this talk because we're ultimately interested in here in obtaining the unweighted mean in rotations, which means we would be interested here in lambda equal to 1/2. We do see that the geometric and arithmetic mean approximations are not exact in that plot. So on the right we have a chart of different cases for different relative attitudes. You can see that the number of iterations required by our algorithm versus the PRA of the relative attitude. And this points to the fact that for 2 rotations only, our algorithm is actually not advantageous because the Karcher mean converges to the exact result, the geodesic mean, in only 1 iteration. That's if the initial guess is actually R1 or R2. Okay. So for only 2 rotations, we don't see the advantage yet in our proposed algorithm. What we need to do is go to more than 2. But before I do that, let's take a digression and look at a type of multi-agent cooperative control protocol known as the containment protocol. So if you have a group of agents, you can have one set of followers and one set of leaders. In the graph here, you can see that the green agents are the leaders and the yellow agents are the followers. So according to this graph topology, we have a 6x6 Laplacian matrix. And for this control protocol for the followers that's shown here, we actually get a compact form that involves the Laplacian. So you can actually prove that the followers, if the leaders stay fixed, the followers converge to the convex hull defined by the leaders, which in this 2D space is actually this triangle defined by agents 4, 5, and 6. So now we can apply this to SO3. Let's look at the case of 3 leaders and a single follower, and let's look at the containment problem on SO3. First, in the case that the 3 attitudes are in close proximity. And our containment protocol here is, it's a kinematic level protocol, so we set the angular velocity equal to this sum, and it involves, again, extracting the skew symmetric component in the y function. And when we plug that into the left invariant kinematics, we actually get a gradient descent algorithm. And again, you see the cost function that is minimized in this containment protocol is exactly the same cost function that we actually minimized in our algorithm to compute the mean of n rotations. So that should be no surprise that then we actually converge in on the same attitude for our follower that we get by our algorithm. And here is an animation. In this animation, you see the 3 fixed leaders in blue, green, and red, and the follower is in yellow. And you can see it going to the convex hull defined by the leaders. So these plots are of the 3 elements of the principal rotation vector. In those plots, because the leaders are relatively in close proximity, you do see those elements converging to the convex hulls. But if we have the leaders widely separated, as in this example, and you see the PRAs of the relative attitudes on the right there are pretty large in this case. So we actually compare our result in our algorithm with that of the Karcher algorithm with 3 initial guesses, with R1, R2, and R3. And you can see that the Karcher algorithm gives 3 different results. So it does not exhibit robustness to the initial guess, whereas our algorithm actually converges on the same result for all 3 initial guesses. The results from the arithmetic mean and also the quartile mean are shown at the bottom, and most importantly, the quartile mean using the Markley method actually gives exactly the same result as our algorithm. So now let's look at the corresponding containment problem for the same 3 leaders. And we see that Again, for 3 leaders and 1 follower, this containment protocol up at the top causes the single follower to converge to exactly the same final attitude that we got using our algorithm. Now you may ask, is there a containment algorithm that actually gives you one of the results that the Karcher method actually showed? And the answer is yes. So underneath this horizontal line, you see if we modify the containment protocol using a log function instead, this actually converges now to this attitude, which turned out to be the second rotation obtained by the Karcher algorithm, that is, using an initial guess of R2 only. And this attitude is actually 171.3 degrees from the result from our algorithm. So this points to an advantage that ours has, which is when the weight of the rotations is on the opposite side of the manifold, you see a flip of the follower to the other side where the weight of those rotations is. And we'll see that in another example in a second. And here is a comparison between the 3 elements of the principal rotation vector for these 2 algorithms. So this is the final example I wanted to show. And this is for computing the mean of 5 rotations. So here we actually choose the initial guess to be the relative attitude, or in other words, the geodesic midpoint between 2 of the 5 rotations. So our first initial guess is the geodesic midpoint between R1 and R2, and so on. And you can see that the computed RM from the Karcher algorithm actually is not the same in these 3 cases, although the second and the third cases do give the same result. And you can also see the number of iterations that are required. For our algorithm in the right column, you see that it gives the same result for all 3 initial guesses, although the number of iterations is higher. So this again demonstrates the robustness to the initial guess, unlike in the Karcher algorithm. And then here's the corresponding containment result. In this case, having 5 leaders and 1 follower. And the containment algorithm causes the follower to converge to, again, exactly the same attitude that corresponds to the result from our algorithm. And again, you see that if we change the containment protocol using the log function, then this actually converges into a different rotation matrix, which is actually identical to the second and third rows of the Karcher method, meaning the use of initial guesses R34 and R45 only. And this final attitude is actually 14.8 degrees from the result from our protocol. So we see that the Karcher technique fails to converge when to the true average when the initial guess is chosen as R12, but ours is, again, robust to the choice of the initial guess. How much time do I have? 3 minutes? Okay. So I'll mention this final example then. I said the last one was final example. But this is another example with 5 rotations. And in this case, we select R1 to be this, this rotation matrix, and then we choose the other 4 so that the PRAs are theta 1, 2, theta 1, 3, and so on in this table, where the negative PRAs are interpreted as flipping the direction of the principal axis, of course. So you can see that the average of these PRAs gives you 0, meaning that you would expect for both of these algorithms to converge in on the rotation R1. And in fact, in set 1, it does, but in set 2, the Karcher algorithm actually converges in on the same R1. On the other hand, our RM hat actually does not. It converges to something else, which is actually 180 degrees away from R1, about some axis. So what happened here? Well, you can see that we have actually moved these relative PRAs in such a way that the weight now is on the opposite side of the manifold SO3. Okay, so when we did that, we would expect for the follower in the containment algorithm to converge to the opposite side of the manifold, and actually our iterative algorithm to find the mean of rotations does the same thing. All right, so in conclusion then, we've proposed basically a modification to the Karcher algorithm. It's a very subtle modification, but it enlarges the region of attraction and improves robustness to the initial guess to computing the mean of rotations on SO3. And it does agree with the result from chordal interpretation using the Markley algorithm. I should say that it also agrees with the result from the containment problem for n leaders and 1 follower. And we are currently working on studying the containment problem on SO3, which has very subtle issues that do not occur, of course, on containment problem on Euclidean spaces. One final point I'll make is that this is more than just a mathematical and theoretical problem. So, for example, you could use the same algorithm to average the mean of rotations on higher dimensional spaces like SON. And this brings me back to the paper of Daniele's that I was really inspired by and motivated some of my recent work, which is paper on higher dimensional rotations. And that was actually very instrumental in some of my recent work, and I can say that you know, this is also applicable to the problem of higher dimensional rotations as well. Thank you.
We have time for maybe one question. Any questions? Well, let's go ahead.
Oh, interesting. Thanks. What happens if you just average the Euler angles or do something on those? I've seen the work by Markley and the quaternions, and then this is new to me.
Yeah, I mean, we avoid using Euler angles or any other minimal attitudes for singularity issues. If you average Euler angles, you'll probably get a different result than these algorithms do. And you can run into singularity issues. Certainly, I would be afraid of using Euler angles for the containment problem.
Yeah, I think you would just want to be in a regime where you're, you know, not singular.
Yeah.
All right. Let's thank the speaker one more time. Our next speaker is Pete Lealy, Jr. He's a PhD student at the University of Texas at Austin and is a graduate research assistant in Dr. Maruti Akila's controls group for distributed and uncertain systems. His research focuses on learning-based control and trajectory optimization under uncertainty, particularly for space and robotic systems. Let's welcome Pete. That's USB. Which one of these cables? That's the.
I got this. Yeah. Sorry. 1 second.
This is a Mac.
Yeah, it's a Mac.
Sometimes I have impedance issues.
Should I switch to Windows or Dell?
No, never. You move to his Mac if you want to.
Shit.
You got HDMI direct?
Hello? Oh, nice. Sorry about that. I'll make up for the time somehow. So my name is Pete Lilea, Jr. Again, I'm a graduate research assistant in Dr. Muthi Akela's Controls Group for Distributed and Uncertain Systems. And today I'll be talking about successive convex semi-definite programming and information-driven spacecraft trajectory planning. We'll embed this idea of navigation awareness into the guidance optimization. And this will be mainly for rendezvous and proximity operations, just for this presentation. And what rendezvous and proximity operations involves is this broad class of missions where we're planning maneuvers for these closely neighboring spacecraft to interact with some resident space object. That resident space object can be an active or defunct satellite or even some space debris. And those interactions can be the capture, connection, or removal task within those mission operations. And the development of guidance, navigation, and control laws and technologies within this mission regime have really focused on this idea of on-orbit servicing, assembly, and manufacturing, active debris removal, and enhancing space situational awareness. However, when we get into RPO scenarios that involve uncooperative target RSOs, we're almost immediately hindered by this idea from these operational uncertainties from this lack of mutual inter-satellite communication and collaborative decision-making. So what this work really will propose is an optimization of RPO maneuvers for this distributed space system, being a space system of many spacecraft, to resolve that uncertainty in a target RSO while doing these RPO mission operations. So just over the last couple of years, there's been a lot of work in maneuver planning under uncertainty. And I'll talk about two categories of literature right now. One of those categories being covariance steering, which has to do with the steering or maneuvering of some belief distribution of a governed spacecraft to a terminal belief distribution considering some probabilistic constraints. And then pre-posterior motion planning, on the other hand, is more concerned with the configuration of these spacecraft, the placement of their observations, and the resulting resolution of mission uncertainties. In both of these categories of literature consider a priori hypotheses, the onboard sensing modes, as well as sometimes a filtering process. So what this work will really be is an extension of the work already done by Drs. Wolf, Friedrich, Kiel, and Jones, in which we will reformulate some iterates of a successive algorithm to be a convex semi-definite program that can be solved with some readily available solvers, avoiding first-order approximations for this information gain objective that we'll talk about later. And we'll also propose some bootstrapping under posterior beliefs to re-optimize that guidance under the posterior coming from the measurements taken while executing that guidance, essentially. So just as a review, when I have some prior hypothesis of the target RSO's motion, when I collect evidence or observations about that motion, I can form some posterior belief of that motion given that evidence. And what this work is really going to try to do is place these observations within the operating region in order to improve the confidence in this posterior distribution and the estimations made therein. So to quantify the uncertainty in a distribution, we'll actually use Shannon's entropy, which I think came up in an earlier talk. And for a discrete random variable, it's shown as this yellow box here. And what it's really measuring is this expected uncertainty or surprise in sampling the distribution, where low entropy relates to these more predictable outcomes from the distribution and high to more unpredictable. And what Shannon says in this work, introducing this for a discrete support, is that for a continuous support, you should just replace this sum by the integral across the continuous time support, or the continuous support. Where these P's, I forgot to mention, is on the left-hand side, it's a PMF, and on the right, it's a PDF. But when you replace the sum by an integral, it's actually not the direct analog for the discrete version, and it has its own criticisms of not being that direct analog. But we won't actually be using differential entropy directly. We'll actually be using mutual information, which measures this reduction in uncertainty of a random variable when you're given evidence of another. For us, those two random variables will be the belief distribution of the target RSO's motion and the distribution of those measurements we collect from the DSS agents. And where they're jointly Gaussian distributed, we'll find that it's proportional to the log of the determinant of the marginal measurement covariance divided by the determinant of the conditional measurement covariance. Where this B here, you probably can't see it on the video, but this B here is usually 2 to quantify these measures in bits. And these measure comes from information theory, which is pioneered by Shannon Claude. So just to take a step back, we'll talk about some of the other models we'll consider in this optimization. First off, for these DSS agents, we won't actually be considering like the stochastic nature of that transition. We'll actually just be modeling it as deterministic, where we're not really concerned with the uncertainties in those DSS agents' motion, their maneuvers, or the insertion into this RPO operating region. more so just providing this reference for them to track, giving this reference trajectory that's good in terms of the configuration and the measurements taken by them. However, for this target RSO, because we lack that authority over its motion, we're almost immediately prompted to give it this stochastic model for its transition, which is given by this SDE up here, where we've modeled the unmodeled environmental effects as this transformed Wiener process by G2, and passive maneuvers as some uncertain increment off of a nominal maneuver policy. The measurement model is then, as is assumed in most cases, is this smooth function H that's a function of the target RSO state, and the DSS agent state taking the measurement with additive Gaussian measurement noise. And then when we have some a priori hypothesis on that initial target state, target RSO state, and the nominal maneuver policy, we can actually make local approximations for the measurement model here on the left and the motion model. If we look here at this motion model, we can actually collect all of the uncertainty in this approximate motion model here, that being the increments off of the initial state hypothesis and the increments off of the nominal maneuver policy hypothesis, and these unmodeled effects to epsilon, into a single parameter gamma, which we'll use to quantify the uncertainty in its motion, and we'll additionally assume is jointly Gaussian distributed based on the intervariable correlations. And then we'll rewrite this measurement model here on the left again as a batch measurement model that's a linear function of this gamma parameter with additive Gaussian noise. So when we make those assumptions on those approximate models and distributions, we actually find that the mutual information between the measurement distribution and the uncertainties in the target RSO's motion is proportional, again, to the determinant of the marginal measurement covariance, which is a function of the configuration of the DSS agents over this planning horizon, divided by the determinant of the measurement noise covariance. And we'll go over this last constraint here in a second, talk about some of the problems with that. But our objective at a high level is, again, to maximize this sense of information gain from the configuration. But we also need to be considerate of the delta V usage to get into these configurations from the initial states of the DSS agents. So when we transcribe this optimization problem, we find that it's almost a convex semi-definite program. If not for this last constraint underlined in red, which is likely non-affine equality constraint due to the relationship with the target DSS, the DSS agent's dynamics model and this local linear model that we've made in reference to the target RSO's hypothesis. And then we're going to generalize a little bit more, where here we've written out that problem again, instead now with these normalization factors C1 and C2 to balance these sub-objectives to a consistent score, an alpha parameter to prioritize either this information gain or delta V usage. And then there's two categories of constraints here now, the native problem constraints, which we've introduced for trying to set up this information gain objective, and then some operational constraints that might come from the mission requirements. And within both of these sets of constraints, there may be non-conforming constraints that require some treatment. But because it's so close to a convex semi-definite program, we'll actually use successive convexification to solve this optimization. Specifically, successive semi-definite programming, be it the SCVX procedure, which at a high level will approximate these non-conforming constraints near a reference trajectory. It'll solve a locally approximate penalized convex semi-definite program near this reference in a given trust region. And then based on the performance of that optimization, it will update the reference trajectory and trust region accordingly. And then it'll iterate through this process until some convergence tolerance is met. And this has convergence guarantees that you can find in this paper that have to do with constraint qualifications and characteristics of the problem. But I won't go too much into this for this high-level talk. So we'll do this optimization in this RSO approach in low Earth orbit. We're trying to task these two agent DSSs, which are initially in this collinear measurement configuration, to approach an actively maneuvering uncooperative target RSO, where we believe it to be in some 400-kilometer altitude low Earth orbit while it's trying to take informative measurements of the target RSO with these ranging sensors. So we'll also impose some additional constraints just for this case, those being these safe interagent separation, which just makes sense. I don't want them to collide or want them to think they're going to collide or get too close to that collision. And then this safe agent target separation, which is just some statistically normalized distance coming from the prior hypothesis. And then some fuel and terminal speed constraints. The first two of which being non-convex, inequality constraints, which require some treatment through that SCVX algorithm, and the last two being convex constraints that don't really require treatment. So when we do this over different prioritization factors alpha, where alpha equaling 1 is a pure minimum delta V optimization, and alpha equaling 0 is this pure maximum information gain objective, we're able to perform this parallel front, which is telling us a little bit about the sub-objective trade-offs when we do this optimization. And the main takeaway from this is really that there are instances where I can spend about 5% of my fuel budget to gain 40% more information about the target. So why wouldn't I? And if we look at an intermediate case, we can go a little bit more on the time series data, and we just see that the entropy in the posterior belief under these approximate models is reduced compared to this purely minimum delta V optimization in that right-hand plot, top right, sorry. So there's already a few limitations in this work up until this point. The first being this assumption of Gaussian random variables, which I'd really argue is only to make this proxy objective to promote these good configurations within the operator region. And then there's this sense of optimization near prior beliefs, in which the substantial deviations from the prior hypothesis of the true target state can cause degeneracy in these distribution approximations we made, as well as causing some excessive suboptimalities, which we do not want. So what we've been extending this work to is doing this online replanning in situ under posterior beliefs, where we notice that, yes, I prescribe this configuration guidance to the RSO agents, but while they're executing this guidance, I'm actually getting measurements which can inform me more about this guidance task and help me refine this sensing configuration and reassess these mission risks and constraints. So what we'll do here, and this is something we're still working on, but is we'll first, in that green box, is optimize under the prior. We'll update some reference maneuvers which will be tracked in the environment. And while it's tracking those reference maneuvers, it'll take some sensing measurements, which will be filtered through some alpha beta-like filter, which will update some motion posterior, which we can then re-optimize under if we wish to. So we'll go back to that previous task, this time doing this bootstrapping, and we find the following. Here I've actually just restricted it to planar to plot a little bit more of the plotting elements. And this motion posterior in pink that you're seeing is just an EKF going over both of the agents' measurements. And every now and then you'll see that that gray ellipse collapses down. That's when we replan under this posterior coming from the EKF. And we see that we're able to complete this approach task a little bit more effectively under these posterior beliefs given our guidance algorithm. So within this work, I know this was a quick talk, but we've developed this structured successive semi-definite programming method for optimizing this sense of information gain and fuel usage with convergence guarantees. We've also proposed this bootstrapping algorithm for replanning under posterior beliefs. And we further verified these methods in simulated low Earth orbits where these DSS agents have been equipped with target ranging sensors. However, this bootstrapping that we've proposed and are still working on has this added computational cost that really needs to be addressed in order for us to deploy this on board in practice. Thank you for your time. Any questions?
Are your dynamics linear?
In this case, yes, but it's not restricted to be.
Okay, so my prior experience with these problems, with these belief space planning problems, if you have nonlinear dynamics, so you really can't balance the control and the, like your information objectives, especially if you're doing Gaussian stuff, right? So you really have to relax the control objective because your like the covariance, it's just minuscule compared to your actual control effort if it were nonlinear. So that's why my question is, like, if it is a nonlinear problem, then your alpha 1 minus alpha, that was why I was curious, right? That you are able to balance them. In my experience, you'll have to put alpha to be 0.
Alpha to be.
If you were nonlinear.
Are you saying because of the size of this determinant of the covariance?
Yeah, basically to have any effect that the cost just is dominated by the control cost if the dynamics were nonlinear. That's why I was wondering, is that the case here? So you seem to have nonlinear dynamics.
These aren't nonlinear. They are linear time varying, but it's just because it was simpler to implement. But in this case, what we're actually doing is this C1 term is an initial information gain based on the minimum delta V trajectory. In practice. In this one, we didn't do it for this parallel front, mainly because we were trying to show you're really only getting 1% more to some initial reference that we're iterating on for a minimum delta V. But for a little bit more prioritization on this information gain, we can gain 40% information. But in practice, again, the C1 should normalize it. And the normalization of that, we talk about in the paper. And the C2 is another normalization factor on the input. So these are more so like on the same score in which we're saying we're using some percentage of the fuel and getting some percentage of information. So that's how I balance it. I don't know if that would solve what you're talking about.
It's okay. We'll take this offline. I can send you some pointers as to what I'm talking about.
I would definitely appreciate it.
Thanks.
Thank you so much.
Any other questions?
Thank you for your time.
Wait, hang on. I've got a question.
Sorry.
So that convex, that P delta y equal to h of x, how did you successively convexify it?
So we make a first order approximation. So maybe, we make a first order approximation, and there is a requirement on smoothness for all of these functions in order to make that approximation.
So yes. Is that what Bechet's software doing?
That's what I'm doing by hand. So this is the procedure. We don't send this into some like off-the-shelf software.
Okay.
The only off-the-shelf we use is the thing that's solving the semi-definite program, which is just coming from Mosaic.
Okay, excellent.
Shout out.
Thank you. So let's thank the speaker one more time. So our next speaker, come on and set up, is a senior, Kapilan Karunakaran. He's a senior at Mira Loma High School in Sacramento, California, where he's currently pursuing the IB diploma. As an aspiring engineer, Kapilan has done internships and training programs at MIT, Beaverworks Summer Institute, and NASA Ames Research Center. He has published research on topics ranging from air quality estimation using machine learning to sustainable aviation fuel, and has contributed to open source chip design projects such as Tiny Tape Out. Kapilan is a nationally ranked candidate master in chess and a passionate STEM student. Please welcome Kapilan.
All right then. Hello, my name is Kapilan, and today I'll be presenting on modeling contrail formation using an SIR framework. And I did this research in correspondence with Mr. Alonso and Dr. Seyshire, who both work at the Department of Mathematical Sciences at George Mason University. So starting off with a bit of background on what the actual problem is. So contrails that are released from aircraft, they are able to trap heat within the atmosphere. And specifically, it's these prevailing contrails, the ones that kind of stick around after the aircraft passes through, that can spread across the atmosphere, and this can lead to an almost enhanced greenhouse effect kind of condition. And this leads to almost a 35% contribution in all of the aviation industry's emissions. And this problem is not going to get better without a solution, because as global air traffic increases, it will only increase the amount of contrail formation. And therefore, we need a solution in order to find a way to model this properly so we can kind of understand the problem and move on from there. So what we did was kind of a creative way of modeling these contrails using an infectious disease model. So the SIR model is a compartment-based model that uses a system of differential equations in order to model the transmission of various infectious diseases. And it starts with these three separate compartments: susceptible, infected, and recovered. So in the image on the right, you can see the three equations, the base equations that are usually used for the three different compartments. So susceptible to infected, there is a rate of transmission, which is beta. And then from infected to the recovered compartment, there is the rate of recovery, which is represented by gamma. And the visualization of these three equations over a period of time is represented in the graph below. However, what we realized was that contrails can have a kind of analogous transmission to an SIR model, which is what we took our three separate compartments to be susceptible as the cold, humid areas that are prone to contrail formation. And this is kind of an oversimplification, but what actually is happening is we're taking the Schmidt-Appelman criterion, which compares the vapor pressure and temperature and visualizes the mixing line, which is based on a specific aircraft's fuel combustion efficiency. And by taking the specific area that satisfies the Schmidt-Appelman criterion, that is the susceptible compartment for our model. And from there, the infected and recovered are pretty standard. The infected is just areas where contrails are present, and the recovered is after contrails have dissipated the areas that represent those occasions. So what is our problem statement and our goal? So we're starting off by developing a one-dimensional SAR model to be able to model these rates of contrail formation and dissipation accurately. And in order to do so, we have four major steps. So number one is we currently have the SAR equations in the previous slide that I showed, but what we need to include is an advection constant, which basically represents the fluids, which are air in our case, being able to move contrails throughout the atmosphere. And after that, we'll be using the method of manufactured solutions to solve this partial differential equation and verify our numerical solver. And after that, we're implementing the forward time-centered space. This is a specific finite difference method, and to make sure we're accurately modeling the stability conditions to show that our solver is actually working as intended. And finally, we're just going to repeat this for all three equations, so every single compartment for susceptible, infected, and recovered, and display this to show a visualization. So starting off with the reasoning behind why a partial differential equation system and not just an ordinary differential. So the main reason here is that contrails, an ordinary differential equation system would be able to model how contrails move throughout time. However, what we also want to see is through a one-dimensional line in space and how contrails change in that specific dimension. So now because of that, we have this advection constant. You see u times the partial of s with respect to x. And by adding that additional variable, we have these new parameters, the constant velocity of advection. It's important that it's constant. I'll explain why in a bit. And other than that, we just kind of modified beta and gamma. Rather than representing rate of transmission and recovery for an infectious disease model, it's now rate of contrail formation and dissipation. Okay, so the second step was to use the method of manufactured solutions and to validate this PDE system. So for example, this is just for the susceptible compartment, the equation on the top right. And basically, we manufactured two different solutions, so s of x comma t and I of x comma t, because those are the two variables we have. And now by creating a forcing term, because what's going on here is that in the original equation, there is a sort of error, and that error can be solved by adding on a forcing term, f of x comma t. And in order to solve for this forcing term, what we're doing is we're just taking the partials with respect to x and t of the two manufactured solutions we have, s of x comma t and I of x comma t. And it's important to note that these, all we really wanted them to be was differentiable. It is true that you could take various other equations in order to do this, but this was simple enough for the solution we needed to find, and it worked well. So after we do this, we solved for the forcing term, but that doesn't really get us where we need to go. So we have this forward time-centered space method, which is a explicit finite difference method in order to fully solve out this partial differential equation. So there are two other ways to do this. One is implicitly through the backward time-centered space and also the Crank-Nicholson method. So the reason we chose this is that it's the least computationally intensive, and it can generate an equation by using the time step that you're currently at and the time step that you're moving forward to in order to estimate the time derivative. So if you see that image on the top right, if you are currently at, say, point j comma n, then the forward time-centered space method would use j comma n and j comma n plus 1 in order to calculate estimate the time derivative. And for the centered space part of this finite difference method, you would use the previous step and the one immediately after. So in this case, modeled by this image is j minus 1 comma n and j plus 1 comma n in order to estimate the space derivative. However, one of the main things that is true about the FTCS method is that it needs a stability condition, which is not required by backward time-centered space or the Crank-Nicholson methods. And this stability condition, the CFL criterion, is represented by this equation here. And I have an example of what happens when the stability condition is met versus when it's not met. So this is a modeling of the susceptible group, so the first compartment, of a graph of the equation we had. It was like cosine of pi x, right? So under the stable conditions, notice that it is almost perfectly modeled by our partial differential equation solver. And you can see this by the convergence check, where all the errors are extremely low, within like 1,000th of an error, right? So this is in comparison with what happens when there are unstable conditions. And the reason that this is occurring is because as the time steps get larger, the FTCS method, its stability conditions kind of break down. And because of that, we now have a situation where you can see that as position of x approaches 1, the graph of our numerical solution just kind of goes crazy, right? It has all these jagged edges. And now we have the results for the rest of the infected groups and the recovered groups. And if you'll notice that these infected and recovered groups, I'll go back to this one real quick. So the infected group is following the pattern of the sign equation, right? In the previous couple slides, I showed you that I of x comma t was a sign function, which is what is this kind of representing. And while both do show extremely low error, there is kind of a larger error on this one compared to the recovered compartment. And this is likely due to the fact that it's used in all three equations, and there is some sort of error with likely the solver that we would need to fix. So kind of in conclusion, what we developed here. So number one is the one-dimensional advection model for understanding contrail mechanics. And we moved on to verifying this using the method of manufactured solutions, or MMS. And this would be able to accurately track contrail movement. And from there, we imposed the FTCS forward time-centered space method along with its stability conditions. And finally, this would be able to predict the rate of contrail formation and dissipation within 1% of its actual values. That was shown by the error charts in the previous couple of slides. However, there are a couple important extensions to this work. So aside from the fact that pretty obviously this was only working in one-dimensional space, this could be moved on to two-dimensional and three-dimensional space, and you just have a lot more compartments and variables for the SAR model. But specifically within this one-dimensional system, remember I told you that it was a constant wind velocity, or advection constant, that we used. However, by implementing the Burger's equation, we could now get the variable wind velocity, and this would model contrails more accurately given the fact that in different positions in space, wind velocities do change quite drastically. And also the next extension is to introduce a kind of contrail feedback system, given the fact that when contrails form, it's in a specific atmosphere of cold and humid air. However, the formation of contrails would change the atmosphere in that specific location. And this makes the areas surrounding that specific contrail more susceptible to further formation. And in order to incorporate this contrail feedback system, we have this equation that incorporates the radiative heating of contrails. So I'd like to thank Mr. Alonso and Dr. Stashire for guiding me with my work on these SAR models and working with me throughout the summer and the rest of the year. And yeah, thank you for listening.
Thank you very much. Let's thank the speaker. Any questions?
I just want to say congratulations. I'm super impressed that you're in high school. Did I read that right?
Yeah.
Awesome.
Thank you.
I mean, very impressive. It's great work.
Yeah, thank you.
It's a big problem, and it's hard to model it.
I have a question. Where are you going for undergrad?
I don't know, but I have applied to Texas A&M, so hopefully.
You've applied?
Yeah.
Very good. Who do you want to work with?
Dr. Dunbar, I was really interested by your talks. So.
You're the winner. Okay, that's very impressive. Let's thank the speaker one more time. We have a break, coffee break, and then it'll followed by the last session. Thank you. Very impressive. So you must have received offers.
Horse FF3.
Hi, everybody. We're going to start in a couple of minutes. If you can take your seats. All right, guys, second warning, we're going to get started soon, like in a minute. All right, so finally we reached the last session of the symposium, session number 8. Gonna chair it. We have some nice talks here before the final fireworks with Daniele's keynotes, right? So I'm going to get started introducing the first note. I just want to warn everybody that I had just a crash of the drive, so I have to go by memory, and I'll ask the presenters to add something that you want if I miss it, okay? So first one is easy. Komal Gupta, she's one of my graduate students at the Space Force Center. She's a second year PhD student working on machine learning, deep learning, AI applied to space situational awareness. Background is in physics and electronics, basically. Anything else you want to add? Turn it up. All right, stage is yours.
Pretty much it. Okay, thank you for the introduction. Hello, everyone. I'm Kamal. I'm going to present my work on physics-informed deep neural operators for XGO angle-only initial orbit determination. Now, that's a lot, but what does that mean? So the motivation for this work comes from the fact that we have an increasing number of objects in cislunar space, which means we need more robust, scalable methods for orbit determination in this region. The challenges here are the fact that the distances are huge, so the measurement noise is much larger. Also, the perturbations make it difficult to use many classical methods which rely on assuming that the orbits are Keplerian. So in this work, we propose a solution based on neural operators. I'll get to what that is in a minute. So neural operator-based models, which we train to map directly from observations to state. So in essence, to solve the OD problem. And we train this model with a physics-based loss function, which learns the dynamics of the region. And then we compare it with classical IOD methods, including Gauss and double R iteration, based on their capability to initialize batch least squares OD algorithm. Now, first thing first, what is a neural operator? So a neural operator, you can think of it as an analog, as analogous to the neural networks. Now, most people know what a neural network is. It learns a mapping from a vector to another vector. Now, on the other hand, neural operators learn mappings from a space of functions to another space of functions. The advantage that gives us is that when we use a neural network, the solution is constrained to the grid that we use while training. On the other hand, when we use neural operators, the output is a function which can, in theory, be evaluated at any point. So we're not tied to a grid. in physics, in anything that involves solving PDEs or ODEs, and you can think of it as something that takes place of an ODE or a PDE solver, yeah, I mean, if you're solving a PDE, for example, the pendulum equation, you can think of the input functions as a forcing term, for example, and then the output functions will be the solutions of the PDE. DeepONet is an architecture. That's the one we use in this work, and it's an architecture that's specially suited for operator learning because it induces a very strong inductive bias for operator learning. Now, how does it do that? It does that by taking in two inputs. One of them is an input of functions, which are discretized over a grid. The other one, which is the trunk input here, is another network that encodes a series of spatiotemporal locations where we want the output to be evaluated. And the output is another set of functions. So the branch input is a set of functions, the output is another set of functions, and the trunk input is where we evaluate the output. In our case, because we want to solve the ODE problem, the branch input is a time series of observations, which in our case is topocentric right ascension and declination. The output functions are the estimated state, or the position and velocity. So 6 components in total. And the trunk input are the times where we want the output state to be calculated. Now, note that we have 6 different outputs for 6 different components of the state. So we have 6 different branch networks, each of which takes the same input and outputs a component of the state when combined with the same output of the trunk network. Now, the original DeepONet paper doesn't really specify what architectures to use in place of these branch and trunk networks. So for our problem, we use a convolutional network for the branch and a simple dense layer for the trunk. Now, we train our model using a synthetic data set that we generate using perturbed two-body dynamics. The perturbation here includes the third-body fix of the sun and the moon. The observation model is topocentric right ascension and declination. We assume that we know, we know the observer. The observer is located at Biosphere, which is situated a little bit outside of Tucson, Arizona. And we assume that all the observations are actually recorded over a period of a single night every 15 minutes. So over 8.5 hours. Now, during our research, we noticed that a single DeepONet model was not really able to capture the entire complex dynamics of the entire cislunar region. So we divide this region into 3 zones. The first one is the region is the green one here, which is the region just above the geostationary belt. The second region is in purple. It goes all the way from 100,000 kilometers to 314,000 kilometers. The third region is the one immediately close to the moon with a radius of 70,000 kilometers. And we train a separate DeepONet model for each of these zones, and we generate a separate data set for each of those models. Now, I mentioned earlier that we use a physics-based loss function, but there is more to that. So we use a compound loss function to train the model, which is a sum of, or a weighted sum, I should say, of regression loss, physics loss, and observation loss. So what are these? Regression loss is the one that is usually used in supervised learning. It anchors the operator to real data. So it makes sure that what we're learning, the states, is realistic, you know. The physics loss, on the other hand, enforces the dynamics, which is very important in this region because of all the perturbations involved. And the third one, the observation loss, ensures that our measurements are consistent with what we provide as input. So the output actually represents a state which is mapped from the input. We trained these models, all three models, in a supervised learning framework using a mini batch gradient descent algorithm with the traditional optimizer Adam and for a fixed number of epochs. Then when we take the best model based on the minimum total validation loss, and it took us around 3.5 hours for training a single model on a single NVIDIA GPU. Now, here onwards, all the results are mentioned in canonical units, so in DU and TU, where 1 DU is the radius of the Earth. Now, before I get to results, we also need a few metrics to evaluate our model. Now, in our case, we use the index of the best fit point, assuming that we don't have the solution. So we use the output to compute observation residuals, and we take the minimum observation residual as a metric to say, okay, this is how good our prediction actually is. Now, the point on the important thing here is that there is an additional step involved after getting the prediction from the DeepOnet, which is that we take the best state with the best. By best, I mean the one with the minimum observation residuals, and then we propagate it back and forth numerically in order to generate a smooth trajectory, which is then used as the IOD solution. Now, looking at the results next, you can see that in all three of our zones that we had, the observation residuals after training are less than a degree. We also forgot to mention that we've also computed the position error at the point with minimum observation residuals, and we plot a histogram of that too. So the position error at the point of minimum observation residual is less than 10% for all three of our zones, and the observation residuals themselves are under a degree for each zone. Now, how do we use this DeepOnet as an IOD method in a pipeline? We get angle-only observations in the form of topocentric right ascension and declination. We pass that through the DeepOnet, which gives us a trajectory. We take the state with the minimum observation residual, propagate it back and forth, generate a smooth IOD solution, use it to initialize batch least squares, and then finally, that gives us an OD solution. Now, some results before I'll show you some plots, but before that, some numbers. So, as I mentioned, quantitative comparison in this case is based on the number of samples for which we get a solution with batch least squares, for which the position error is under a threshold. We set the threshold as 0.1 DU for zones 1 and 2, and 0.25 DU for zone 3. And the percentages that I mentioned in the table here are the number of trajectories, or the percentage of samples in our data set for which we get a solution with error less than the threshold. So we see from this that the proposed DeepOnet model actually provides an initialization for batch least squares to converge within the threshold for as many as 5 to 10% more samples compared to using Gauss or a double R iteration as an initialization. And we also see that the DeepOnet's inference time is actually several orders of magnitude better than both Gauss's method and double R iteration when used as an IOD. Now, so let's see some examples. So these are two samples in zone 1 for which we have good solutions. There are a bunch of cases there. I hope you can see all of them. So we see that for these two samples, all three of our IOD methods, that is DeepOnet, Gauss's method, and double R iteration, provide a good initialization for the trajectory to converge. And then we also have cases in our data set for this zone where one or both of the classical methods fail, and we still have the DeepOnet providing a good IOD solution in that case. The same thing, we see the same thing in zones 2 and 3 as well. So we have cases where all IOD methods provide a good solution, but we also have cases where one or both of the classical methods fail, and the deep net is still able to provide a good solution. Same thing for zone 3, which is the most difficult one because it's closest to the moon, also the most perturbed one, the farthest one, but we still see that we have cases where one of the classical methods fails and the deep net works. So in conclusion, we see that neural operator-based methods actually have the potential to provide an IOD solution in the XGO region for cases where, especially for cases where Gauss and or deep RR iteration methods fail. We also saw that the proposed model can provide an initialization for Batchley squares filter to converge even in the presence of perturbations, which is what we saw in zone 3. And finally, we see that the inference time of the model is several orders of magnitude better, or several orders of magnitude smaller than the computational time for both Gauss's method and RR iteration, which makes it suitable for online applications. In the future, we want to extend this work to use data with longer observation duration, such as using data data from several nights, using observations that are not equally spaced, and using different architectures for branch and trunk networks. That's it. If you have any questions, please let me know.
All right, questions?
Thank you for the presentation. And could you explain a little bit more about your measurement model?
Right.
Any noises?
Yes. So I guess I forgot to mention that part. Right. So the data generation pipeline actually includes adding measurement at the end. So we generate our data by sampling Keplerian orbital elements. Then we propagate it using the perturbed two-body dynamics model that we have. And then we compute the observables from there and add measurement noise to it.
Can I have some extent of the noises you made?
Right. So right now we add about 0.5 arc second to both of the angles both of the observables that we have. So. Yeah.
Mm-hmm. And when you compare your method with the Gauss and the RR, have you used the same dynamic model used in this problem formulation?
Yes. Actually, no, because Gauss, we use both Gauss and RR. Gauss and RR both use Keplerian model. So
based on two-body, right?
Yes. Yeah.
Okay.
Yeah. That's the disadvantage. That's what we're trying to claim, that we can learn the perturbations directly and Keplerian, and we succeed where Keplerian models that assume Keplerian trajectories fail.
Mm-hmm. In my opinion, it would be great to have the same dynamic model and compare the performance together. So I'm developing the Cistruna IOD, so we can collaborate about comparing based on the same observations and compare the performance.
Yeah, I would love to talk to you about that later.
Thank you.
Yeah, this is something that we can definitely do. I just want to also mention that we tested other algorithms. We just published one in Acta Astronautic on XGeo, which is a physics-informed orbit determination on real data, and we show excellent performance on that. So one of the plans is eventually to, this was kind of a first pass, that's why we did it with simulated data, with the capability to explore this for real data. Okay. Any other questions? Nothing? Okay. Oh, so.
Maybe I do not fully understand about the those kind of the estimation, but just wondering, like, instead of using the two-body motion, and then like you use the like zone 1 to 3, and then like near zone 2, can you also assume the dynamic model as the restricted three-body problem, and then like you can use the model as well? Then like you expect that it's gonna well perform?
I guess we can substitute, we can use any dynamical model. I mean, the DeepONet itself doesn't depend on what model you use. We use the perturbed two-body model to generate our data here because we want to claim that, we perform better in case of perturbations. So, but you can swap out, if I understand what you're saying correctly,
like instead
you
of
can
the
swap
generating,
and use, you can use three-body or circular restricted three-body problem, anything, It's not model dependent, so.
All right. Thank you very much.
Right. Let's thank again our speaker. All right, Bahat, where is it? Oh, hey. All right, going by memory, then you can add whatever you can. Okay, or wherever you wish. Bahat, you are a technical lead, right, at the Human Landing System for the Insight team at Johnson Space Center. This is what I remember. Anything else? You want to add?
I forgot my own bio. So I'm a technical lead for the HLS Insight team at Johnson Space Center. I was also the adjunct assistant professor at the same department from 2018 to 2023, I think. And that's it.
All right, thank you.
Thank you.
It's not going. What's happening?
Is this something?
Do you have an HDIN? Any chance? Or? It seems like it's not picking up the signal. It's kind of strange.
Is this the correct call?
Maybe not. Try this one. Other stuff here. You have it? Okay. No, you don't. Is the magic happening? No? Oh, here you go. It's going. Thank you.
Okay. Thank you for the introduction. My name is Bharat, and the topic is regularized universal Lambert solver using Kusenheimer-Stiefel transformation. Now, we would think that by now we have, the astrodynamics community have beaten this problem to death, but if you look at in the literature, every year we see more than one actually research paper on this very problem. So what I'm looking at in this work is on the regularized version of the Lambert solvers. I believe comparatively this line of research has gotten much less attention than the other solvers which are not regularized. I don't think I have to introduce Lambert's problem to this audience. The only thing I would say here is the Lambert's problem is not the only two-body orbital boundary value problem that admits a elegant solution, but it is arguably the most well-known, of course, and also the most widely used two-body orbital boundary value problem in any trajectory design or optimization tool. So my motivation for this work came from this desire to have a very fast, a Lambert solver that can handle all the edge cases and still doesn't lose any numerical precision in computing the velocities. Now it could be a tall order because all the Lambert solvers that I see in the literature have at least some limitations. Different solvers have different limitations, but they would have some. I won't claim today that I have the solution for this, which can handle all the edge cases and very fast, but I think I have improved a few equations for the Lambert transfer time equation for the regularized version of the solvers. Okay, so these are some well-known Lambert solvers in the literature, starting from the classical solutions by Lagrange and Gauss. I think the modern solvers, we can agree that they all start from the very first work, I guess we can say that is from the work of Lancaster and Blanchard with Gooding's modification for generating the initial guess. Then we have Bate, Krayz, Badin, Izzo, Torres, Russell, and then some some new methods for solving this problem using contour integrals or theory of functional connection by Professor Motari here. Only two or maybe two papers on the regularized Lambert solver are in the literature. The very first, I think, work in this area was done by Donald Jesuiski, who actually used to work at GSC, based on his formulation of how to solve orbital boundary value problems in using regularized equation of motion. Krayz actually formulated the Lambert transfer time equation, but he didn't supply the initial guess scheme to form a complete Lambert solver. So that work was done by Torre, I hope I pronounced the name right, Torre and Fentino in 2018, and they used the Lambert's that equation directly from Krayz's work. So yeah, so most solvers which are not regularized, you will see that their velocity reconstruction equations will have some singularities for some edge cases, but and we'll see in the equations in the later slides that the regularized solvers won't have that issue at least. Some basics of the Kustenheimer-Stiefel transformation or KS transformation. I am not including all the equations here. There's a fantastic book from Stiefel and Stiefel who can, with all the details. I'm just showing the very first, the Sundman transformation or one version of Sundman transformation, and the KS transformation that transforms the equations of motion for two-body to a four-dimensional space, and that basically transforms the nonlinear equations into very linear type of equations, and the solution becomes basically the four harmonic oscillators. The last equation on this slide, I don't have a pointer here, the delta T, which is basically the Sundman transformation with the radius magnitude is from the case transformation. By massaging that equation, the last one, we get the Lambert's transfer time equation for the regularized solvers. So in 2019, actually I and Robert Ali, we actually looked at I think 6 or 7 different boundary value problems in the two-body context, and we included Lambert's problem also, but that our focus was not on that particular problem. So this equation that I'm showing here is basically the version that Krayz used in his work, and we just massaged it a little bit. And so this equation has very important properties. First of all, it doesn't have any singularities for any edge cases, except only just one singularity we can see, which is when the eccentric anomaly difference is an integer multiple of 2 pi. So 0 degree transfer is all fine. It's only when the 2 pi, 4 pi, 6 pi, those are the singular cases. Pi, 3 pi, 5 pi are not a problem here. And that is the only singular cases for this equation. And it's a single equation that works for parabolic, elliptical, and hyperbolic cases. I think many of the solvers, they will have singularities for the parabolic case, but they can handle it separately. But this equation actually, the same equation works for all 3 cases, and for the parabolic case, of course, we have an analytical solution, and this equation reduces to a quadratic equation. I have some more properties here on this slide, and I would say yes, for the multi-rev elliptical transfers also, it's very easy to handle using this equation. You just bound the independent variable z in this case between some specific bounds for the multi-revs, and that's all you have to do to get the solution to multi-rev elliptical transfers. The last property is important here. It's not a property, but it's an observation that this particular version of this regularized transfer time equation, it is dependent on 5 different stump functions. And it's not very difficult to compute stem functions, but we can do it. We have recursive relations. So we can compute C0 and C1, the first two functions, using trigonometric or hyperbolic functions, and then rest of them we can generate using recursive relations. But for implementation, these recursive relations are actually, in modern computers, they actually slow down the whole process, because you can't use much parallelization in the CPUs, basically. So what basically I did was I massaged the equations quite a lot. So after many hours of using stem function identities and algebra, this was the final equation that I settled on. So this equation has all the good properties that we saw in the previous one, which was my starting point, and the addition. But the benefit in this equation is much more simplified. So it only depends on two the two basic stem functions, C0 and C1. So the previous equation, if you remember, it was that required computation of 5 stem functions. This is only C0 and C1, so only 2, and all the other properties remain the same. The singularity wise, again, the only singularities were only for the 2 pi and 4 pi and 6 pi, those kind of transfers, but the 0 degree transfer is all fine. So this was the transfer time equation. If I go to the next slide, then I'm showing you the velocity reconstruction equations. And the fantastic thing here is, even for the pi transfer cases, the collinear transfer where the orbital plane is not defined, even then these equations are actually still work. Even though you don't know the plane, it can be any arbitrary plane. These equations will give you a solution. So that's I think that may be the only or the regular solvers which have this property. And of course, because they're regularized, you don't see any of the radius variables in the denominator, so they don't lose accuracy if those transfers come close to the central body. I am not showing in this slide the derivatives of the transfer time equation, because we need those for implementing a complete solver. So what I'm showing here is if t is the scale time, which is the function of the independent variable z, all its the next 3 derivatives, I was able to express them again only in the 2 stem functions, C0 and C1, and they have the same properties as the transfer time equation. There are no singularities except for that one case. Yeah. So some results for the. So I actually this work is actually still in progress. I still have to come up with a robust initial guess scheme for this solver. But what I did was, for comparing how lightweight these equation is compared to the more standard solvers like Goding and the recent one, McElreath, I think he's a Margie's student. Recently, Margie's research group presented this Lambert solver, which uses the Harrick's universal functions and a very lightweight equation. I think it depends on 4 universal functions, but the equations are very simple. So I compared the computational burden of solving the transfer time equation and the 3 derivatives with the Goding's method and the McElreath's method for 2 different types of transfer, elliptic and hyperbolic. For elliptic transfer, the eccentricity was very high. I did like 1 million computations where I changed the eccentric anomaly from 0.01 degrees to 1,000 degrees. So yeah, and the results are here. All the numbers for the computation time are relative to Goding's method. So for the elliptical case, the proposed the transfer time equation and the derivatives, they use 30% less time than the Goding's method. The McElreath solver actually was more efficient than the proposed method and the Goding's method. But for the hyperbolic case, the McElreath solver was more than 4 times more computationally expensive compared to Gooding's method. And the proposed method, the regularized solver, was only 9% more. It has 9% more. It took 9% more time. So more balanced, I would say more balanced performance from the proposed, the regularized equations. So I believe the next slide is the last one, is the conclusion. So to summarize, I presented a simplified equation for the regularized Lambert solvers, which are only dependent on only the two basic stem functions. These the new equations have no singular cases except for just one case of 2 pi or the integer multiple of 2 pi transfers. The 0-degree transfer again is all fine. The velocity reconstruction equations have no singularity at all. The forward work, of course, is the coming up with a robust initial guess scheme and comprehensive testing against the more state-of-the-art solvers. And the results we just saw, it has a much more balanced performance compared to the standard Gooding's method, and also compared to the more recent, the Michael-Reith solver, which also uses universal functions. It is much more computationally efficient, at least in case of hyperbolic transfers. With that, I conclude my presentation. Thank you for your attention.
All right, thank you. Questions?
Thank you for the talk. Just wondering, like, the process might be related to the root finding process, and then, like, currently, how do you get the initial guess for the problem?
Yeah, that was the forward work.
Right.
So far, I'm not using initial guess, any initial guess formula to start the iterations. The computational time that I'm showing is not for doing the iterations. It's only for only for evaluating the transfer time equations and the 3 derivative equations.
Okay.
And over and over again.
Mm-hmm.
That's it.
All right. Thank you.
Any other questions?
Thanks, Bharat. Yeah, no, I'm definitely interested in chatting a bit more offline about this. It's a little misleading to say that pretty much all those other ones you listed are regularized in the time sense, but in the state they're not. And so I think that's one minor correction, because they all pretty much rely on the Sunman transformation.
Yeah. So velocity reconstruction equations are not. They are the ones which mostly have singularity issues, right? When or not singularity, I mean they're not regular. So yeah, transfer time equation, yes, those are regular. Yeah.
And then on the Gooding, the standard algorithm that folks compare with Gooding is the one that he posted, like, typeset Fortran from some journal paper a long time ago. So did you port that to MATLAB, or what was the devil's really in the details when you compare these, like, timing problems?
Yeah, so I actually didn't implement the Gooding's algorithm myself. There is a MATLAB code available online by this person. The link is here.
Yeah, okay.
And the reason I wanted to compare with MATLAB, because when you implement in Fortran or something these compiled languages, the compiler options you use, there are so many other variables that can change the performance, one way or the other. So that's why MATLAB is, I think, a better way to compare these algorithms, where you can only compare the algorithms and not the implementation that much. So that's why I chose MATLAB platform to compare the equation that I presented and the other ones.
Yeah.
And the Margie's research group solver is in MATLAB also.
But I do think that the other question about the initial guess is not trivial, and then the number of iterations is not trivial. But I've worked quite hard on those edge cases to, using series and other things to get better numerics, and so I applaud just a cleaner formula that doesn't have a divide by R. Although usually the edge cases are truly edge, and that they're not usually interesting except for academically. They're really, eccentricity of 100,000 kind of problems.
I think I have seen your MATLAB codes. I think is online, right? The only similar case I think in case of your solver that I saw was when the terminal position vectors have the same magnitude. That was, I thought, it didn't work at least for me on my computer.
Yeah, we should chat. I think when the terminal velocity is 0, that's a problem.
Okay.
But you have other issues if that's going on. Thank you.
Yeah, thanks.
Any other questions? No? All right. Thank you very much. Bye-bye. Ben, how you doing? What's that? Okay. All right. So why don't you set it up? Ben completed a PhD under Dr. Mortari 2010 when he created star ND, star identification algorithm, which has totally improved the performance of a star identification algorithms over the state-of-the-art algorithms. Currently, he is developing publisher tools for SingAccord, a music notation patented for non-musicians to sing along with the new songs without formal training, specifically designed for church congregations. All right. Most recently, and here I read quote here, so this is something you wrote, just to be clear. Ben completed 4 years as a lead iOS developer at Truth Social, helping President Trump to save free speech, where he leads the iOS team to build a social media app from scratch in 3.5 months. That's your quote, right?
It was a rush, yeah.
That's your quote. All right. Thank you.
Howdy. There it goes. Osama posted his photo with his jersey, so I was like, I went through my photos last night and dug one out. And, they say the measure of a good teacher is not in how many students they've educated, but in how many students they've inspired. And I still remember the first time I heard a presentation for Dr. Mortari, and I remember sitting in his stellar navigation class, and every time he presented something, it was this joy that was, for lack of a better word, infectious. And those ideas and these connections that he made with mathematicians and with other other disciplines of the hope of what we could accomplish if we kept going and we kept connecting things, that was infectious for me. And these ideas get in my brain and they rattle around. And so I just wanted to say thank you, not just for the education, which you've done a superb job of, but for the inspiration. So thank you very much. And I think this week we've seen a bunch of people who've been inspired by you. And it's been some great work. I'm going to jump back in time. I don't think we have a lot of people in Star ID in here, back when TFC meant the flower constellations. It's been a while. But just to reorient everyone to Star ID, when we do the Star ID step, we're going to take some sort of geometrical measurements from the unit vectors to the stars in the spacecraft reference frame. We're going to calculate some sort of parameters from those. We're going to do a database search. The database is going to give us some possible matches. Some of those are not going to be in the error bounds, and we can do a filter step and discard those. And then we get our our body vectors. The identity of the stars from which we get our inertial vectors. And back in 2010, my dissertation research was, I called it Star ND, and that was an algorithm that used a star in the image with the nearest 3 stars to it, which I then used 2 functions to calculate 3 parameters, and I then did a multi-dimensional bin search, and that was asymptotically faster than what had been published before. However, because it used the nearest 3 stars, there was some time where you had to measure the distance to the other stars in the image, and then you had to sort them. And that meant that the dominant amount of time that you spent doing this star ID algorithm, as you can see from this graph here, was actually measuring the distances and then sorting the stars. And since then, I have wanted a solution, been inspired by a solution, maybe bugged to get a solution that didn't have to do that. If instead of using a nearest stars approach, I had a pick any stars approach, so I could pick any stars in the image, I don't have to sort them, then it could have several other beneficial features. Be more resilient to false stars due to things like radiation, thermal noise, angular motion. It could use databases with smaller fields of views, and it could eliminate that timing. The downside of pick any stars algorithms is that the databases turn out to be huge. With a nearest star approach, you can have a database that's linear in the number of stars in your catalog. With a pick any stars, it's combinatoric. And so I'm going to show you a pick any stars approach now that gets performance even better than StarND did. In order to do that, I'm still going to use a multidimensional bin search. Bin searches are theoretically the fastest kind of range search that you could do, but your data set has to have special criteria in order for that to work. It has to have nice minimum and maximum bounds, which I'm sort of drawing here with this box, and then throughout that range between your minimums and maximums, your data points need to be nearly uniformly distributed. Now, I've been having PTSD flashbacks to Dr. Junkins asking me during my dissertation defense to find nearly uniformly distributed, but it sort of doesn't matter because as your databases get larger and larger and larger, the difference between the performance of this and the performance of an algorithm that does depend on the size of whose search time does depend on the size of the database is going to be huge, and you can do a very poor job of getting a uniform distribution and you're still way better off. But in general, you want to have one data point per bin. It's okay if some of the bins, and these are BIN bins, not BEN bins. It's fine if a couple of the bins have like 2 data points in them or 3 data points in them. That's fine in the end. But you don't want to have any giant clumps of data because the way the search is going to work is look at these dotted lines here. This is like an error range, and the bin search is going to find all of the items in those bins. So you don't want a clump of data into just a few of the bins. You want to keep it spread out. And so you may ask, well, wait a minute, can't I, if I have data that's not uniformly distributed, can't I just know what the distribution is and then divide by the distribution and then I have uniformly distributed data? And it is not going to let you get away with that. Because what happens is if you start dividing like that, your error ranges are going to explode. So here, these dotted red lines here are an example of an error bound that's now grown to cover many different bins. And when you go in and do that database search, it's going to pull out everything in all of these bins. And now your performance guarantee that it was going to be really fast is lost because it's pulling out all of these answers in all of these bins that aren't even within, they're not even within your error ranges, really. And there were some rare cases with StarND, because I used normalized parameters, where that error would get divided by a very small measurement value. And in very rare cases, it would get really big and it would spike, and you'd get long execution times. Now, those long execution times were still as fast as the next competing algorithm when it was doing its best. So, you still want to go with StarND, but I would really love to get rid of those. I'd really love to get rid of those spikes. But the thing that has inspired me the most, the thing that has stuck with me over the last 15 years and wish I had a better solution, was that theoretically I was able to show that the number of independent parameters, which is the key to getting your uniform distribution of data, theoretically should have been 2s minus 3. And StarND only had 2s minus 5. And this 2s minus 3 theoretical best has stuck with me, and every couple of years I just pull out my laptop and start trying to figure out where I'm going to get those parameters again. So here we go. Let's do it. How many stars should we have in our pattern? The more stars you have in your pattern, the size of your database explodes combinatorically, so you want to have fewer stars. The more stars you have in your pattern, the probability of a mismatch plummets, so you want to have more stars in your pattern. So how many am I going to take? I'm going to take 3. This is a very, very carefully selected plot. Don't try to find this on your own. I had to fiddle with the settings to make it look this good. If you have a probability of finding one item in your database, that's not the right answer. That's probably a wrong answer. It means it's just randomly there's going to be a wrong answer sitting there. If you go with 2 stars in your pattern for these carefully selected parameters, you're probably pulling out hundreds of answers out of your database. And this is what drove the time in Pyramid, was multiple searches of pairs that then had to be cross-correlated. And that's the benefit of going with star and D, was we didn't have to do that. But if you go with something like 4 stars, the probability is like way, way, way down here. But 3 stars is a nice little equilibrium, just under 1. Right? And you can fiddle with this and make it go above and below depending on your field of view and that sort of thing. But I'm going to go with 3 stars because it rides that optimum point where I'm probably not pulling wrong answers out of my database, but I'm able to keep the size of my database as low as possible. So what is my star pattern? I'm going to pick 3 stars. I can order 3 stars in 6 ways. So my canonicalization is I'm going to pick star number 3, such the inner star angle between 1 and 2 is the largest of the 3 inner star angles. I am then going to always represent them in the right-handed sense. So if star 3 were to lie down here, then I would swap my identities of 1 and 2 so that it's always up here. And that means star 3 always lies within this blue area relative to what I'm calling stars 1 and 2. Then I'm going to do feature extraction. Just for time and for the easiness of saying things, I'm going to call these theta and x and y. There's some small angle assumptions that go into that. So if you're trying to code this, pay attention to these vector functions over here. These are the actual parameters that I'm numerically using. But I'm going to call the parameters theta, approximately the inner star distance between these stars, and then orthogonal x and y. And ask the question, are these parameters uniformly distributed across the possible range? So here is a normalized display of the data entries in a 1,000 star database. And as you can see, across this theoretical range, they are very uniformly distributed. That's very good. You get something like this and you go, yay, we found it. But the problem with this is that it's normalized, and I'll get to that in another couple of slides. Moving to a larger database that's so big you can't see the individual data points. Here's a histogram of a 7,000 star database, and you can see that the top surface of this histogram is very flat, and again, that's telling me the distribution is very uniform. There's a couple little nubs here at the corners that are possibly maybe related to binary star systems, but basically the height of those nubs is low enough that I kind of don't care. Again, it doesn't have to be perfectly uniformly distributed. It just has to be nearly. And the height of those is small enough, it doesn't matter. But those were normalized views of the database, meaning I have divided the x and y coordinates by that theta value. And I don't want to do that because that dividing by that theta value when theta gets small is what makes the error ranges explode, which is what makes the search time explode. And here's an example of one of the error parameter plots from star ND where that's what happened. Normally, the error parameter is very, very small, and then right here in this corner, it would spike up. And so I want to avoid those spikes. So I got to ask the question, is it still uniformly distributed when it's not normalized? So I'm going to take this x and y plane and rotate around to the back and take a look at that. And what you can see is that as the theta goes from these large values up here to these small values down there, the whole three-dimensional volume just sort of shrinks into this corner. This is very not uniformly distributed. It is very not rectilinear. So it's not a good mapping to a multi-dimensional bin search, and yet somehow we're going to make that work. In particular, if I look at the distribution of database entries along the theta axis, what I see is not just theta, which would be bad, it's not just theta squared, which would be worse, it's theta cubed. I mean, this is a very, very highly not uniform distribution along the theta axis. And so I can't just stop here and do a three-dimensional bin search and get good results out of this. Instead, and I don't really have time to go into why you wouldn't do a whole bunch of other things that some people would think to try or have tried. I only have time really to go into what I'm going to do. And that is I'm going to divide up the theta range into equal slices. Now each one of those slices is going to have, a cubic number of entries in them. But instead of doing a three-dimensional database, I'm going to do a one-dimensional database in theta, which will then map me to a sequence of two-dimensional databases. Each one of those two-dimensional databases is going to be a slice in X and Y. And that database will be independent from all the others. So if it has tons of items in it, it will be able to divide up X and Y into lots of little cells, and it will easily distinguish the entries in the database based on the X and Y. But down here, where theta is small, the theta is going to be doing most of the lifting in differentiating those entries in the database. And for instance, down here in this last one, there's something like one entry in that. I mean, that's not much in X and Y, but in theta, that's really good database entry discrimination. So again, for time, I just have to sort of skip directly to the numerical results. Here's sort of the results out of my dissertation with a mean for star ND being around 4,100 clock cycles. With this approach, with I guess I'm calling it star slice. I hadn't come up with a good name. The mean is around 251 clock cycles. And remember, star ND is still doing the same kind of three-dimensional bin search that this new approach is doing. But because it has to measure the distances between all those stars and sort by them, it's got all this extra time that's in there that I just skip it. I am assuming in this work, I'm just doing a 3-star pattern, and I'm assuming in this work that you're going to get to numerical precisions where you need to have identified 4 stars in order to have the correct statistical probability that you don't have a mismatch. And so essentially, I'm just going to stitch these together. I'm going to do 2 3-star searches, 2 of the stars will be shared, and I'm going to confirm those. But the key is that each one of these 3-star searches is only pulling out 1 entry. It's only finding the correct answer. So I've got my statistics set where I'm probably only getting that 1 entry coming out of there. And in the rare case where I get 2, I can just double check with the other search and make sure they're correct. So I'm still can approach the statistical certainties of 4 stars, but doing 2 3-star searches, which pushes me up to 500 clock cycles or so. But again, that's comparing to like a few thousand, that's still good. One of the benefits here, and I won't go into the complete algorithm, is that you can reject false stars more easily than with star ND. With star ND, every time you conjectured that your first star was a false star, you then had to recalculate the distances to all the other stars in the image and resort them. And now you can skip that. And so you can take more of a pyramid approach where you can more easily iterate through the possibilities of which one of those stars is a false star. So it dramatically reduces the amount of time it takes you to iterate through the false star possibilities, where star ND would tend to increase execution time. Now, turning over to the database size, the problem with this is the database grows so massively huge. With star ND, because we only had 1 entry per star, that grew linearly, and I identified some edge case scenarios and errors where you could add additional incorrect answers into the database so that at runtime you got the right answers, and that would add, in the worst case, about 20% to the size of the database. But it was 20% linearly in the number of stars. With any triple of stars, you've got this massive increase. That's the number of stars in your database times effectively the square of the number of stars in your field of view. So that grows huge. And so one of the advantages of using a pick any stars approach is that you can search the literature for other papers about different aspects of star ID, and you can then sort of pick things that were in other papers and sort of attach them onto here. And so some of the existing literature already covers how to do things like cull dim stars from your database in regions of the sky that are densely packed. I'm not going to go into the details of how to do that. I'm only going to ask the question, if we did that, would we still have a uniformly distributed database for this approach? And so I did some testing with that, and yes, that sure does look pretty uniformly distributed to me. And with that, I'll put my concluding graphs back on the screen and ask if there's any questions.
Thank you very much. Questions?
Good work, Ben. So I'm not an expert in this field, but just so when you're talking about star ID, we mean star identification, right?
Yeah.
So basically, so what you did is different than using a star catalog. Like, do you compare with you said data? You have a data. So a data of stars. So is it a star catalog or what is it? How do you after looking at a star, how do you identify how it's going to be different from using a star catalog?
So if I take the phrase star catalog to mean a list of the stars and their directions, then my process is take for every star, find all of the stars that could be, find all of the star triples that could be in the field of view at the same time, calculate these 3 parameters that I identified for that triple, and then insert that into these bin search databases. So I would calculate the theta value of that star triple, and then I'd put that in a box. I do that for every star in the database, and then for every star triple in the database, and then for each of these bins in the theta dimension, I would then come back and build a 2-dimensional bin search for the x and y values of that star triple. And so I'm directly searching the database I'm directly searching the bin database. And then that database will have in it the IDs of the stars in the catalog. So then I can go back to the catalog and extract out the unit vectors in the inertial frame.
Okay, I didn't get a star-ND. What is? I didn't get that one.
Oh, star in ND is just the name that I gave to the method that I presented in my dissertation. It had a property where you could take those 2 equations and apply it to an arbitrarily large number of stars in the pattern. So I started with 4 stars, but you could add a 5th star, and you could take those same 2 functions, apply it to the 5th star, and generate 2 more parameters. And so instead of calling it star 4D, I called it star ND because you could have n number of dimensions.
Okay, thank you.
Any other questions? All right, let's thank again our speakers. Next is Tom. All right, while you set up, if I remember correctly, Tom, Aaron's, you are a 3rd-year PhD students for the laser here at Texas A&M, laser lab at Texas A&M, under Professor Maggi and Jenkins together. Anything else you want to add? You're good.
Okay. So I'm Thomas Ahrens. I'm one of Dr. Maggi and Dr. Duncan's PhD students, and we are interested in studying what we're going to call the norm-dependent wobble problem, and present some solutions to it. This is obviously motivated by a lot of Dr. Mortari's numerous papers on the subject. So just to present the problem briefly, for those who haven't seen it, in 1965, Grace Schwabe posed the following problem. Given a set of n measured unit vectors, b1 through bn, and their corresponding reference unit vectors, r1 through rn, related through this orthogonal matrix A, how do you determine the rotation matrix which minimizes the least square cost function? And this is difficult because you have to require that this matrix A is orthogonal, and it has a determinant of 1. And this has been solved in lots of ways, and there are lots of different attitude parameterizations to use for this. The most common methods are the quaternions, the classical Rodriguez parameters, the modified Rodriguez parameters. And there are a lot of popular methods for solving this. Probably the most famous first method for solving this was Davenport's Q method, where he showed that this is equivalent to solving a maximum eigenvalue problem. Then the Quest method by Schuster. Markley presented a method that uses the singular value decomposition and the foam method. And then Dr. Mortari has several methods as well, which give computational benefits, or in other cases, sort of other sorts of optimality, so to speak. So we sort of wanted to study this question. The wobble problem typically assumes Gaussian noise, or we just blindly use the WABA solutions in the case of non-Gaussian noise. And the question we want to ask is this optimal? Especially in the presence of new imagers, right? As we have advanced photodetectors now. Essentially, we measure Gaussian point spread functions. And in modern cameras, when we have these complex lenses and optical arrangements, such as planoptic cameras, we measure not only intensity but also direction of the light, or orthophoto lenses. How do you then characterize those noises? And it turns out you can actually tune these PSFs as well, which creates an even bigger problem when you no longer have this Gaussian noise. So we need some sort of new error models for these image formations where we have to determine the pose and attitude. So a few others have proposed a sort of generalization of the WABA problem. Schuster made a generalization where you take direction, measurements, and attitudes. And Sayaki added some set of unknown angular rates and showed that you could actually parameterize the solution in terms of the initial angular rates as a way to get torque-free motion. So what we're going to do is take a maximum likelihood approach instead and consider Gaussian, Laplace, and uniform distributions. And this leads to what we're going to call the norm-dependent WABA problem, where you're now given that same set of vectors, but instead they're measured here with an additive noise, nu j. And we want to now determine the rotation matrix, which instead of minimizing the least squared cost, minimizes the p norm cost function. And again, we still have the orthogonality constraint. So just quickly on maximum likelihood estimation, we generally want to obtain some estimate where we have a unknown quantity or set of quantities that maximize observing the data. And we construct the likelihood function, which is essentially the joint distribution of our probability y tilde, our measured quantities, conditioned on some values x. And the requirements for the maximum are just the necessary and sufficient conditions. And then you can rewrite this just in typical optimization framework where you want to minimize some cost function j of x hat. And that's how you can sort of transform the maximum likelihood problem into a optimization problem instead. Now in the case of attitude determination, in the sort of perfect measurement world, our measurements are related through this matrix A. But when we consider the additive noise model, where our measurements are the truth plus some value nu j, we then get something of this form, where now the maximum likelihood estimation for the rotation matrix, we just plug this in to our cost function, and we need to minimize this cost j, which is the sum of the negative log probabilities. And we're considering here the three different distributions. Here I'm just showing the sort of 1D slices. So on the left is the Gaussian distribution. This is going to be a 3D distribution, but it's actually projected onto the tangent plane at the point of observation. The Laplace distribution, which is essentially two exponentials stitched together, and then finally the uniform distribution. So starting with the Gaussian, like I said, this is not exactly a 3D Gaussian. It's a Gaussian which projects onto the tangent plane at the point of observation, ARJ. And this noise is then going to be orthogonal to that point, which gives this covariance matrix. And then when you just go ahead and plug into your cost function, you get this term here. And then finally, in a minimization problem, we can drop any constants. And we find that we get back the least squares cost function, which is exactly what WABA originally proposed. So the WABA problem with weights being the inverse of the covariance is actually a maximum likelihood estimator for Gaussian noise. Now if we switch to the Laplace distribution instead, we have this 3D distribution. Again, we just plug into our negative log likelihood, which we need to maximize in order to be a maximum likelihood estimate. And now, dropping the constant terms, we find that the maximum likelihood estimator for the Laplace distribution is in fact the one norm cost function, where here beta is essentially what is called a scale parameter for the Laplace distribution. And then finally, for the uniform distribution, this is a little bit trickier. The probability is going to be 0 if we don't observe something within our bounds. So if this condition is met, again, it's just the negative log likelihood. But this does not contain a rotation matrix A. So instead, the maximum likelihood estimate is found on minimizing the maximum residual, which essentially enforces the distribution bounds. So you try to minimize that box as much as possible. And this leads to the infinity norm cost function. So what we found is that for the Gaussian, you get back the WABA problem, which is the least squares case. For the Laplace distribution, you get the one norm problem. And then for the uniform distribution, you get the infinity norm problem. But we still have this orthogonality constraint to deal with. And what are we going to do about that? So Arthur Cayley found this very elegant transformation between skew-symmetric matrices and special orthogonal matrices or rotation matrices related as such. And in typical attitude representations, we choose that skew-symmetric matrix to be the cross-product matrix of the CRP or Gibbs vector. And you can rewrite this in terms of the principal rotation angle. And this is what that orthogonal rotation matrix then looks like. Dr. Maggi is a fan of the Gibbs vector, as is proved by him placing a pen on Gibbs' tomb, which is apparently a thing. And then remarkably, when you plug this in and you take A transpose A, you get that this is satisfied trivially for any choice of the Gibbs vector. So we've removed this orthogonality constraint entirely. But now we have a cost function in terms of those, the Cayley transform. So we rewrite that cost term nu j in terms of our Gibbs vector. And if we define these sum and difference matrices, and then this new variable nu prime, which is the scaled noise nu, we get a linear function of the parameters. This does beg the question, though, is the maximum likelihood estimate for nu j the same as the maximum likelihood estimate for nu j prime? And the answer to this is no, as most of you can probably see. It's actually scaled by 1 plus g tilde. So we can't actually directly solve that problem, but we're going to instead show numerically that we can actually still get what I'm going to call the best available maximum likelihood estimate with this linearized version of the rotation matrix. So if we go back to our Gaussian distribution, and we have now nu prime instead of nu, we get, again, defining these summation and difference matrices. We get that the Gibbs vector is actually just the standard weighted least squares solution. And this is actually Dr. Mortari's solution in the optimal linear attitude estimator method. And the nice thing about this is that you can compute the Gibbs vector directly just by inverting a 3x3 matrix, this S transpose WS, and it's easy to get that Gibbs vector. Now in the case of the Laplace distribution, we have the one norm again. So what we're going to do is we're going to introduce non-negative slack variables, which then introduce additional constraints. And this results in a linear programming problem where we're trying to minimize some C transpose A subject to the inequality constraint. And then finally, for the uniform distribution, we have the infinity norm. And we're going to do a similar thing, but instead of requiring a vector of slack variables, we just need one non-negative slack variable. And again, this leads to a linear program, but now it's a different one. where we have slightly less variables to solve for. So to summarize these linear estimators can all be solved, and we can be guaranteed solution to them. In the Gaussian case, we just have those three variables which we solve for with the matrix inversion with the weighted least squares. In the Laplace case, we have 3 plus 3n slack variables and 6n constraints. This is a linear program. In the uniform case, we have 3 plus just n slack variables and 6n constraints. Again, this is a linear program. So we're guaranteed solutions to all of these. And what we're going to do is through Monte Carlo trials, we can show that these linearized estimates actually do maximize the likelihood when compared to the other methods. And we're going to do that by generating Gaussian, Laplace, and uniform noise of various scales for a different number of observations. So here's the Gaussian results. These are the errors in the rotation angle for 2, 3, 5, and 10 vectors. And these aren't too interesting to look at, but if you go to the likelihood function, you can see that here I'm also comparing Quest and Ole do, in fact, minimize this cost or maximize the likelihood. And that's fairly easy to see compared to the Laplace, the L1, and the uniform, the infinity norm cost functions. If we then go to the Laplace case, here again we have the rotation angle error and then the likelihood. And we see that pretty much overall the Laplace L1 cost is in fact the maximum likelihood, except for this one little case here, which as the errors go to 0, sort of all of these cases converge. So as you increase the number of trials, you would expect this to be consistent. And then finally, for the uniform distribution, we see that the infinity norm is in fact the maximum likelihood estimator. So in conclusion, when we have Gaussian, Laplace, or uniform norm distributions, we get the least square, which is the wobble problem, the one norm or the infinity norm problem in the maximum likelihood approach. And the Cayley transform is quite beautiful in that it allows us to remove this orthogonality constraint, but sort of at the cost of requiring this linearization of the cost function. But we do see that the linearized solutions do still provide the sort of best maximum likelihood when compared to the other norm solutions. And there are a few things we still want to do with this. We can quantify or sort of model the error between these linearized solutions and the actual true maximum likelihood estimator. We also have not done any covariance analysis yet, which is quite easy to do. And then also the multiplicative measurement model, which is actually the correct measurement model to use here if you're measuring things on the sphere. And then finally, you can also do maximum a posteriori estimation, which is equivalent in this case to the uniform prior. So with that, I'll stop and take any questions.
Thank you. All right, questions?
Yeah, very nice presentation, and I think the use of the Cayley transform is very elegant, but my question has to do with before you employ the Cayley transform, we know that the Gaussian case gives rise to an orthogonal Percustes problem for the optimal attitude.
Correct.
Can you say something about the Laplace and uniform cases? Does it give something similar to an orthogonal Percustes problem?
Yeah, not that we've seen so far. Yeah, I'd probably need to do a deeper literature review on that, but yeah.
Any other questions? No? All right. Let's thank our speakers. Thank you. Kapil? Where is Kapil? All right, Kapil, come over. Yeah. All right, so here we have a team, right? Ready to get going, and so you're all undergrads here, engineering at Texas A&M. Why don't you introduce yourself and your colleagues? Turn it up. Turn it on. I mean.
All right. Hi, everybody. My name is Ansh Patel. I'm currently a sophomore at Aerospace Engineering.
Howdy, everybody. I'm Vedant, and I'm a freshman general engineering major here at Texas A&M.
Howdy, everyone. My name is Kieran. I'm a general engineering freshman at Texas A&M, and today,
hold on. There you go.
And today we present our study on optimal trajectories and fuel efficiency for Earth to Mars missions, particularly within the context of an emerging lunar economy. We also extend the study by including machine learning techniques to enhance mission planning.
And real quick, I'd like to thank Isabel and Mortaz as well for their contributions. So we focus on the preliminary analysis of two main orbital architectures. One is a direct LEO to LMO architecture with a tug refuel in LEO. And the second one is a LEO to LLO, or low lunar orbit, to LMO with a tug refuel in LEO and LLO. The purpose of the paper is to determine the optimal Earth to Mars orbital architecture for a Starship class vehicle. We use classical orbital analysis to come up with the delta V for each transfer. We then transfer that delta V to propellant capacity and then convert that into the regolith needed to produce the oxygen in ISRU, given that the Starship uses methane and oxygen for propulsion systems. The key steps we use is using a neural operator to predict trajectories for each transfer, and then a preliminary orbital analysis was used, again, to determine delta V and propellant use. So the challenge of space travel has always been about propellant capacity. Our goal of this paper is to decrease the amount of propellant capacity needed for a Starship when taking off in order to increase its propellant capacity, its payload capacity, to help with supporting habitat structures, scientific equipment, as well as support development for long-term interplanetary travel. By looking at an overall architecture rather than individual components, we can figure out an efficient and optimal orbital architecture for long-term interplanetary travel for a Starship class vehicle. Given that we are using preliminary orbital analysis, such as patch Collins approximation, the Hohmann transfer, along with the rocket equation, we make several assumptions along with that to make approximations, which then limit the scope of our study as well. So we only focus on in-orbit transfers, and we do not focus on liftoff or landing as well on the planets. As well as that, we also remove many constraining factors such as rendezvous maneuvers, the practicality of cryogenic oxygen delivery in orbit, along with timing constraints with launch windows. Again, our scope of study is preliminary and a first-order analysis, so further analysis needs to be taken and conducted to make a conclusive result from our study.
So to start, we first needed to calculate minimum delta V values for 3 different trajectories. The first one was low Earth orbit to low lunar orbit. The second trajectory was low Earth orbit to low Martian orbit. And the third trajectory was low lunar orbit to low Martian orbit. For the first trajectory, we iterated through apoapsis distances and intercept angles. For the next two trajectories, we iterated through hyperbolic excess velocities, and then similarly intercept angles. So this is a schematic of the Earth to Moon situation. You could see the apoapsis distance. Note that in this diagram, it's at an anomaly of 180 degrees, but this doesn't necessarily have to be true. This is a similar diagram for the hyperbolic excess after Earth to Mars. And this is another diagram from Moon to Mars. So in Python, we iterated through a bunch of different values for the 2 parameters for each trajectory. And as you can imagine, this creates a coarse grid of values. The optimal minimum delta V we find would need to be found more rigorously through an optimization algorithm. So we use differential evolution here to find the true minimum. For example, if we iterate through 50 apoapsis distances and 50 intercept angles, we get a maximum of 2,500 points. Now, as you can imagine, since we're iterating through such a wide range, not all of these trajectories are valid. So we end up with even less points. This isn't rigorous, which is why we use this differential evolution algorithm and then we seed the algorithm with the optimal point we found in the coarse resolution solution, and then this algorithm would find the true minimum. So this is the minimum delta V we found from Earth to Moon. This is the minimum we found from Earth to Mars. And so for Moon and Mars, we actually found two solutions. The first minimum we found that you could see here is the mathematical minimum of our model. But as you could see, this is extremely low. And a potential explanation for this is the fact that we didn't account for time of flight, which is another limitation of our study. However, due to the extreme sensitivity of this value in minor orbital trajectory conditions initially, we took a more realistic minimum from our coarse resolution grid of 513. Now, one of the limitations of this method is that it's exhaustive and it takes a lot of time. A parameter sweep to find iterating through apoapsis distances and intercept angles to find minimum delta V and perigee values is not efficient at all. So, and due to the patched conic, since it's hard to solve it in the reverse direction to solve the final to the initial conditions, I created a neural network to fix this issue. So we generated many apoapsis distances and intercept angles and found the delta V's associated with those flight conditions, and then trained the network on the reverse. So we input the delta V and then the perigee radius, and then we get the initial flight conditions. So to train this model, we trained all our models over 200 epochs. For this one in particular, we trained it with mini batch gradient descent. So it was 16 batches per epoch and 512 data points per batch. This is a schematic of our network. You could see we have an input of 2 nodes, 2 hidden layers, each of 64 nodes, and then an output of 2 nodes. These are the loss curves for this model. You could see that the error is quite small. So one limitation of the neural network is you could only query trajectory by trajectory. To solve this, we used an operator to get around this. And effectively, what an operator would do is you'd be able to put in the moon conditions, the orbital radius, the radius of the moon itself, and then the mass of the moon too, and then you'd get all possible trajectories from Earth to Moon. So for a Fourier neural operator, which is the model we used, you have to input a square grid. Now, as I said before, to generate data, we iterated through apoapsis distance and intercept angle, and that's square, because if we iterate through 50 apoapsis distances and 50 intercept angles, we get a maximum of 2,500 points. But not all of those trajectories are valid, and our data generation filters out the invalid trajectories. So really, we're left with an irregular grid. This is problematic for this model, which is why we had to interpolate the data onto a square grid and then input it into the model. So these are our loss curves for this model. You could see that the error is still quite low, and here it predicts every single trajectory. Now, the limitation, as I said, for the Fourier neural operator was that you needed a square grid to input. So the deep network operator is another method we can use to get around this. It doesn't require a square grid, so even if our input data is irregular, it will still take that. And the advantage is, there's no interpolation error, and we have a branch network and a trunk network, so effectively 2 neural networks. This is the architecture. You could see the 2 neural networks, and then you dot product the output to get the result. You could see the loss curves are, it trained well, and the percent error is still quite low. So this was more experimental. We wanted to see if we could get the advantages of both operators in one by creating a hybrid. So for this model, we replaced the branch network, of the depot net with the FNO. And the idea was that it would inherit the best of both worlds. But unfortunately, it actually inherited the worst of both worlds. You still had to pre-process the data to input it into the FNO. And because the model was more complex, it took a lot longer to train. So this is what the architecture looks like. You could see that the branch network of the depot net was just replaced with FNO. And then these are the loss curves. You could see that the loss curves are a lot more sporadic and unstable. So this is a final comparative analysis between all models. In terms of scalability, the operators got a rating of 1, which is better. And then the neural net got a rating of 2 because it could only predict trajectory by trajectory. The convergence rate increased in complexity. The training time, the neural net being the simplest, trained the fastest. The deep net effectively being 2 neural nets, trained the second fastest, and so on. The learning rate was determined experimentally. And in terms of generalization, all the models generalized well. They did not overfit the data. Their percent error at the last epoch was the same as the percent error on the training data, which the models had never seen before.
So here are the calculated delta V and regolith requirements for 16 paths from Moon to Mars that we were able to define using the trajectories that were given by the neural operator. To define these trajectories, we first defined 3 major scenarios. Major scenario 1 is a minimalist architecture in which the only capability of the Starship is to refuel in low lunar orbit. This acted as a gauge for us to measure the efficacy of other future major scenarios. Major scenario 2 is based off of NASA's plan to use its Gateway's power and propulsion element to charge a solar electric propelled space tug. For the sake of further scalability, we decided to place SEP tugs in both low lunar and low Earth orbit. And for major scenario 3, it's similar to major scenario 2, but instead of solar electric propelled space tugs, it's bipropellant chemical space tugs in low Earth and low lunar orbit. Looking at the data here, the data highlighted in orange represents the 3 trajectories with the lowest delta V requirements. The biggest pattern that we noticed here is that all of these trajectories were direct trans-Martian injections, whether they were tug-assisted or not. And looking at the data highlighted in yellow, we can see the trajectories with the lowest regolith and propellant requirements. The trend we saw here is that they were tug-assisted translunar injections, and that they may or may not have included a tug-assisted trans-Martian injection. As for the interpretation of the results, we noticed a few major things. Lunar orbit staging tends to perform extremely poorly without space tugs. This is seen in major scenario 1, where the most efficient trajectory in both terms of delta V and regolith usage is the trajectory, which is a trans-Martian injection from low Earth orbit. Additionally, trans-Martian injection trajectories that use the precise trajectory were the most efficient in both delta V and regolith usage, but due to their sensitivity and relative newness in scope, we've decided that further studies need to be conducted to accurately estimate the practicality of this trajectory. And now, looking at our key takeaways, we can see that SEP tugs tend to outperform chemical tugs. They can provide more delta V percentage requirements, but this is a trade-off for time of flight, as chemical tugs have larger thrust and therefore can have slower time of flight. Additionally, we were able to define the optimal trajectories for unmanned and manned missions. For unmanned missions, we were able to see that a low Earth orbit to low Earth orbit refuel, to a tug-assisted translunar ejection to low lunar orbit, to a trans-Martian injection to low Martian orbit optimized regolith values, whereas for manned missions where time of flight is a significant factor, we were able to see that direct trans-Martian injections from low Earth orbit are optimal. And for future work, we would like to optimize orbital trajectories for a Starship-class vehicle using more analysis with neural operators, including both time of flight and 3-body problems. We would like to add time of flight into our model, as for crewed missions, time of flight is an extremely important consideration. Thank you all.
All right. Questions?
Good job, gentlemen. Describe how you went from regolith mass to fuel mass.
So we used a conversion factor. We assumed that lunar regolith is about 45% oxygen from recent publications, and then using Texas Tech's research on molten regolith electrolysis, they saw a 75% efficiency conversion. So we multiplied the two together to create a conversion factor from oxidizer to propellant, and we use a 3.6 to 1 propellant to oxidizer ratio.
And you assumed that the liquid oxygen could be delivered to a vehicle wherever it is.
Yeah, that is one of our key assumptions.
Okay, so another thing to put on your to-do list.
Yes.
How to get that there.
Questions?
Very good work, guys. Quick question regarding delta V. So this delta V that you are reporting is the departure delta V and arrival delta V. Am I right? What is that? How did you calculate delta V?
For all of the
for one typical trajectory from LEO to Mars capture.
So the idea was initially, I'll use an example for LEO. There's one delta V to escape Earth, and then the second delta V is to circularize at Mars.
Yeah.
And then if needed to get to low Martian orbit, which we took as 300 kilometers, there was 2 more delta Vs to circularize. Now, ideally, you already are at, the perigee of your approach is already at 300 kilometers, but sometimes it wasn't, so you had to do additional circularization.
Yeah, the delta V for departure is provided by the launch vehicle, whatever it is.
Yeah.
So, and then for the landing scenarios, you don't need to have any delta V. You directly jump into the dive into the atmosphere, and you basically land, or if you have a rover or lander, right? Unless you want to get into the orbit around Mars, then yes. But just want to clarify about this delta V. And for launch, for departure, basically as far as mission design is concerned, we don't say departure delta V. We basically, that delta V is going to be taken care of by launch vehicle, and instead we go with the parameter C3, which is the V infinity squared. And V infinity, I'm not sure how much you're familiar with the concept of V infinity, is you are, right? Yeah, so basically my point is, when talking about delta V, we have to be careful. It has different, so you need to have a delta V breakdowns, and then for mission design purposes, we don't basically consider launch delta V. It's basically launch vehicle to take care of that. For the lander or rover or whatever, we don't have an arrival delta V. Only delta V for typical Mars trajectory is DSM, which is deep space maneuver, basically. But for most of the practical purposes, we do not need to have also DSM. So pretty much you can get to Mars with a 0 delta V mission, a 0 delta V trajectory. So ballistic launch is going to be by the launch vehicle, and arrival, the whole energy of the spacecraft is going to be dissipated by the atmosphere. Okay,
Yeah. Sorry. We will take that into account in further studies, but for this study, the assumption was we're just calculating total delta V and to go into stable orbit around. But yeah, thank you.
Any other questions? I have one, maybe a final one. My understanding is that in the deep-on-net architecture, even the full neural operator, the Fourier one, you didn't put any physics, right? It's a data-driven only inversion. Is that correct?
Yeah, we were generating data as the model was training, generating in batches and putting it in, and the script would generate more data. To generate data or to train the operator on a whole moon, we had to vary moon parameters. So we might generate patch conic data for a moon that was slightly less mass, slightly more orbital distance, slightly more radius. And the idea was for the model to not learn the specific moon scenario, but learn the pattern of a patch conics calculation, and then we tested it on the real moon parameters, and that's how we got the results.
Gotcha. Some suggestion, if I may, for future work. You might want to put physics regularizer there. Basically do a physics-informed, deep-on-it kind of approach. The reason is because you're always solving inverse problems. Inverse problems are naturally ill-posed, right? That's one of the reasons why when you use differential operator, differential evolution algorithms or whatever genetic algorithms, the problem is that the landscape is always constellated by a lot of local minimum. You have to have a way to regularize it. So if you can put the physics of the patch conics into two bodies, fine. You should be able to get even better results and making sure that you regularize the inversion.
Okay, thank you.
Anything else? All right, thank you. Right, this concludes the session. Now we're going to have the final fireworks.
No, Maruti. La ruta. La ruta se llovía. Pero
Sì, sì, non c'è tempo, io volevo solamente questo computer. Just connecting.
Start in a few minutes.
Give me 1
Because-
minute.
Because you have remote connected, you want to wait for a few more minutes.
Yes.
Howdy. Let's start. This is the time we're all waiting for Professor Mortari to give us his keynote presentation. It is the end of a very successful symposium honoring Professor Daniele Mortari for the past 2 days. And the presentations were from colleagues from all over the world, students, current and former students, and interesting, very fruitful collaborations that have been built over the years. You see now how the discussions are influenced by all these long collaborations. Professor Jenkins sends his regrets. He had to go to see a doctor urgently because he most likely went to DC, Washington, DC, and he caught a cold or something, and he has fever, so he is doing well, but he couldn't come. Also, he didn't want to spread the virus to the rest of us. But he told me on the phone, even though I could sense from his voice that he was ill, for about 5 minutes, he was telling me what to say about Daniele, and I have forgotten all of it. You know the story about how they met in Italy, and it is not just because of the fine wine that they both shared. Daniele had a framework and an implementation that was much more efficient than John's. And if you know John Jenkins, he eliminates the competition by doing something better or by bringing the competition on his own side. And that is how this long collaboration in the late, early 2000, 2001, so 25 years ago, they connected. Daniele came and visited us. At that time, I was also at Texas A&M. And I remember John saying, I met this mathematical genius, and we must hire Daniele. And he was a great proponent for you, Daniele, coming to Texas A&M. And I know you started a great collaboration with John and with many other colleagues and students, joint students, who are now doing extremely well. Daniele got his PhD in nuclear engineering, safety of nuclear reactors, and that was his doctorate. And then, of course, he loved space. Space and nuclear reactors have something in common that he only knows. He spent, of course, quite a few years at the University of Rome, Perugia, so he spent quite a bit of time in Italy before he joined us, as I mentioned, about 25 years ago, where he became a professor of aerospace engineering. Based on his long CV, and there are many papers, as I mentioned also yesterday, about 500 publications, archival and conference proceedings, and 100 invited talks, presentations. That is quite remarkable. Daniele co-advised 20 PhD students, many masters and other visitors and postdocs. And he received many honors. When he became fellow of the Institute of Electrical and Electronics Engineering, IEEE, the citation was for his contributions to navigational aspects of space systems. So he became a fellow from IEEE, an aerospace nuclear engineer. It's quite remarkable. And then in 2015, when he received the Dirk Brouwer Award, the citation was for his seminal contributions to the theory and practice of spacecraft, orbital and rotational dynamics, particularly attitude determination and satellite constellation design. And you have seen some of these presentations from his colleagues and former students on these topics. Of course, there is quite a bit of discussion about some of the recent work he did, and I believe, Daniele, there are several PhD students who worked on these functional connections, and there are two I wanted to mention. So Carl Leakey, his PhD was on the multivariate theory of functional connections, and then Hunter Johnson studied with you on the theory of functional connections, a journey from theory to applications, and that was done in about 5 years ago, 2021, and then later on this continued, and it has impacted the field, even though it is just recent, 2 PhD theses in 2021. They have had a remarkable impact. So if I want to summarize in flower constellations, attitude determination, and then in this more recent theory of functional connections, you have made great contributions, and the impact is felt already and will be felt for the years to come, Daniele. I would like to ask Maruthi, where are you, Maruthi, to say a few more things, since you know the field much better than I do, to highlight some of his technical contributions. And then we have Daniele giving us his keynote presentation.
Okay. Howdy. Howdy. Yeah? Were you using this?
Yes, sir.
Yeah. Howdy. Howdy. Yeah. So I know that I'm the last gate before our distinguished guest of honor takes the podium. I'm going to be the last gate before our distinguished guest of honor takes the podium, so I'll try to be brief. And I also admit that due to the unfortunate last-minute Dr. Jenkins falling under the weather, I did not have a lot of advance notice to be able to capture succinctly the vast body of work that Daniele has contributed to our field. I'll start off with maybe on a more personal note. I've known Daniele, just like maybe many of us, for several decades now. My first interaction with him was when I was still what at that time I was a promising young man. I was a grad student, and I came across his first paper, ESOC. And of course that's an acronym. That's an efficient way that he came up with to solve the celebrated Wawa problem, computationally efficient way. Of course, he went on to improve ESOC, and that became ESOC 2. Along the way came OLE. I think someone was referring to that earlier as well in one of the talks, and that was using the Gibbs parameterization, but essentially solving that problem. And later, of course, he had a very fruitful interaction with the late genius Landis Markley, looking at robustness implications. And in every one of these pieces of work I would consider are seminal and foundational to the field. And of course, so I was a grad student, and I was tracking the ESOC 2, and it was one of those AAS conferences when I first saw Daniele in person, and he was still a professor back then in Roma. He was so, of course, as he still is, he's so warm and welcoming, and I was intimidated, but he kind of, he was really embracing. And I needed a ride back to Denver Airport. This was a conference in Breckenridge, I believe, my first interaction. And Daniele said, no worries, I have a rental car and you don't need to take this ridiculous shuttle and we can go together. And I shared a ride with him, and we had a bunch of, some time to spare before our flights to catch. And he said, yeah, let's go to Denver downtown. And what do? We ended up visiting the Mint, the Denver Mint. And we strolled around and we had a good time. And Daniele, I remember that. I'll also mention, over the years, of course, I think I can say that I have earned his friendship. I certainly am proud to say that Daniele is one of my dearest professional colleagues and friends. He certainly appreciates my South Indian roots and affinity for spicy food. And he introduced me to pasta arrabbiata, which of course he has cooked for me on multiple occasions to the extent that I have somehow reverse engineered or re-engineered. I can't say I make it just as good as he does, but my kids like it just as much. So what I do. But going back to research, and I kind of stopped at Ole and the work he was doing for attitude determination, but there was another vast body of work that I consider Daniele has made profound impacts with the K-vector. Essentially a way to search and process data, static databases, and obviously the motivations were for onboard star identification in the context of star trackers. But Daniele and his collaborators have went on to do remarkable things, including nonlinear function inversions and many other applications in different fields of domains of mathematics using the K-vector theory. And then, of course, the flower constellations the theory existed, at least the idea existed, in the early 2000s, but Daniele just took it off to a different level with the 2D lattice theory, the 3D lattice theory. I hope I can see certainly some of the mathematics. I hope they earn their way into the top 3 equations that he's going to present, but there's certainly a lot that I know, and I know a lot of us in this room have certainly enjoyed and appreciated the work that he has done in the flower constellation domain, which in today's context is highly relevant with the proliferation of all the constellations, Starlink and Planet Labs, and you name it, the VLEO assets that everybody wants to build. The questions that I think were articulated yesterday in one of the talks about capacity. And characterizing capacity, orbital capacity, I think, are very nicely framed in the context of flower constellation theory. And of course, there is the theory of functional connections. The last, but the most elegant, I guess, right? That what started out like 5 or 10 years ago, as Dimitri Lagoudas was mentioning, has grown into so many applications that you can use in machine learning and in multi-domain, multi-computational systems, not just astrodynamics, right? So, remarkable career. Congratulations, Daniele. Thanks for having all of us. Of course, you guys won't hold me for my affiliation from that other school, because I'm one of you. I went to school here, so I still bleed maroon somewhere. But we had such a good time. Thank you, the Department of Aerospace Engineering here at Texas A&M. Thank you, the College of Engineering. And thank you, all the volunteers, the staff. I know that Manoranjan Maji, who is physically couldn't make it to the conference, but there must have been a lot of back-end work in the technical part of the program that he was able to put together. We should also acknowledge, obviously, AAS and AAA for co-branding, co-sponsoring this event. But an amazing event. Of course, it's not done because the best is now right here. So let's all give a big, warm applause and welcome my dear friend, Professor Daniele Mortari.
I want to say many things, but my voice is limited anyway. So when I decided to prepare this talk, and looking back at what I've done during these past years, I can squeeze a little bit and boil down to essentially 3 equations. And that's the meaning of this one. What I want to give you an emphasis, not too much, application and things like this, but where this idea come from. So the origin, to give you a sort of a history of what's going on here. Okay. So I should say, a sort of life in 15 minutes. I will give you 1 minute of biography. So the beginning of, and a little bit about the beginning of research, but this has been already discussed everywhere. And then we go to these 3 equations, which are basically the rotation in any dimension, the flower constellation, and the theory of functional connection. Okay, so this is me, 70 years ago. That was my first experiment. I received photographer in my house because I became famous because I decided to start walking by grabbing to myself. Any walk. And so there are many of these pictures in my family. And I want to tell you also some things. I spent 8 years of my life in this institution, in 20 kilometers above Geneva. My father was an immigrant in Switzerland, and this institution collects son of immigrant, but also orphan. And I grew up, and my first language was French, because it was in a part. So moving forward, then I became doctor in nuclear engineering. I've been working at the Aerospace School of Engineering at University of Rome, occasionally teaching also in Perugia. And since 2002, I took a position here at Texas A&M, became a colleague of many of the colleagues here. So the initial research basically was essentially focusing on the concept of rotation at the very end, because attitude means working on rotation. And I developed various techniques in single point, with also in filtered, working with the Maggi and our new dean, actually, Dr. Bishop. We published a very beautiful paper, and I forget Renato Zanetti, yes. We published the filtered attitude estimation. Then the K-vector, but I'm not going to talk about the K-vector, so like this. So let's go directly on the rotation and orientation.
Okay? These two concepts, most of the time they are confused. They intended the same things, but they are different. They are different things. So all the stories start around 92 at Goddard. I was sent at Goddard for 2 years because I was working for the San Marco project. So commuting with Goddard, I became studying the AOCS, and I became aware about Landis. We became good friends. And during one of our discussions, Landis told me, you know, Daniele, in 4 dimensions you cannot rotate. I say, what are you saying, Landis? You can rotate in 2 dimensions, you can rotate in 3 dimensions, in 4 dimensions you cannot. He said, well, basically, you know, the proof that he came out with was pretty simple, actually, and was very convincing. And basically, the matrix performing rigid rotation must be a matrix, a special orthogonal matrix, an orthogonal matrix. So this means that is a real orthogonal matrix, so the eigenvalue must lie on the unit radius circle. So in 3-dimensional is easy because you have 2 complex conjugated that are associated with the angular rotation and 1 that is associated with the axis of rotation. No, because in the CE equal to E there is an eigenvalue equal to 1. Now in 4 dimensions, okay, you have 2 for the angle, 1 for the axis, where you put the 4th eigenvalue. And actually there is no room because you cannot put it at -1 because otherwise you have an axis that always flip 180 degrees. So you cannot describe 0 rotation, for instance. You cannot put it at 1 because otherwise this implies that you can rotate about 2 directions that are orthogonal. How you rotate simultaneously around 2 directions that are orthogonal? I came back in Italy, and the idea that solve everything appears to me while at the dentist. I was waiting that the injection make effect, and then I start to believe that yes, maybe in 4 dimensions you can rotate around the 2 orthogonal directions, not only, but any axis belonging to the plane identified by these 2 directions is also an axis of rotation. We cannot imagine. And so I try to write down the math based on this idea, and I figure out the equation. I figure out the equation, which is this one unboxed, is an equation that contains a little revolution. Because we always think about the concept of rotation associate an axis. So you rotate about an axis. But this axis in 2 dimensions doesn't exist. In 3 dimensions, yes. In 4 dimensions, doesn't exist. So the invariant parameters of the rotation is not the axis. It's these 2 planes orthogonal to the axis. Is different. And so in this equation, the big matrix P is a matrix which is basically listing 2 orthogonal directions. And this matrix here basically works in any dimension. It performs the rotation in any dimension. And it is made of 2 parts. The first part is an identity matrix plus something that is symmetric. The second part is what is called the two-form. Basically, a sort of equivalent of a cross product, basically. And so J is the 2x2 symplectic matrix. And so based on this, with this new element that is invariant with respect, you can do many other things, like rotation as a transformation of a subspace. You cannot do this when you consider the axis. And there is no need to introducing any extra dimension. Okay? And so using this formula, I found out, because my first equation is actually made of two equations. And the fact that starting from a four-dimensional space, the concept of rigid rotation and the concept of orientation, which is the displacement in space of a set of orthogonal axes, they do not coincide. A rigid rotation brings to the final destination only two axes. Now, in 3 dimensions, if you bring two axes at the final destination, you automatically bring also the third axis. And that's the reason why that rotation and orientation get confused. So Euler, basically with the principal axis theorem, but in n dimension, how to reach an orientation based on a sequence of rotation. And, you know, I've been working a little bit and I found an amazing formula. To give you an example, when you are in 4 dimensions and you make a rotation about an axis, rotation on a plane, all the subspace of that plane remain invariant. This means that in 4 dimensions you can simultaneously rotate in 2 fully orthogonal planes and the object is not broken. And you can rotate as you like. It's difficult to accept this. But this formula tells you, basically, that in order to obtain a given orientation, which is described by an orthogonal matrix C, this is a product of rotation acting on fully orthogonal plane in that space. And the amazing thing is that the product of this matrix is the same of the sum of the same set of matrices. I never see in my life something like this. A product of matrix that is typically doesn't commute, but the product of a set of matrices is the same of the sum of the same set of matrices, plus a diagonal matrix which depends only on the dimensionality of the space. And so, basically, this is what is the generalization of the Euler theorem. It tells you that you need NP rotation in order to reach any orientation, basically. Based on this study, basically, I found out 2 different sets of matrices. Well, not I found out. They were already existing. But matrices that are simultaneously orthogonal and skew-symmetric, and matrices that are simultaneously orthogonal symmetric. And I think I found out that these kind of matrices are the extension to the matrix field of basically the property of the trigonometric function. So they work like angle. It seems strange, but you you can write like the sine square of that matrix plus the cosine square of that matrix is the identity. And not only this, many. And I remember I published a paper called Matrix Trigonometry. Zero citation. But anyway, so now, yes, the theory is beautiful, but what you can do with this? So, long time ago, I found out that if you collect a given, if you take any object, and you spin this object about any axis, the quaternio in four-dimensional space describe a big circle. And so if you collect these vectors, the quaternion, in the four-dimensional space, and you perform the SVD of this collection of a quaternion, then basically, since the left singular matrix is orthogonal, they identify the plane that are a characteristic of my decomposition of orientation in a subsequent rotation. And so you can build a matrix which is made of the sum of these two forms that contains only information about the direction of the angular velocity. And so this can be used to estimate the direction of the angular velocity and also the angular velocity. And amazing, it was the singular value, the sum of the singular value is exactly the number of quaternions that you are considering. And so the purpose of this is that if you are in a poor spin, basically you will find sigma 1 and sigma 3 different from 0. And sigma 3 and sigma 4 equal to 0. Because they lie on the plane where the quaternion lies. And so this parameters tells you, hey, pay attention, because my attitude, the angular momentum, the angular velocity is a changing direction. And so this was my first block. Then Dr. Maruti Akella and also Zanetti's a student, they take this piece of work and bring to the professional level. So, and I was very happy about this. Okay, flower constellation, equation number 2. Now, also here, I want to say a little bit of story. But is first of all, I need to explain where is born the flower constellation concept. And the unintentional creator of this theory was actually Professor Broglio. Then I started to develop the theory as an engineer. So it was not really good. Then I found out a mathematician who told me, please step aside. Let me do the work. And then I will talk a little bit about the necklace. Okay. So in 1980, Professor Luigi Broglio, he was a 4-star general, a very powerful person in his field, basically without using a computer, only paper and his pen, he devised a system that calls Sistema Quadrifoglio, or 4-leaf clover system, where you can put 4 elliptical orbits on an equatorial plane, and you put the satellites in some specific position. And this position allows, basically the purpose was to provide information of the physical property of the upper part of the atmosphere, the troposphere, and communicate in real time all over the world. That was the main idea. I was in charge of, by Professor Broglio, to investigate the property of this system. Just to give you an idea, who was Luigi Broglio, I think this picture tells you everything. I had the pleasure to visit him several times, and there was pictures with all the Pope, President. Lyndon Johnson went to visit him. Von Braun went to his space base. This picture was taken inside the platform, I believe Santa Rita, in Kenya. And so what I want to do is to use all the program it works. So I know the program showing how does it work the Sistema Quadrifoglio. So these are the Sistema Quadrifoglio. So basically, you see that these satellites is going to close here. He collected data at the perigee for the troposphere. And so now let me froze when this is falling down, for instance. Okay. So you see that these satellites, it can collect the physical data and transmit to this one, that can transmit to this to the other, and also to the. And so you have a small network, a dynamical network, that allows in real time to transmit the data, basically over the world. And so while I was studying this this system, I found out something that I didn't believe at the beginning. But I found out this property here. These 4 satellites are in the same identical trajectory in a rotating frame. And so here you see that basically they constitute a sort of a juggling in space, coordinated juggling in space of these satellites, such that you have always some satellites around the apogee. So four eccentric orbits that actually keep 3 apogee persistent. And so after finding this, I went to Professor Broglio. I told him, Dr. Broglio, there is this kind of property in your system. And he looked at me and he told me why it should be important for the project. I don't know. Why should be project? And then, I left University of Rome. I came here. But this idea that placing satellites in the same relative trajectory, rotating frame, or even that belong to the same orbit, but in the same identical trajectory was obsessing me. And then basically let me stop here. I go back with that. And so basically I came out with a theory. So the orbit must be compatible, okay, resonant, and there is same semi-major axis because they need to have the same period. Same eccentricity inclination argument of Perigi. I distributed the orbital plane in Eveling mode using a ratio between two integers, Fn divided Fp. And then what was very complicated is to find where to allocate the satellites in order to obtain this. And this was what I found. And this was creating the flower constellation, basically. And you can see here in this formula, all the terms were integer. And the mathematics of integer, it belongs to number theory. So use this in order to perform optimization is difficult. And I have zero knowledge in number theory, but I saw that was a guy, a postdoc in number theory, giving a talk, and I went there to listen his talk. I didn't understand anything about his talk, just with the purpose to show him this. To show him this, I said, I need your help. And so, and this guy is Martin Avendano. And Martin basically was a postdoc in number theory, and he fell in love for what you can produce with all these integers. And he found out basically what the flower constellation is from a mathematical point of view. And he was basically he was a lattice of point on a torus. That was the topology, basically, of a flower constellation. Why was a torus? Because you distribute the mean anomaly between 0 and 360, the reductions of the node between 360, so all the bounds can be connected and you form a torus. The space is a torus, basically. And the flower constellation were basically symmetric distribution of this lattice because 0 and 360 must be the same. And so during the time, there is a rolling of these satellites in one axis and also in the other. And so basically you have, with Martin basically, and with the help of Jeremy here, basically we came out with the 2D lattice flower constellation. Then we were not satisfied enough, and we extended this not only in 2 dimensions using a mean anomaly and Radhanshenko, but extended also to elliptical orbit using the argument of Perigi. So you have a torus, 3-dimensional torus in a 4-dimensional space. And this is basically what is a flower constellation. This matrix here, basically, is called Hermite normal form. And basically, you can describe all lattice using a matrix made of integers. But it's cumbersome. And so there are some special transformations that minimize the number of parameters. And so you cannot transform like in spectral decomposition to a diagonal matrix. What you can do the best in number theory is to transform into a lower triangular matrix. And these are the minimum parametrization of a flower constellation, basically, where it tells you basically where to put in terms of a mean anomaly, argument of Perigi, and everything. Now, because of this double symmetry, triple symmetry in case of 3D, the theory allows very easily to compute if there is any collision between satellites. You don't need to check all the combination, but just a very few items, just because this is continuously self-repeating. I will show you some flower constellation in action soon. And so, based on this, we found out that this was for something like 3,000 satellites. And so we see at some inclination, there is the maximum distance, the minimum maximum distance is 400 kilometers. And this is associated with what we call the non-self-intersection satellites. So this relative trajectory, okay, it doesn't intersect itself. If it doesn't intersect itself, there will be no collision. You don't need to check it. But if you increase the inclination, you see that some very interesting inclination appearing around below 70, something like this. And as Richard Linares has shown with a mega constellation, they can easily describe it by flower constellation, basically. And they are this kind of okay. Let me skip a necklace. Yeah, it requires too much work. I want to show you some, just for those who never see flower constellation in action. So you see here, these are all integers. And so let me show you, for instance, some, you can build satellites in a constellation that does like this. So the constellation can be seen as a sort of a rigid object, where it continuously maintains its object in space. I don't know what kind of a space mission you can do with this. I don't know, but there is an infinite configuration with this property. Like this is another flower constellation. By the way, no, I want to say something here. This flower constellation, one of my students had a nice idea, because if you close this loop, they go through the magnetic field of the Earth. Basically, you build up, you take advantage of Faraday law of inductance. So you create a dynamo. This is a space dynamo, basically. So you transform potential energy in electrical energy. Now it doesn't work around the Earth because this transformation implies a decay of the orbit. But it may work around the Sun at a sufficient distance where you can compensate this decay with the solar pressure. And so, well, that was an idea, just an idea. Then let me show you this one. This flower constellation, for instance, has proved that, let me stop it, prove that you can keep satellites aligned for a long time using elliptical orbit. What kind of space mission you can do with this? I have no idea. But it's a property that I didn't know that was possible. Okay? And just let me show you this one. I like this. This is a sort of morphing constellation where he moves from a 5 circle to a pentagon. And you can build also group. So I can add another constellation, and in the second constellation I can put, oh, I love this constellation here, where the satellites, they fly in 3 by 3. These are the orbit. They are flying 3 by 3. And when they get close to the perigee, they rearrange themselves and they form 3 spiral. And so you, sorry. And here you have basically a group, flower constellation group. Well, let's stop here for the flower constellation. So, but let's go back. Okay. This is an example of a necklace. It's very important because you can embed into the design of a constellation the budget. Basically, how much money you need to pay to put for launches, how many satellites you need to manufacture. So this can be done, and it extends a lot. So let's go on and let's move to the theory of functional connection. Also there's, which is my, this appears around 2016. It happens in my life, unexpected completely. And at that time I was teaching numerical analysis, sophomore level, and I was teaching this, the Lagrange polynomial. Lagrange has proved that you don't need to invert a matrix to find a line passing through 2 points. You can directly write an equation. And this equation, basically, they have, I hope everything here, except someone from my family. But there are 2 terms that are called the switching function. When x is equal to x1, the first coefficient is 1 and the other is 0, and vice versa. And when I was writing this equation in the board, and at a given point I had an idea, and I stopped looking at this equation. I think the students, they start to laugh because they were thinking that I was not able to continue, or I forget something. But the idea that came to my mind was this. This is not the only way to build a switching function. You can put, any kind of a function there. Same structure, except gx1 that must be different from gx2, but g of x can be anything. And what is representing this? Is representing infinite functions that are forced to pass through these 2 points. And so this formulation is not anymore a function, is a functional, because it's a function of a function. And it doesn't work very well like this, because you have the function to optimize is on the denominator also, so it becomes a mess. for derivative and all these things like this. And so I decided, okay, let me start from the first simple things. How to describe all the function passing through one point. And I found 3 different ways. 2 points. Endpoints. How to include the derivative. How to include the integral. How to include the limits. And the appetite, you know, it comes eating, you know, you say in Italy. And so, and this is basically the formula for a univariate theory of functional connection. So it provides you a functional for n constraint. And these n constraints can be as crazy as you think. But they must be linear. And you have the switching function, phi k, okay, that must be built by inverting a matrix, basically, and the projection functional that depends on the free function. So just to give you an idea, this is, if you know the derivative at x1 and at x2, this is the function that describes all possible trajectory satisfying these 2 constraints. And this includes also partially defined trajectory, okay, or discontinuous trajectory. So you can put on g of x whatever you want. Whatever you want. This function is basically constrained to pass through these 2 points, to have these 2 derivatives. And this is an example, for instance, for an integral constraint, where I take 2 damper oscillation at the edge, and I impose that the connection, the function connection these 2 points must maintain the integral for all the... And one of my students told me, you should put a fish over there. This is basically what I'm talking of, what I mean by constraint. A constraint is basically ruled by a linear operator, which is this C of k, is the k constraint, acting on a function. For instance, an example is this. We can accept this constraint. So it's not only constraints like a point, or line, but also linear combination of derivative, integral, and so on, equal to some 1. When you know this operator, because you know your constraint, the projection function are very easy. It's the same things, but written in terms of a free function instead of the y function that you're looking for. Many things happen using this formulation, and one of these aspects is basically a sort of interesting property for the Taylor expansion. If you look at this equation and you do not consider the term in G, this is the Taylor expansion. If you consider only n term, you have an approximated value. But if you write in terms of the theory of functional connection, you have the exact value for limited truncation. The problem is that you need to find what is the free function. Okay? So these are all properties that should be analysis. And then we start with the, I've been blessed and very lucky to hire 2 amazing students, Carlick and Hunter Johnston, right after I discovered all these things, they were so amazing by, really enjoy working on this theory. I remember I left Carl Hunter telling next week, try to do A, B, and C. They can, 2 days after they did A, B, C, D, E, F, they come down. So at the very end, when after a few, so just let me tell you one thing. They graduate, these 2 students, they graduate. They took the PhD with the 20 articles each, plus a book. And I remember that we were brainstorming continuously in my room, and sometime in my house we were eating. So cooking Italian was part of the PhD program, basically. And so we moved from univariate to bivariate, so in 2-dimensional, to n-variate, multivariate. And in multivariate, it comes out, this is the expression, basically. In multivariate, you can see this is the tensor formulation of the theory of functional connection, which is a theory of functional connection is nothing else than the generalization of interpolation. Not one function pass satisfying constraint, but all the functions. And so this part is uninterpolated, whatever. I don't care how you interpolate this. You interpolate this. The second part that you add describe all possible manifolds that are zero at the constraint. So the second part doesn't disturb the interpolation to satisfy the constraint. But it disturbs inside. So you have all the variation inside. But you don't need to change the constraint. Examples are many. This is, for instance, using equality and inequality constraints. And so to describe all the trajectory under 2 bounds and then pass through the 2 points. By the way, inequality constraints, sometimes it appears to me not the right definition of something, because inequality at the very end is a sort of a domain definition. So you want to satisfy in this domain. And so the domain is inside these 2. And this one was in a bivariate. And there are, I think, 3 constraints which are the boundary, red curve. There is a 3 in one direction and 4 in the other direction. And I use the free function with the modular arithmetic, so that you obtain a discontinuous surface, but it satisfies the constraint. It's forced to satisfy the constraint. This is one of the first example in trying to apply to solve the differential equation. It was a 3rd-order differential equation. And we compare with the state-of-the-art, which is a ChebFun that uses spectral method, collocation method, and so on. And we push both the theory, the TFC, by increasing the number of basis functions, because at the time we were using, I think, Legendre polynomial, and the parameters to increase. And we obtain 8 order of accuracy better. 8 order. So it's not a small gain. And 2 order of spin gain. So he was solving at less than a millisecond, almost at a machine learning, machine accuracy. Then I apply this to many things. This is an example to curved surface, where you are talking about geodetic. And this is a way to solve the problem of boundary value problem on curved space. So that, for instance, on the top, you have an initial guess, which is the black, and the algorithm converges to the red, which is one definition that I love very much about geodetic is that a geodetic has the acceleration always orthogonal to the tangent plane. And when you have this characteristic, then your velocity in the curved space is constant. And that's the reason why the speed light is constant, because it's following a geodetic. If you are following a geodetic, then your acceleration is always normal to the tangent plane. So you say one thing is the same. And this allows you, for instance, to solve boundary value problem usually in the relativity, for example. You shoot a light in one point, and what they are doing? They are integrating using the topology of the space-time, right? As initial guess point, because you know the point and you know the velocity also. This allows you to solve the boundary value problem. Where I should shoot the light in order to arrive here. Okay? And so these are all boundary value problems for what this is an example of a two impulse in a 4-body problem from the Earth to the Moon. 4-body because we include also the Sun as a gravitational, and the right and the left trajectory are associated with the final 10 minutes. With the final purpose of rotating in a clockwise or in a counterclockwise around the moon. So when they get close, you will see that one rotates in one side and the other in the other side. This is an example on how to apply indirect optimal control to land on asteroid Bennu. This work I need to acknowledge Dr. Furfaro and his group that they have done a lot of work using TFC. And here you see that basically you split the whole trajectory with the two waypoints where you enforce the continuity, basically. And so why is the TFC is powerful? Because when you have a constraint optimization problem, when you have a problem in general, you look your solution in the whole function space, right? And then you try to enforce your constraint. But if you use this functional, then you collapse all the whole function space to just the subspace where the solution is. And so you deal with a subspace that is much, much smaller. Not only that, but you transform a constraint optimization problem into an unconstrained, and then you can use a more easy problem to solve, more robust, more accurate, more fast things. Now, embedding a constraint in an optimization problem is classically done using Lagrange multiplier. Successful you classically done with the Lagrange multiplier. So you can embed the constraints, but the theory added some new variable, the multiplier. Now, it's my experience that sometimes it's easy to compute the multiplier, sometimes it's difficult, sometimes it's literally impossible. While TFC doesn't add any additional variable, and there is no obstacle to write the constraint function. Is everything straightforward, easy. This is just summarizing what you can do. You can use constraint on point derivative, limit component, fractional operator also. So derivative, fractional derivative, like 1.3 derivative or 3/8 of integral. So some inequality. And so this can be used to solve ODE, PDE, integral differential equation, quadratic problem, nonlinear part, so many things. Just going very fast and showing you one thing that is interesting is that every mathematical structure that allows to be described by a minimum parametrization, you can apply TFC. To give you an example, if you take a unit vector it satisfies a quadratic constraint. No? So if you try to apply, you obtain an equation is quadratic in the free function. But unit vector can be parametrized by a minimum. And you apply to each one of these. And this idea can be applied to matrices. For instance, I can interpolate matrices. You have an orthogonal matrix at the time T1, or a symmetric matrix, and I can describe all the trajectory of a symmetric matrix that pass from one to another. So interpolating mathematical structure, preserving the structure of that mathematics. An example of this, for instance, is in the Gaussian, n-dimensional Gaussian. N-dimensional Gaussian, for the mean, there is no problem. The mean is unconstrained. For the covariance is symmetric, and so it can be decomposed in eigenvectors. You need to compute the inverse. You compute the inverse using the Schur decomposition, so it's a function of a matrix. And that's it. And you can add also the singular, the sigma k be persistently positive using Heaviside function. This is an example that you start here from with a two-dimensional Gaussian, and you have at the end a two-dimensional Gaussian. I choose randomly the variation of each one of these parameters, and it gives you this kind of dispersion. This should be done inside something. Give me another minute. One student of mine has proven that you can apply TFC to any vector space. And this is really, really crazy, because that formula on top is looking for a function whose parameters is a 2x3 matrix. And it spit out a vector. And this is a relative constraint, and it works the same. You can apply this to this. You can apply to finite field. So where you need to deal, you need to do your, this is important for cryptography, for instance, where you need to deal with only 4 objects, 0, 1, A, B, using an addition and multiplication table. It works the same. You can use from a function that maps string to complex number. Okay, so for instance, this is a constraint. F using tau plus F using TFC is equal to F grid. It works the same. And he has a lot of examples. And this is, I would like to at least show, sorry, okay. I would like to show you what I'm trying to do now. Basically, this equation, x squared plus 1, what is x? It's the square root of minus 1. Nobody knows what is an imaginary number. Okay? But this equation can be written in this way. So x squared plus 1 squared equal to 0 squared. And this is a degenerated Pythagorean triangle. It's a triangle that basically has two sides, one that's square to 1, one to minus 1, and the hypotenuse to 0. Well, elements that square to 1, or minus 1, or to square to 0, they are called geometric numbers. Using the geometric numbers, you can build any kind of algebra. For instance, if you use three numbers that square to 1, you have the Euclidean space. If you use three elements of square to 1 and 1 that square to minus 1, you have all the space of a relativity theory. Now, when you have a sum of 3 elements, space square minus c squared t squared. If you use 3 elements of plus 1 and 1 0, you have the projective element. And basically, based on this geometric number, you can build the geometric algebra. The geometric algebra is really, really powerful, but it requires to reset your brain completely. So when you find the geometric algebra for the first time, you are in love. But then you start to sweat. It's very powerful. What you can do with two vectors? You can build a scalar product or a cross product. So Clifford basically invented the geometric product, AB, which is the scalar product plus the external product, which is basically an area. So it's a scalar plus an area. Well, this product, AB, can be inverted. So if you have AB equal to something, you can recover A or B. So you can compute the inverse of a vector. And this, in this formulation, this includes complex number, quaternion, spinors, geometric, whatever. Lie algebra, differential geometric, everything is included there. In a unique formalism. And the most powerful element of the geometric algebra is what is called the multivector. The multivector is basically an object that has a scalar, C1, plus the 3 elements of the vector. These 3 elements, E1, E2, E3, are the geometric number that square to 1. Okay? Then the bivector, where E1, 2 is the geometric product of E1 times E2. And then the 3 vector. So it's 8-dimensional space. You can describe with this object everything. To give you an example of the power, the 4 Maxwell equations, basically in geometric algebra, are written as a single equation in terms of multivector. And these 4 equations are nothing else the scalar part of the multivector, the vectorial part, the bivector part, and the trivector part. And obviously, you can apply TFC, a multivector. And I think I will stop here. But let me go I prepared a presentation of 2 hours, I think, something like this. Okay. So first of all, I want to say thank you to all the people who organized this, to you guys that attended, to who put the money on this, so that the registration is so cheap. The College of Engineering, Department, Aerospace Engineering, and the Institute of Scientific Computation of Mathematics. Then there is also the blessing of our American society. A special thanks, I want to say thank you to many, because a lot of people, I didn't do everything here. I had the help of many people. But I want in my life to say a special thank you to this folk. Don't want to mention.
Cheers are okay. I'll Photoshop it out.
everyone. So the dinner is all ready and set up in $2.99. So it's going to be the room that we had lunch in if you just go out of those doors and to your right.